Yeah, somewhere all set.
All right, everybody. It is 9, so we'll get started. It is my pleasure. Let's see. Are we all ready? It is my pleasure this morning to introduce Yuji Shi. She is coming to us from CMU, where she has my new favorite professor title, the Sense of Wonder Endowed Professor in Electrical and Computer Engineering. So that's career goals. And she has numerous contributions to the foundations and theoretical underpinnings of data science, machine learning, inverse problems, has won numerous awards, including the prestigious PCASE Award, and we're very excited to have her open up day 2 of DeepMath. So thank you.
All right, thank you so much for the introduction. How do I get the slides up? Oh, awesome. So it's my great pleasure to be here today, and I'm going to kind of talk about 2 work that we have done. One on sort of the low-rank models, the other is on diffusion models. But I think the sort of the underlying theme is that connect them is that we are using them to as a way to model data priors. I thought it would be fun to let this work. I tried this work before, but oh yeah, works now. I thought it would be fun to open with a picture generated by ChatGPT to describe mathematics of deep learning, following Aaron's example yesterday. And this is sort of my attempt. All right, So let me get into the main content. So we have a lot of data these days, and that's sort of because we have a lot of imaging and sensing modalities. And if you have read the recent monograph by David Donahoe titled Data Science as a Singularity, I think one main contributing factor that he attributes to a lot of the nice things, wonderful things we've seen in AI these days is not because AI is at a singularity, but really because we have data science as a singularity. We have a lot of data that we can leverage to drive the design and development of new machine learning AI models. So as someone trained originally in signal processing, one of the problems I care a lot is the so-called inverse problem, which is essentially trying to extract useful information from data. And often, because the way we are collecting data, we have a lot of limitations in the way we can collect data, we can design our equipment. Often the data is kind of indirect measurements of what we are really interested in observing. And the data often are very limited in its size, can be very noisy, sometimes even corrupted. So often we are dealing with problems that are very yield-posed. So examples can be, for example, the very famously known problem like phase retrieval, and there are also a lot of imaging problems in computational imaging, like medical imaging, microscopy imaging, and so on and so forth. Because these problems are often very yield-posed, we can think of this as essentially like we are trying to find some kind of needle in a huge chunk of haystack. And in order to do so efficiently, we cannot just purely rely on the data itself, but often have to try to gauge some prior information, prior knowledge about the data in order to make the problem tractable. And this has been sort of the pursuit of a lot of the work we've seen in applied math, in signal processing, imaging communities. And roughly speaking, you can sort of classify the prior we're putting on the data in kind of two categories. The first type is what I call kind of subspace models. This encapsulates models such as sparsity models, low-rank models, union of subspace models, and things alike. And in order for you to use these models, it's kind of the head work is kind of small in the sense you don't really need to have training data to train such models, but you're really using your domain knowledge to figure out what is the right prior to use. And often these kind of subspace models are simple, they are interpretable, they are kind of parsimonious, that a lot of nice structures we like about them. On the other end, we've seen that increasingly people start to try to train more powerful, more expressive priors in the form of neural networks. Right? So there's a lot of methods that has been developed along this line of thinking. Unlike the kind of subspace methods, often in order to use neural networks as data priors, we often have to do a lot of training at the beginning before we can actually use them to solve our inverse problems. And often the data requirement is quite huge. You have to have a lot of training data, a lot of prior data in order to kind of train a good model for this. And people have developed a lot of architectures for doing this. For example, there are GAN models, VAE models, and recently diffusion models have been really taken off. And that will be sort of also one of the focus in my talk today. So besides these priors, of course, one of the questions that we cannot ignore is also the algorithmic perspective, right? Given these priors, or given the way we want to model these priors, how do we actually approach them and make use of them to solve our problems? What is the algorithm we are going to use? And often, people just use almost the most simple method you can think of, that is some kind of local iterative methods, such as gradient descent, stochastic gradient descent, and so on and so forth. Why are they so effective? How can we understand their performance? What are the kind of convergence properties we can talk about them? And that's something I want to talk about today. So with that in mind, I'll share two recent work in my lab, and one on sort of each side of the priors. The first one is focusing more on the sort of classical low-rank structures, where we are actually taking kind of an optimization perspective. So the problem we're going to look at is kind of a prototypical low-rank matrix sensing problem, but with over-parameterization. So you can talk about a lot of fancy questions like generalization, connecting to deep learning, but we are also caring a lot about yield conditioning, the condition number, which is often the hidden line in the problem we are solving in practice. So we're actually going to talk about the sort of preconditioned version of gradient descent, and we're going to show particularly the interplay between preconditioning and over-parameterization. Because typically when you think about preconditioning, you think about it as a mean to accelerate optimization. But it is actually not clear while you're accelerating optimization, do you still get a solution that generalize? So that will be something we want to talk about in the first part of the talk. Another question I will be talking about is sort of moving towards understanding diffusion models, taking a model of a sampling perspective. So in particularly, we'll be looking at the question, if you are given some kind of good score function estimates and you want to generate samples based on the score estimates, how fast you can actually sample. So this is sort of the second part of the talk I will be focusing on. So with this sort of brief opening, let me directly jump into sort of the first part of the talk. And this is based on joint work with my student Xinyu Xu, who's a PhD student at CMU, and also Yandy Shen, who is currently a postdoc at Yale, but actually he will also be joining CMU next year. And also my colleague Tong Ma, who's a faculty in statistics at the University of Chicago. All right. So let me start by setting up the problem. So I'm sure a lot of you are probably very familiar with this problem. This is kind of a prototypical model that you can think of. Let's say we start with some sort of big data matrix M of size N1, N2, but the rank of this matrix can be very small. So the rank R typically is much smaller than the ambient dimension. Instead of directly observing this matrix, often we have access to measurements of this matrix through some sort of linear map, some kind of sensing or imaging device, resulting in a collection of measurements Y. And the number of measurements we have typically lies in this so-called sample-starved regime, meaning it is not enough for you to just directly recover the matrix without using any prior. So it's much smaller than the ambient dimension, but maybe just barely enough if you can leverage the underlying low-rank structure. So with this kind of, in this kind of regime, the use of the low-rank prior is really important. It is really critical for you to make the problem kind of well posed and solvable. And the intuitive way for you to address this problem is to take this kind of low-rank factorization approach. So let me explain this a little bit. So imagine maybe one of the most natural way for you to write out an objective function for this problem is just to seek some kind of a rank R matrix, if you know the rank, that minimize observation residual in, say, the least square norm sense. However, instead of directly optimizing over the big ambient matrix C, I'm going to actually take this factorization that directly leverage this low rank structure. So I'm going to actually write my matrix C as a factorization of two tall skinny matrices X and Y. Each has a dimension that's proportional, roughly speaking, to the rank of the matrix. And then I can actually directly plug in this factorization and drop the rank constraint and try to do optimization over the matrix factors X and Y. So this gives me some kind of unconstrained optimization problem. This is going to be more tractable because I'm directly optimizing over a problem space that's sort of proportional to the underlying degrees of freedom rather than the ambient dimension. Nonetheless, the problem becomes non-convex, right? Because I can no longer uniquely specify these factors X and Y. They can only be specified up to some invertible transforms. So obviously, this problem is non-convex. So the challenge is how can we actually understand sort of the convergence properties of this kind of problems. Nonetheless, there has been a lot of work that has been done in the maybe past 10 years-ish that has put down a lot of good understanding about convergence behaviors of this problem, especially when the sensing operator A has nice properties, such as when it's generated from maybe some Gaussian ensemble and things alike. And often you get to see convergence curve like this. So this is an example that's plotted for the problem matrix completion. where I only get to observe maybe a small number of entries randomly selected of some low rank matrix. And I try to just run this vanilla gradient descent formula on top of it using some kind of spectral initialization. As you can see, the nice thing here is all these curves are decaying linearly fast, suggesting you have a linearly convergent algorithm despite of non-convexity. So this is really nice. But if you are careful, you immediately observe that if I tweak the underlying matrix, where everything is the same, except that I'm only changing its condition number. So condition number is just the largest, the ratio of the largest non-zero singular value versus the smallest non-zero singular value. And you can see actually the convergence curve kind of becomes slower, slows down as you increase the condition number at a linear rate. And this is actually not very appealing or pleasant, because often in practice, the problem we're dealing with are highly U conditioned, especially when you are trying to discover some kind of weak signal, or if you have closely correlated or closely located sources and you want to tell them apart, you often are dealing with problems that are very U conditioned. So when you are facing real world problems, even though you have this kind of nice linear convergence guarantees, in practice, you often observe gradient descent converges very slowly because of this conditioning number. But on the other end, gradient descent is really nice, right? In machine learning, we use it all the time because you can parallelize gradient descent very easily. You can distribute your data and run this kind of procedure in a distributive fashion in an almost seamless manner. So we still want to use gradient descent type of algorithm, but we want to get rid of the condition number. So the question is, can you actually accelerate the convergence by getting rid of the condition number to a rate that's sort of provably like dimension free, right? So that's kind of the first question we addressed. And in our work a couple of years ago, we developed this formula that we call scaled gradient descent. So in this approach, this is a really simple method. It basically follows kind of the setup, this two-stage setup that people have for understanding gradient descent in the past, in prior work. So we use the same spectral initialization. But the one key change we are doing in the algorithm is how we do the gradient update. So instead of following the vanilla gradient in these problems, we actually scale or precondition a little bit. And the way we are doing this is basically, say you have two factors, x and y. You're going to precondition your left factor x using information from your current iterates of the right factor y. So remember, these matrix factors are tall matrices. So I'm going to construct, say, this y transpose y. And this is just going to be a small, tiny R by R matrix. And I'm going to take the inverse of it, which is computationally cheap, and then attach this to the right of the gradient. Similarly, I do the same for the right factor, but using information from the left factor. Okay, so very small change. If you have implemented gradient descent, you can very easily update your code and try this new version. And intuitively, what this is doing is kind of doing preconditioning. And it's also doing this on top of this vanilla gradient loss, least square loss without adding the so-called balancing regularization that you often see in prior work when people try to run gradient descent. Okay. And so how does this formula really work? If you try to run this on the same toy example I showed earlier, and you can immediately see that the convergence curve of the scale gradient descent method actually probably actually get rid of the condition number dependency. In the sense, no matter what is the condition number in use, they all kind of lie on the same curve. And in fact, they lie exactly on top of the curve of vanilla gradient descent when you have perfect condition number. So this means you can get a huge computational saving when you replace the use of gradient descent by this scaled gradient descent method, because now we have a convergence rate that is condition number independent. And the saving can be quite considerable when the condition number is large. Okay. And we were actually able to make, so now you see the performance. You may wonder, why does this work, right? What is the underlying rationale for this to work? I'm not going to show you the full analysis, but just give you a little bit of intuition. And one of the key reasons we think that makes things really nice is this scaled GD has a nice invariance property. In the sense, remember that when I factorize this low rank matrix, there is some ambiguity in my factorization after some invertible transform. So if you choose different invertible transforms when you factorize these two factors, even though they give you the same low rank matrix, but when you rank gradient descent on these 2 points, their trajectories can be very, very different. But on the other end, if you do scaled gradient descent, the next iterates will actually be always covariate. They will change accordingly with respect to the same change of the invertible transform. So on the other, in other words, if you think about the trajectory as something over the low rank matrix manifold, you always get the same trajectory, even though you are implementing this in the factor space. Of course, to make the analysis really go through and to realize the condition-free, condition number-free convergence rate, we have to actually open the kind of black box of the gradient descent iterates and carefully analyze the trajectory of the algorithm by using kind of a distance matrix that is actually incognizant of the underlying preconditioning we are using. So this is also kind of one key factor for getting a good convergence rate. So if you do all of this, you end up getting this there seems to be a delay. You end up getting this convergence rate. So I'm only showing kind of one simple version of this. In the paper, we actually also look at a lot of other sampling operators. But let's say you are working with a very typical Gaussian design for these problems. And if you just use the standard spectral initialization, you can actually show provably that the scale GD algorithm converge in a number of iteration that is logarithmic with respect to the accuracy. So in order to reach some epsilon accuracy, it only takes you a number iteration on the order log 1 over epsilon. And this is happening at the same statistical sample complexity that is required by prior work, such as gradient descent, as long as the number of sample is greater than the degrees of the freedom of the problem up to some factors of the condition number. So this actually gives you some kind of strict improvement of gradient descent in the sense, under the same statistical requirements, you can probably accelerate the computation. So everything seems to be nice so far. But if you are careful, you may be very suspicious that I actually cheated a little bit up in the front when I say I know exactly the rank of this problem. In practice, often you do not know the rank, right? This is actually a parameter that you have to estimate very carefully, the problem related to model selection, right? So what if I do not know the exact rank? And a typical thing that people do is try to do over-parameterization, right? If you do not know the rank, it's probably safe for you to overestimate a little bit. So instead of factorizing the problem as the exact true rank, you actually use some rank R prime that's larger than the true rank. And in this case, I'll be only working with a positive semi-definite case for simplicity. And in this case, my scale GD algorithm becomes a little bit simpler. It's just one update formula over this factor X. However, I may encounter some kind of an issue because if the parameterized rank R prime is larger than the true rank, and in my update rule, I have this kind of inversion on the R by R matrix, which is now become an R prime by R prime matrix. So this matrix itself may become numerically unstable, even yield conditioned. Right? And not only that, my analysis also breaks down. So I have to actually modify things a little bit. Fortunately, there is a very easy way for you to modify things. And this is intuitive, very similar to when you try to just do some kind of ridge regularization, but just, sticking into plugging in some kind of scaled identity before you do the inversion. And this actually makes things work. But there's another question that kind of brings up when you try to deal with over-parameterization in these problems. Because when you over-parameterize this kind of low-rank problems, you no longer have all the nice fairy tale stories about all the local minimum or global kind of story. You end up now starting to have infinitely many global minima, but not all of them will generalize. So the interesting question here is, if I have preconditioning, and I know preconditioning helped me to accelerate optimization, so I can find global minima faster. But am I still guaranteed to find a minimum that actually generalize? So this is no longer clear. And in fact, people have been thinking about similar questions in the deep learning literature. So this is actually one of the paper title I put down, where they were asking a similar question, but for different problem context. In the sense, does preconditioning actually help or hurt generalization? So in our context, basically we want to understand when I try to run this kind of scaled or preconditioned version of gradient descent, do I still at the end of the day find the low rank matrix I want, even though I'm over parameterizing? So fortunately, the answer is yes, but you have to be a little bit careful about how you actually do things. So there are a couple ingredients here. One of the probably key things that we are doing here is, again, this kind of small random initialization that I think yesterday there are people also talk about this kind of initialization schemes. So if you do small random initialization and pick this parameter lambda, which is the sort of the regularization thing you add in the preconditioner, on the level of the smallest singular value of a low rank matrix, you can actually guarantee at the end of the day, you can find the low rank solution up to some absolute accuracy, again, with a number of iterations that is almost independent with the condition number at a similar sample complexity as before. So in fact, our analysis also give a exact convergence guarantee and a random initialization if you have a correct rank specification. So that sort of generalizes the previous theorem I mentioned when you have exact rank specification, but we're using spectral initialization. All right. So let me sort of illustrate this theorem a little bit and contrasting this with sort of over-parameterized gradient descent. And both algorithms, as you can see, kind of have some kind of two-phase convergence when you are zooming in on sort of the reconstruction error. In the sense, the algorithm, initially, you do not see really any decay in terms of the reconstruction error for some amount of time. And after that, you see some kind of linear convergence. So over-parameterized GD has been analyzed by this nice paper by Stoger and Sotano-Totabi, where they show that essentially the first phase is doing some kind of feature learning. They're trying to pick up the right signal space. And this phase take a number of iterations when you ignore log parameters on the order, say, the polynomial factor of the condition number. And after that, it takes another number of iterations as sort of a linear convergence, but with a prefactor that depends again polynomially with a condition number. So both of these phases has quite pessimistic dependencies with the condition number of the problem. Now on the other end, if you run our scale GD algorithm, the initial phase is really, really very sharp. I have to actually zoom my picture in order to show this. In practice, when you run this algorithm, you really see the initial phase because it just takes maybe a small number of iterations. So in the theory, we show that the initial phase takes, roughly speaking, log factor number of iterations. And after that, you get into this nice linear rate of convergence as what we see in the exact parameterization case. So the convergence rate again becomes condition number independent in the second phase. So what this is suggesting is our scale GD methods actually pick up the single component much faster than gradient descent, even when you are using this kind of small random initialization, suggesting this kind of inductive bias or implicit regularization is also happening, even when you have this preconditioning in your algorithm. So let me just say very quickly a little about the analysis, trying to maybe provide a little bit of message about what is happening in the beginning phase of the algorithm. Again, this picture is a little bit of enlarged to highlight these different phases. Their length shouldn't be taken as is. It's kind of like a cartoon-ish illustration. So roughly speaking, there are like 3 phases of convergence. And just like the case with the exact parameterization, one important thing that we need to do when analyze this kind of precondition algorithms is to figure out kind of the preconditioning effect. So a lot of the metrics we are tracking in this preconditioned version of this algorithm are also scaled according to the spectrum. I'm not putting the formulas here, but if you're interested in the details, you can look at our paper. So the first phase of the algorithm is very similar to what is happening when you run vanilla gradient descent. In the sense, you can think of this as doing some kind of approximate power method. And one of the key curve you want to look at is kind of the green curve. So essentially, after this initial phase that takes, roughly speaking, logarithmic number of iterations, you can ensure that the leading eigenvectors of your iterates actually are aligned with those of the adjoint operator applied to your observation, and while still keeping the other eigenvectors relatively small. In the second phase, this is kind of the middle phase. What is important to observe is sort of the signal strength. And in this phase, we are starting to see the signal strength actually grows exponentially, but still unbounded at a constant rate. And this is very important because in gradient descent, the signal strength will grow very slowly, suffering from the yield conditioning. But with scaled gradient descent, we can actually ensure the signal strength is ramping up exponentially fast at a constant rate. So that is, again, also just take logarithmic number of iterations. And after these 2 phases, you kind of getting into the local regime that's very similar to as if you have the exact parameterization and things to just start to converge very similarly to the original scale GD method. So in fact, you can drop the lambda I, drop that part and just use the vanilla scale GD method. And in this case, you can track the reconstruction error of the method, which now decays exponentially. So with all these phases in place, we can basically get the theorem we just showed. All right. So this is, again, just very high level perspective of the underlying dynamic of the algorithm. And this is kind of also in line with a lot of analysis that you heard about and you've seen in the literature about understanding the trajectory GD type of algorithms. But one of the key things we have here is how this preconditioning sort of plays a role in getting rid of the condition number dependency in the convergence rate. So one last thing I want to mention about this method is you can actually also go beyond this kind of exact low rank matrix recovery problem, but also allowing yourself to deal with a more general problem where the underlying matrix can be not necessarily exact low rank, but only approximate low rank, coupled with additional noise in the problem. And the question is, can you actually expect this kind of non-convex paradigms can deliver kind of mini-max optimal rate for this kind of noisy reconstruction problems? And the answer turned out to be yes. And this is kind of just a highly simplified version of the theorem, but I want to just show a little bit of the flavor in the sense when you have approximate low rankness and the noise in your observations, you expect to have 2 types of errors in the reconstruction, right? One is sort of related to the noise floor, how large the noise is. The other part is related to how good the low rank approximation is. And both of these terms actually depends on the exact the true low rank R rather than the over-parameterized rank, right? So this again ensures that this algorithm is really learning the underlying low rank solution, even when the model is sort of imprecisely prescribed or when your measurements are sort of noisy. And this result is optimal up to some dependency on the condition number. And this dependency on the condition number, just to highlight, this is in terms of statistical performance, right? But we are getting rid of the dependency on the condition number from the optimization perspective. We're now claiming that we are finding a solution that has a better quality than gradient descent. But we're just saying by using this preconditioned version, you can find basically the same solution or the same quality solution at a much faster rate. Right? So the gain is computational. All right, so with that, let me just quickly sum up the first part of the talk. I think the message is very simple. If I want to summarize this in a slogan, it's basically preconditioning helps. And we think there's a lot of interesting directions for people to examine sort of the power of preconditioning for other type of non-convex learning or deep learning problems. One of the immediate problems that might be of interest is actually analyze over-parameterized scale GD for the asymmetric version of matrix sensing, which turns out to be not as straightforward. So that's why the result I showed in this part only work on sort of the symmetric case. It's actually interesting to extend this to the asymmetric case. And as I mentioned, it will be interesting to also leverage scale GD to other learning problems. We've had some separate papers that we actually apply this kind of scaling idea to problems such as super resolution, where you can also get rid of dependency in terms of the dynamic range of the signal profile in the convergence rate. So that's sort of all I want to say about this part. All right. Now let me move to maybe the second part of my talk, which will be focusing more on sort of understanding the non-asymptotic convergence of diffusion-based or score-based diffusion models for generative models. And this is based on joint work with Skin Lee, who's currently assistant professor now at CUHK, and also my colleague Yuxin Chen and Yuting Wei, who are faculty at University of Pennsylvania. All right, so what is generative model? So a generative model has been very powerful as a way to sort of help us to learn data priors. So imagine if you have some training data given, which are collected by drawing from some data distribution. For example, I may have data pictures drawn from the distribution of houses. And the goal is to learn some kind of generative model where the model can actually allow us to generate new samples from this data distribution. And one of the probably very popular and powerful state-of-the-art methods to do generative modeling is the so-called diffusion models. And this is sort of inspired by non-equilibrium thermodynamics. And there's almost a lot of the sort of the SOTA generative models that you see in practice that are hitting the news, like DALI, stable diffusion, are all powered underneath by this kind of diffusion models. So what is this diffusion model mathematically, or intuitively? I think there's an expert like Holden will be probably talk much more about this. But let me just give you kind of like an intuitive illustration here. So on a high level, what this diffusion model tries to do is, let's say you start with the data distribution you want to sample from, and you have a lot of the data, and you're going to add a little bit of noise at every step along the way, so that at the end of this process, the image essentially look like just pure noise. So example could be, let's say we want to sample from the data distribution of mathematicians. And I would be just adding noise so that at the end of the day, it doesn't look like a mathematician anymore. It just looks like pure noise. And this is usually called sort of the forward process in these diffusion models. But my goal is to actually generate samples that look like the sample from the data distribution, right? So how do I actually sample? And in order to do sample, I need to do this so-called reverse process, which will actually start with something that looks like pure noise. So actually, let's say I start with something look like pure noise. And I will try to kind of revert back. And hopefully at each step, the noise is getting removed a little bit, little by little. And at the end of the day, I'll be able to generate an image that looks like is closely mimicking to the data as if it's generated from the data distribution I want. So at the end of the day, I'm able to generate another mathematician. So the magic here is how do you actually do this, right? So the forward process seems to be incredibly simple, but how do you actually do the reverse process? Or how do you actually ensure that when you're doing this reverse process, at every step, the distribution actually match with the forward process? And this turns out to be a deep question, but was beautifully answered by a lot of the mathematical theory a long time ago. And this is known to be feasible as long as we know the sort of the score functions. And I find this to be remarkable. So how do we actually do this? So let's say if you have the score functions, what are the score functions? The score functions are sort of the marginals of the forward process that is basically the gradient of the log probability at every step of the forward process. Okay, and this is taken gradient with respect to the x, right? And often, in practice, people learn these score functions using some kind of neural network based on training data. And this is something I will not be touching in today's talk. But once you learn the score functions, you can actually use these score functions in every step of the reverse process, and being able to sample from the distribution you like. Okay. So often in the literature, when people try to understand this paradigm, they take a divide and conquer approach where you will be thinking about the first step where you try to learn the score is essentially where you try to learn the data prior. And after you learn the score functions, after you can take them as given and try to do kind of the processing you are interested in, whether this be a sampling problem or this be an inverse problem. So in today's talk, I'll be focusing on just the second step, which is the data generation. I will also not be doing any inverse problems. It's just sort of a sampling problem. Given the score functions, how do you actually sample from the distribution? All right. So one of the type of sampler I will be very interested in today's talk is this so-called deterministic sampler based on probability flow ODE. So in this approach, we are taking a forward process, which is given in the top line of the equation. As you can see, we initialize the forward process as a sample from the data distribution. And at every time, we're adding in a little bit of Gaussian noise. So at the end of this process, it will actually convert very quickly to something that just looks like pure Gaussian noise. And that's my forward process. And what this deterministic sampler tries to do is to define the reverse process in a deterministic manner, where you start with a Gaussian sample. So your YT is drawn from the Gaussian. And every time you're going to go back one step, only using the previous YT. So you get YT minus 1 using only YT by applying some kind of maybe nonlinear function phi t. What is this phi t look like? This is going to actually be using your score function. And as you can see here, the only randomness that is coming into this process is the initial step, where you take the initial YT from the Gaussian. But every step when you go back, we are not actually adding any noise. The reason we are highlighting this is there is a separate type of sampler that's called stochastic samplers that actually add a little bit of noise in every step you are going back. And in the paper, we also look at stochastic samplers, but for today's talk, I'll be just focusing on this kind of deterministic version. And the deterministic version often in practice is observed to be faster in terms of convergence, in terms of sampling, compared with the stochastic sampler. And seems to also has less understanding before our work. So that's why we kind of want to just focus on the deterministic version for today. All right. So what is the underlying intuition behind this formula, or where does all this come from? In the continuous time, and this is how people originally motivated everything, is that if you take the continuous time limit, you can think of the forward process is essentially defining this OU process. Where the marginals is basically the distribution of your XTs. And for every SDE, you can actually reverse this based on classical literature in SDE. So if you reverse this process, this gives you some kind of time reversed SDE. And based on this, you can actually define all the stochastic samplers, which I don't have time to talk about today. And then you can further take the marginals that give you these deterministic samplers based on the so-called probability flow ODEs. So all this are kind of feasible for you to do sampling. And you can think of the sort of the discrete versions I showed in the previous slide is kind of like a discretized version of this continuous time SDE or ODE processes. But the question we want to understand is to actually understand the performance of the discrete time models, and especially how does it converge sort of non-asymptotically? Can we pin down the non-asymptotic convergence rate? And there are a lot of prior approaches for understanding this problem. Holden has done a lot of very nice work along this line. But typically, the way people do this is actually to take somewhat a detour where we'll first look at the continuous time limits by using a lot of tools from the SDE and ODE toolboxes. And then you kind of discretize back by controlling the discretization error. From an analogy point of view, you can think of this as, even though you want to analyze SGD in discrete time, but you actually first go to gradient flow. And after you understand gradient flow, you try to convert back. In reinforcement learning, this is like when you try to do like ODE type analysis for TD learning and then try to then convert back. So this is nice, but it's not as friendly to someone like me who's originally trained in engineering and don't have a lot of knowledge in SDE, ODE. So they seem to be a little bit hard and far-reach. And on the other end, existing analysis based on this kind of approach are also somewhat inadequate when understanding deterministic samplers. So we are actually going to take a different perspective because after all, if you think about the update rule we are using, it's some kind of iterative algorithm, right? So can we actually develop some kind of non-asymptotic framework that try to analyze directly this kind of discrete time processes and can also accommodate all sorts of different samplers. So that's sort of what I'm going to talk about today. And we're also going to make some assumptions, but the set of assumptions we are going to make is kind of minimum. In the sense, we're not going to assume like a lot of smoothness properties, things like that. The only assumption we're making on the data is we want to make sure the data is essentially bounded up to some polynomial factors of t. And you can pick this exponent as large as you want. We also need to choose the learning rate quite carefully in order to carefully control, for example, the initialization error and the discretization errors and so on. So with these choices, we actually have this theorem. And just to begin, the first theorem assumes we have perfect score estimations. If you assume you have perfect score estimations, there are only two types of errors, right? The first one is the initialization error, because in your forward process, at the end of the day, it looks like Gaussian, but it's not really a Gaussian. But when you initialize a reverse process, you initialize using true Gaussian. So there is a little bit of error, but that's not important. That's not very critical, right? And then you have discretization errors. So the main thing we have handled here when we assume perfect score estimation is mainly the discretization error. And we can show that this deterministic sampler essentially converge at this rate if you look at the total variation error. So if you want to get some, say, epsilon accuracy, right, for iteration complexity, then the iteration complexity, roughly speaking, will be dominated by the first term, right? So it will be something like a d squared over epsilon. And if you compare this with previous results for stochastic samplers, focusing, say, on the accuracy levels, this is actually faster because this rate is 1 over t. While in previous works, so the best rate people have achieved for stochastic samplers is only 1 over square root of t. So this kind of somewhat corroborates why sort of ODE type of samplers is observed to be faster. This is not a precise argument because these are just comparing upper bounds. At similar times of our work, there are also a sequence of concurrent works that look at this problem. So one of the paper is by Chen et al., where they also look at the probability flow ODE sampler. So in their paper, they didn't get like a concrete polynomial time dependency. And they also have some exponential dependency in the smoothness parameters. Another paper by Holden, they also look at the convergence of this kind of samplers with some kind of interspersed stochastic correction steps. So in their results, they have better dependency in terms of the dimension of the problem. In contrast, our dependency with the dimension is in some sense much worse because we have d squared. So what about the case when you have Scout function estimation errors, right? So this is one of the important things that sort of bridges with the neural network training part, because the Scout functions are trained by neural networks. There's no way that you can get perfect Scout estimation. So we have two assumptions on the Scout function error. The first one is trying to look at kind of the L2 error, which is basically sort of summing over all the errors, the L2 errors at every step of the Scout function training. The other thing we have is this is sort of a new assumption that we have to develop that actually look at the Jacobian matrices of the Scout functions. And you add up the errors of this Jacobian matrices over the forward process. You get this Jacobian error. And we have the following theorem basically said that this sampler, when you have stochastic, will have Scout estimation errors, will converge at this rate up to some errors of both the Scout function estimation errors and the Jacobian errors. In fact, this assumption of this on the Jacobian errors is not removable. So if you only have the Scout function estimation error alone, and you want to control the total variance error, you will actually not be able to get a proper bound. So this assumption on the Jacobian error is actually inevitable in this setup. You can potentially get rid of this by maybe going to distance measures such as Wetherspoon distances, but that's kind of something to look at in the future. All right, let me see. Yeah, I guess I have a little bit of time just to give one very quick glimpse on the analysis. So this is just our update rule for the problem, where let's say I'm going to call the update formula for the reverse process as something like a phi t. And the goal is to show essentially that this probability distribution somewhat match at every step of your process, right? And let's say in order to show this, what I want to show is what I need is to just ensure this probability ratio is close to 1 on some kind of typical set of the distribution. And if you, let's say you're at time t and you want to go back one step to t minus 1, you can rewrite kind of the progression of this probability ratio as a multiplication of 3 things. Not sure if you guys can see the details of this, but kind of the right things were kind of the recursions, right? The thing you are tracking. So if you already have a good matching at time t, you kind of can not worry about like the last term here. And there are only 2 terms you need to care about. So the first term is a ratio that tells you the relation between yt and yt minus 1. And the second term is a ratio that tells you the relation between xt and xt minus 1. And for the first term, so let me, there's a delay. So let me plug in the expression for yt minus 1, which is using this phi t's, right? So you get this formula. So it boils down to just to control these two things. To control the first thing, you can do some kind of change of measure. And at the end of the day, you are going to basically control the determinant of this nonlinear operator phi t. On the other end, for the second term, that depends on sort of the forward process. Because the forward process is adding a lot of the Gaussian, so this is actually not so hard to control by using some kind of concentration bounds. So with this kind of elementary toolkits that we developed, you actually do not need to have advanced knowledge in the literature of SDE or ODE in order to understand sort of the non-asymptotic convergence of this kind of diffusion processes. So with all that being said, let me try to quickly sum up the second part of the talk. So we have focused on developing kind of non-asymptotic convergence rate for sampling from deterministic samplers in today's talk. In the paper, we also have results for the stochastic case. But again, the rate we have is not optimal in the dependency with the dimension of the problem. But one thing we are trying to highlight here is we find this framework to be somewhat elementary, that you probably, if you, a lot of people, at least when I first started working on this problem, I'm kind of intimidated by the two boxes in SDE, ODE. But hopefully, our paper can sort of inspire more people to work on this type of problem, that you can actually look at this very interesting problem without really having a lot of like initial knowledge, at least, to start the journey. There are a lot of interesting future directions. One thing is, can we actually accelerate the sampling processes? Can you design accelerated samplers that converge faster? One of the things that I'm very interested in is also inverse problems. When you try to leverage these score functions, these score-based generative models to solve inverse problems, like in the first part of the talk, what kind of convergence guarantees we can say? How can we design efficient algorithms that leverage these generative models in a proper manner? There's also an important question to develop end-to-end theory for these problems. So in this talk, we assume that we have perfect or near perfect score estimations. While in reality, this score function will be trained by neural networks. So it will be very interesting to actually analyze like a full pipeline that actually covers both steps of the procedure, that accounts for both the optimization aspect of score functions and also the sampling aspects. So with that, I think I can conclude. If you are interested in this work, there's some relevant papers. You can find these papers on my homepage. I'll be happy to take any questions you have. And thank you so much for your time and attention.
Do we have any questions? Oh. All right, start in the front here.
Hi, thank you for the nice talk, Wedgie. I have a question for the first part on acceleration in the overparameterized regime for low-rank matrix completion. Matrix recovery. So can you comment on the added computational cost of computing the inverses at every step? And like, you know, if I were to measure this with clock wall time, say, would you see the same sort of benefit?
Yeah, that's a very good question. So in the exact parameterization case, the added cost is minimal. Usually you can couple the computation of the inverse with a gradient. So in the paper, we have some runtime plots. The one I showed in the slides is iteration. So that's fine. But when you do over-parameterized settings, it becomes a little bit more expensive and trickier, right? Because that matrix becomes larger. So in principle, the theory applies even you do full over-parameterization. So you over-parameterize up to the dimension of the matrix. But then to compute the inversion of an n by n matrix is not realistic, right? So generally, we think of the problem that we are dealing with is more about handling model misspecification. So typically, the over-parameter rank maybe is a constant factor of the true rank, or maybe up to some log factors in terms of computation, right? You don't really want to over-parameterize that much.
That's right. That's right. And I was thinking whether with that you could understand, given that you need to invert a big matrix in the over-parameterized case, whether you could understand beyond what condition number it is worthwhile actually to accept precondition or not, right?
Yeah, exactly. I think one of the important problems is to do actually adaptive or automatic rank selection for these problems. Especially for this problem, if you care about application, you don't really want over-parameterize, but rather maybe you use over-parameterization initially as a way to do model selection. And then once you kind of figure out what is the right rank to use, you just stay with that rank. Yeah.
Hi, thank you for your insightful talk. I really like the idea of scale GD. Can you comment on the empirical and theoretical relationship between natural gradient descent and the scale GD?
Oh, okay. Yeah, that's a very good question. So this is not doing, I don't think it's doing really natural gradient descent, but both of these are kind of different variants of like a preconditioned or quasi-Newton type of method. So one of the intuition for scale GD is if you take the population version, which is matrix factorization without the sensing operators, so you just do m minus x1 transpose and then Frobenius norm squared. And if you write down the, say, the Hessian at every iteration, so you get something like a big matrix, right? And if you look at the block diagonal components, you get, that's essentially what we are using. And so basically what we're doing is we get rid of the off block component, and then we keep the block diagonal component, which look like something like, say, X transpose X, Kronecker, some identity matrix of size n. And that is why we can just use a small matrix to say computation. And then the sensing problems become kind of approximative versions of this. So it's kind of like a quasi-Newton type of method.
Cool, thank you.
Thank you.
All right, two more.
Hi, Professor, great talk. I was wondering for the low-rank matrix recovery under noise, can you comment about the early stopping time with the pre-scaled gradient descent? I did not get from the bound how it changes the early stopping time for recovery.
Yeah, that's something I didn't mention. You do need to do early stopping. I don't remember the exact formula, but it's very similar to like a lot of the previous works. When you do, it will be kind of depending on also the initialization scale. So yeah, so all those need to be done.
I see, and also the bound depends on the initialization scale of the matrices. But
Yeah.
in that bound that I saw for, I didn't see like an initialization scale.
Yeah, so it's all hidden because if I write everything, that will be like a very dense page. But it will be something that will also factor into the final error. So that will be depending on the final error that you will be choosing that.
Thank you.
Really nice talk. I also have a question for the first part of the talk. So in the end, you showed a three-phase. You shared intuition on the three-phase. So I was wondering why in the third phase the green curve goes up.
Oh yeah, that's an interesting question. So we didn't actually track much of that alignment. So this is looking at the angle. Let's see. Yeah, one of the things is you kind of start also to pick a little bit of like because you over-parameterize, that's sort of, I think it's contributed by the over-parameterization error. So that has some kind of growth, but it's kind of bounded growth. At the end of the day, it doesn't really hurt your convergence. Yes, there may be some kind of, I think yeah, we observe in practice as in the simulation as well. So it's because the main thing you are checking is a reconstruction error, and you're going to do some kind of early stopping as well. Yeah, there's more details in the paper that I don't remember all the details of. Yeah.
All right, let's thank Eugene one more time.
Yeah, thank you.
You
Sure, thank you.
Hold on to it. Oh, it's okay. We'll just. Would you like the clicker? Do you just plan to use the podium mic? We good to share? All right, for our first contributor talk this morning, we have Xixiao Wei from UCSD, who will be discussing quadratic approximations of random interproduct kernel matrices.
Okay, thanks for the introduction. So I'm Zhichao Wang from UC San Diego. This is joint work with Partipandi and Yizhe Zhu. Yizhe is also here, so feel free to ask questions. So I'm talking about the quadratic approximation for the nonlinear random kernel matrix. It's a random matrix result, but there would be some application in the kernel ridge regression models. So unfortunately, I'm not talking about the deep learning. I'm moving back to the more classical machine learning, which is the kernel ridge regression. So suppose we have some kernel function, this little k, on some data distribution, and we have n data set, xi's, and yi are the training labels. We want to consider this kernel ridge regression model for this nonlinear kernels. For this kernel ridge regression, the advantage is that you have some closed form for this kernel ridge regression. The estimator for this kernel ridge regression can be written in this way, where this k little x capital X is a row vector, which is defined by this kernel function. So here this x1 to xn, here it should be xn. So these are the n training samples, and little x is the test point you are applying to this estimator. The main part is this resolvent part, this inverse of this k plus lambda identity. For this part, this k capital X, this is a kernel random matrix. Entry-wisely, it is defined as this k, little k, xi, xj. So this is the main target we want to analyze, since once you understand the eigenvalues and the eigenvalue distribution for this matrix K, you can understand what's the predictions for this kernel ridge regression. So that's the setting we're considering here. So the motivation is still coming from the deep learning, so the neural tangent kernel. So there are two kinds of kernel. I think yesterday we talked about this in several talks. So like if you consider one layer neural network at initialization, when the width goes to infinity, then the output of this neural network, this graph matrix, will converge to some kernel, which is called the neural network Gaussian process, or the conjugate kernel. So here the sigma is activation function, some nonlinear activation function, and W as some random Gaussian or random weight matrix. So essentially, it can be defined as the expectation of this sigma W transpose X times W transpose Z. So this is one kind of kernel function in this initial random neural networks. Another one is related to the NTK. So at the initialization, if you consider infinite weight neural network, then this neural network will be governed by the the neural tangent kernel at initialization, which is defined as the graph matrix of the Jacobian of the output of this neural network. So here so it's a very rough concept here. We just take the limit for the weights of each layer. So specifically, if you consider like a 2-layer neural network, then the neural tangent kernel has a very explicit formula, which the first part is just this conjugate kernel part, and second part is related to the derivative of this activation function. So these are two kernel method, which is hidden in the initial random neural networks. The motivation is that kernel ridge regression is a benchmark for the deep learning. So if you want to say neural network has some advantage, you want to compare it with the kernel ridge regression and say that, so suppose you want to learn some target function, then kernel ridge regression, you have the benchmark, you know how many sample size, training sample size you need to learn this kind of target function. And then your network would be save some training sample size or less training sample size to learn the same target function. So to understand the neural network, we need to first understand the kernel ridge regression, or the kernels here for this NGP and this NTK ridge regression. I hope this makes sense for you. So one specific kernel we want to consider is this inner product kernel. So we define some nonlinear function, R2R nonlinear function G, and we define this G applying to this inner product of this Xi, Xj, which define this kernel function. And we define this capital K is this kernel random matrix with n data points. And Xi's are sampled from some data distribution independently, identically. We want to analyze this kernel matrix. This inner product kernel random matrix appears in many classical kernels, like the polynomial kernels. So you have this 1 plus Xi transpose Xj with some higher power. Also, if you compute certain conjugate kernel, so the 1-layer neural network case. So in this case, if you consider a specific activation function like the ReLU, then under the certain condition for these data points, this kernel is also an inner product kernel. So that's why we can consider this inner product kernel in this case. So our goal is try to analyze the spectrum of this K, this kernel random matrix, in the high dimension setting, where the sample size and the feature dimension, so the dimension for this data point Xi, are all going to infinity at certain rate. Okay, since this is a high dimension setting for the data set. There are several rates we can consider for the N and D. The first step is considering N is proportional D. So this is a classical high dimension statistics setting. In this setting, the first step, the first result is proved by Yarkaruli at 2010. So for this one, it shows that this kernel model is actually equivalent to a linear model. So if you consider sigma is the population covariance for this matrix, and for the data set, you have like 4 plus beta finite moments, and this population covariance is bounded. In this case, this random matrix, this kernel random nonlinear random matrix, is equivalent to this X transpose, this linear random matrix plus some spike and some identity. This approximation is true in operator norm sense, which means all the eigenvalues are close to each other for this capital K and this linear random matrix. Here, these coefficients are some deterministic stuff, which is just determined by the this nonlinear function, this G, which we defined before for this kernel matrix at 0 and at the trace of the sigma. And using this approximation, we can analyze the precise asymptotic performance for the kernel ridge regression, since in this case, it's just equivalent to a linear ridge regression. One thing I want to remark is that the ridge parameter is changed. It's not just the ridge parameter for the linear regression, since here in the approximation, you have an actual identity term. So the ridge parameter is related to the C2. So this is something related to the implicit ridge regression. Okay. The one question we want to consider is that, can we consider beyond the proportional limit, not this n is proportional to d? So this is just one ideal case. In fact, so I want to talk a little bit for this proof and then say something for the difficult part to extend this proof for the more general case. So if you consider this entry-wisely consider this kernel model, then off-diagonal xi, xj, since these are independent, so this one concentrates around 0 well. So if you just consider a Taylor expansion for this nonlinear function at 0, then you can have this approximation. And for this leading term, that is just related to this xi transpose xj term, so which is related to the linear part for this approximation. And we can control this higher order term, since this one concentrates well entry-wisely. For the diagonal term, xi transpose xi is not concentrated around 0, but concentrated around this trace sigma over d. And then we can also approximate this one by the just first order Taylor expansion. And combining these off-diagonal and diagonal together, then we can have this approximation for this kernel model by this linear model. So here the approximation is just using the Taylor expansion at 0 and at the trace of sigma over d. So as I mentioned, once we understand the spectral for this kernel model, then we can analyze the performance for the kernel ridge regression. So here are some pictures and simulations from Kanata et al. At 2021. So in this one, we can see the double descent curve for the generalization arrow and also the training arrow. So here, these are chosen for different ridge parameters and different noise parameters. So essentially, these curves are governed by the spectral of this kernel matrix. So here, this alpha is the abstract ratio for n over d. So you change this abstract ratio here. So our goal is to consider the case beyond the proportional regime and consider like n is proportional to the d square, what happens for this kernel model. In fact, there are several works where consider this polynomial regime for the case that n is proportional to the e to the l, and l is some integer. So here are some cartoons to explain, in this case, in this polynomial regime, what we expect to obtain from this kernel ridge regression. This is a cartoon from Hu and Lu, where you can consider this is the generalization arrow, and the x-axis is abstract ratio for the sample size over the feature dimension. And you can see that when this sample size is growing, so if you have more data, of course, your generalization arrow will decay. So when n is proportional d, we'll have this decay. And when n is proportional to d squared, then the generalization arrow is smaller than the first phase. And then you may have another double descent for the second phase for n is proportional to d squared. And then when sample size is growing to n proportional to the d cubed, then you have another double descent curve. But of course, in this case, the generalization arrow should be smaller than the second phase for the quadratic phase. So this is for the case that the n is proportional to some d to the l. When the case that n is much larger than d to the l, but much smaller than d to the l plus 1, then it will fully learn the target function with up to L degree, but they cannot learn anything for the higher degree functions. So this is an intuition for this kernel regression. However, this analysis can be done for a certain data distribution. In this paper, they only consider like the uniform unisphere distribution for the data set. So here are some other results. For certain distribution, like the hypercube or the uniform unisphere distribution, the precise asymptotic for this kernel ridge regression with this polynomial regime can be analyzed. And for general data sets, we only have some generalization error bound for this kernel ridge regression, especially for the paper EJ and I. We analyze like more general deterministic data with nearly orthogonal properties. In this case, we can have some bound for the generalization error, but we don't have a very sharp approximation for the kernel. So the main question we want to consider is the precise asymptotic for this kernel regression for general data distribution with these polynomial regimes. The first step we can consider in this talk is consider the quadratic regime, where n is just proportional to the d squared with general data distribution and general covariance matrix. The main result can be summarized here. We consider the data distribution has some population covariance sigma, and for the yi, we have this Gaussian moment matching assumption where the first eighth moment is matched with the standard Gaussian distribution and finite moments for the yi. And sigma is some population covariance is bounded by some constant. Then in this case, this kernel random matrix can be approximated by this K2, where K2 has 4 terms. The first one is some spike term. Second one is this XX transpose. The main term is this XX transpose Hadamard twice. So it's just entry-wise Hadamard, entry-wise product twice the XI transpose. And then it's the identity terms. This is true holds for improbability. Explicitly, this K2 has this low rank plus bulk plus regularized terms. So the first 2 terms are actually just related to spikes, related to the D+1 spikes. And this third term is the bulk spectral part, which relates to the bulk of this eigenvalue distribution. And the last term is identity term. And all these coefficients are related to this nonlinear activation function. The main idea for this polynomial, this approximation is that we cannot directly use the Taylor expansion. We have some correction term for this Taylor expansion. Like for the third order approximation, we need to have another correction term to reduce the variance of this correction term. And for the fourth order approximation, we need to have 2 correction term to reduce the variance for this approximation. And interestingly, these 2 correction terms are just related to the Hermite polynomial of third and fourth order. And that is the optimal way we can crack the approximation and to get the sharp approximation for inoperative norm. And I don't have enough time, but we have more results for the limiting eigenvalue distribution once we have this approximation. And it's just governed by some deformed Marchand-Pass law for this kernel random matrix. And for the isotropic case, we have more explicit formula. So here are some simulations for this kernel random matrix. You can see here, there are first D+1 spike. Since D is much smaller than N in this case, these spikes will not affect the global law or the bulk distribution for this kernel spectrum. And if we zoom out this kernel spectrum, then you will have this deformed Marchand-Pass law. Here, this red line is our simulation from our theory. And this blue one is the histogram of this eigenvalue distribution. And these are some more simulations for different nonlinear kernels for cosine and this x squared plus x. And for the alpha, this abstract ratio smaller than 1, you have some 0 eigenvalues at 0. Okay, Once we have this kernel spectrum, then we can have some asymptotic result for the training error and generalization error for the kernel ridge regression. Since I don't have enough time, so I will just skip this part. So we can have some asymptotic result like the training error as d squared and n proportionally go to infinity. Then the limiting training error can be computed by the limiting spectrum of this kernel random matrix. The same thing for the generalizing error. In conclusion, we analyze this inner product random matrix in this quadratic regime. N is proportional to d squared. For general data distribution and the population covariance matrix, we obtain some marginal path law for this kernel random matrix. And using this, we can analyze the asymptotic performance for the kernel ridge regression. Yeah, thanks for listening.
Thank you. We have time for one quick question.
I guess all these results are for the case where the width of the layers you are basically constructing your kernels from scales much faster than the number of samples and everything else. So it's the limit.
Right, that's right.
And is this analysis also doable in the case where it's scaling together with those, but not so faster, like standard over parameterized regime?
Yeah, that's a good point. Right now we don't have this result, but you're right. If you consider like the width is proportional to the sample size, but all proportional to like d to the L's power, then it will have some similar performance for this random feature models. Does this make sense? So yeah. So I expect this will be also analyzed in this case.
So you expect as soon as you have overparameterization, like n is just polylog slower than number of neurons, everything becomes the same.
So the width and the sample size are all go to infinity faster than the feature dimension. In this case, you should be converged to some polynomial kernels. Yeah. Okay. Yeah, thanks for the question.
All right. So thank you. We have a short break now, so we'll reconvene here at 10:50. So grab some coffee, grab some water, and thank you again to the speakers for the first part of this morning. Can we turn this on for a second? All right, everyone, we're going to start in just a minute, so if you want to grab seats and be comfortable. So you're at National Center for AI?
Yeah, in Chile.
Chile?
Yeah.
Excellent, okay. Oh, okay, so you really flew. All right, if you'd like to sit down, we're going to start the second half of the morning session. We're excited to have all the way from Chile in the National Institute from AI, Nicholas Alvarado, who will be talking to us about curvature and dimension trade-offs. So, thank you.
Okay. Thank you for the invitation. My name is Nicolas Alvarado. This is a joint work with my thesis advisor, Hans Lowell, and Professor Mircea Petrache. We all work in the National Center for AI in Chile, and we also are members of the Universidad Católica de Chile. So, this work is called curvature dimension trade-off for generalization in hyperbolic space. And first, this one, yeah. First, let's talk about a bit of Euclidean neural networks. They are classical neural networks, and we have some current challenges. These challenges are related to the high complexity of the data and the high computational cost. So here enters the hyperbolic geometry. Why? Because we can reduce the high dimensional data into a lower dimensional data, embedding in hyperbolic spaces. Let's talk about a bit of hyperbolic spaces. What is the hyperbolic geometry? In this figure, we have zero curvature, and in this zero curvature, we have Euclidean geometry, like the classical geometry. And the figure here, this draw, is an example of the negative curvature. Here we have a hyperbolic space, and you have to think that this is like a potato chips, or like a Pringle. So in this geometry, the geodesics are defined by straight lines, okay? And these generally are like this form, okay? So this has a natural structure to do hierarchical data sets. And you have to think, here we have 5 isometric models. The first and the most studied, I think, is the Poincaré model. So this is like the unit disk. And near the boundary, you have to think they are approaching to infinity. So this is why in this example, the hierarchical tree has many branches on the boundary of the disk, okay? So the other 5 isometric models, are the Hopper plane, and the other famous are the Lorentz model. The Lorentz model is like a cup. So this defines another kind of geodesics too. So the learning model is this set of functions, and is composed by Lipschitz function, okay? So we are working here, and we want to bound the Rademacher complexity of this set of functions, okay? So we have some definitions. We are going to talk about epsilon cover. It's like you have a collection of points of metric space, and you can define it by the distance of every point to this point, and you have a radius of epsilon, okay? And another important definition is the covering number of a metric space. The covering number is the infimum number of the epsilon covers, okay? So, classical generalization bounds, you have like this one, okay? This is a bound for the generalization error and is related to also the Rademacher complexity. From this point, we can bound the Rademacher complexity of the set of functions that we mentioned before via the Dudley entropy integral. This is the Dudley entropy integral. And to get this bound, you have to take a covering number, right? Define this space of functions in the ball, hyperbolic ball of radius r. And you have to use, if I remember well, the Massard lemma, okay, to get the bound, right? Now, our main result is this one. So you have a ball of radius r, hyperbolic ball, and you have the model space M kappa d. In this case, the model space is a hyperbolic one, so we have to think that the curvature is negative. And you have this comparison. So the covering number is related to this quantity, and we have here the trade-off between the curvature and the dimension of the space. Okay, so it's easy to know that kappa and d have interchangeable roles, and you can play with the dimension, get a lower dimension and get a lower kappa here, and you have still the same quantity. So to prove this theorem, you have to bound. You have to get an upper bound and a lower bound. And for the lower bound, this classical formula of the volume of the of a hyperbolic ball of radius r is this here. Also, you can compare the volume of a large ball and the volume of a small ball, okay? And using the definition of a hyperbolic scene, we can get, after some algebraic sets, computations, this quantity, okay? So if we take a curve of Z by balls of a radius epsilon, and this curve has cardinality n, we can bound here and we get the lower bound, okay? For the upper bound, we can take a Pagan number. Pagan number means that we have a collection of disjoint balls of radius epsilon. So we have the maximum number of this, and we can get the upper bound, okay? Now, some straight corollaries we have under the same hypothesis of the previous theorem, that the logarithm of the covering number is also this quantity, okay? And we can assume that if m is this number, the logarithm of the covering number, we have this relation between the curvature, the dimension of the space, and the Rademacher complexity, okay? So this is a deregulation between the trade-off, and we can explicitly find a bound for a generalization in this kind of spaces. Another corollary is this. This basically says that the number of samples n is sufficient and is this quantity of here, the maximum of this number and this number, okay? Okay, so this is an explicit theoretical work, and current work is we are working in empirical methods to prove these bounds. So we have a bit of numerical analysis behind it, and we want to get a real number for study the bounds for the Rademacher complexity in this kind of spaces. Also, we are considering implication for more general Gromov hyperbolic geometries, including a metric tree. And for the conclusions, we prove packed learning bounds for arbitrary learning models in hyperbolic and negative Fourier space. Also, we showed that the curvature has a interchangeable role with the dimension, okay? And we have different effects in increasing dimension at fixed kappa and decreasing kappa while fixed d. And we have a rigorous statement for hyperbolic spaces that we can use to hyperbolic neural networks. So that's all. Here we have a little reference if you want to read something, and thank you for the attention.
Questions while we get set up? Anyone?
Yeah, thank you. I think it's a very good talk. So I have this question. I think in one slide you said the function is bounded, right? From net M to M. Can you show that slide?
Sorry, what number of slide?
The first couple slide. One of the first.
First of couple of slides.
Yeah.
Maybe.
Somewhere.
Yeah.
If
you tell me. This one?
No, more. You have a boundedness, like from net M to M, remember?
Okay. You are talking maybe this one?
No, the capital M. Sorry, some condition.
Yes.
Can you go further?
Further?
Yeah.
There's no equation further. So.
Oh, I remember. Okay. So in the first one of the first several slide. Oh.
Okay.
Oh, okay. You press A.
This one?
No, the.
Sorry. This is the first one.
This first one. Okay. Anyway, so I remember you assume the boundedness for the function. So can you remove that condition?
Yeah. Yes.
Yeah, here, yes.
Sorry.
Yeah. Thank you.
Yeah. Yeah. Yes, in the in this setting, to get this bound, you define f as the same space, but you have take m equal to 1, and it works. I don't know, but I think you can move. But it's important to have Lipschitz functions on. The m constant is the m constant of Lipschitz functions actually. So maybe you're right. You can move the bounds. Yeah, I think so.
Any other questions? All right. Well, thank you again.
Thank you.
Kind of understood that.
Thank you. All right, so for our last talk before lunch, we are excited to have Vidya Muthukumar from Georgia Tech. She's part of the ECE and ISYE departments and has been doing amazing work in online learning and statistical learning. We're very excited to have you here, so thank you for coming.
Okay, thanks to the organizers for organizing this amazing conference, and thanks for the very kind invitation. So my name is Vidya Muthukumar, and I'll be telling you a little bit about the so-called over-parameterized regime for machine learning. Maybe people have heard this word before. I'm going to try and demystify things a little bit today. And the major technical focus of my talk will be to directly compare classification and regression tasks in this over-parameterized regime. So I want to start by giving a shout out to my wonderful collaborators. So a lot of the ideas here originated from 2021, so about a couple of years ago, and were the product of a lot of very fruitful conversations with various people. And more recently, I'd also like to give a shout out to my students. So I've built up a really nice research group over the last 4 years, and Guangui and Kuowei are actually here at the conference as well and presented posters yesterday. So the very high level motivation for what I will be talking about today is this probably by now well-known empirical phenomenon that some of you have come across, which is this idea that state-of-the-art neural networks have this remarkable tendency to perfectly fit their training data. In fact, they're even capable of fitting completely random labels. So they achieve zero training error. Traditionally, in machine learning and statistics, we associate this with overfitting. However, that is not what happens in practice, at least for classification tasks. So I would say that we still do not have a full mathematical explanation for why this behavior is being observed. We have some partial answers, which I will start to unpack in the talk today. But more generally, when we think about deep learning theory and trying to understand these types of phenomena, we can organize theory along roughly 3 categories. First off, on the optimization side, we might want to understand, well, is it even possible to get zero training error? This is a non-convex optimization problem after all. Secondly, we might want to understand like what types of solutions we are converging to in the first place, as these are also typically underdetermined optimization problems. And thirdly, well, do these solutions actually generalize well, and what types of low dimensional structure are hidden and facilitating this? So, okay, there's a bit of a lag. So kind of starting with the first question, which is not one I'm going to be engaging with in this talk, we do know by this point that certain types of overparameterization, most notably in the width of a neural network, does enable this type of faster convergence and being able to achieve this perfect training accuracy regardless of the types of labels. And coming to the second question, which I'll touch upon a few times through this talk, we can ask what types of solutions are being found, say if we used gradient descent to train these neural networks. Again, under some simplifying assumptions, if we look at linear models or the last layer of a neural network or the neural tangent kernel regime, we also by now have a good understanding of the solutions we get from gradient descent, and we know that it converges to solutions with this type of minimum 2-norm bias, which again I'll define formally in just a little bit. The bulk of my talk today will be focused on the third piece of this puzzle, which is whether solutions with this type of inductive bias in fact do generalize well and under what types of conditions this happens. So this brings me to the more low-level motivation I want to say for what I will discuss today, which is the replication of this phenomenon, that is the success of models achieving perfect training accuracy, and in very high dimensional regimes, not only in the case of neural networks, but also in the much, much simpler case of linear models. And again, maybe many of you have seen this curve by this point, the double descent curve. And all this is really saying is that the main surprise in this curve really comes to the right side of the threshold where we start perfectly fitting training data, and the dimension of the model is much greater than the number of examples. And in this regime, if we choose solutions with this particular inductive bias of a minimum L2 norm, it has been observed across many different linear model families that the test error actually decays as we overparameterize more and more. And moreover, all of this is happening as we perfectly fit the training data, including noise in the training data. So by now we also have, I would say, a pretty mature understanding of under what conditions we can see this type of behavior for the case of regression tasks. And when we move to classification, which underlies pretty much all of modern machine learning, the picture actually becomes a lot less clear. So in today's talk, I will address this more complex case of classification. And I'll do this through the lens of a direct comparison between classification and regression tasks, keeping the model family fixed in both cases. So when we do a comparison between these two tasks in this style, what things really boil down to is a comparison between the loss functions that are used for the two tasks, both at test time and at training time. So starting with the case of regression, the picture is conceptually very simple. We evaluate at test time with the squared loss or the mean squared error. This is very classical. And this is a very well-behaved, nice convex loss function for linear model families. So we might as well also train using the same loss function, which is the squared loss. Now coming to the case of classification, things are a bit more subtle because at test time, we use this very discontinuous, not very well-behaved 0-1 loss function. And therefore, when we want to train, the traditional practice is to use continuous convex optimization surrogates to this loss function. And motivated by classical statistical wisdom, the most popular such convex surrogate tends to be the logistic loss for binary labels. And this is more commonly called the cross-entropy loss when you move to multi-class labels. However, it is worth noting that, well, this is not the only surrogate loss you could have chosen. You could have chosen the squared loss or many other different types of loss functions at training time. So what we're going to see through this talk is a direct comparison between all of these types of loss functions. And as we will see through the talk, the picture is very different in terms of this comparison at test time and at training time. So I'll start with just a formal description of the setup I'm going to use to describe our results. And then the talk will be in two parts. I'll start by describing the role of the loss function at training time and then move on to the role of the loss function at test time. And as you'll see that the implications of loss function at these two phases turns out to be very, very different. I will also try to emphasize a few connections to harmless interpolation of kind of noise, the phenomena I talked about at the beginning, but this is not going to be a major focus of the talk. So without further ado, let me move on to describing the basic setup that I'll use for this setting. So starting with linear regression, I'll assume that my labels are actually generated by a linear model. So here phi of x denotes the features and beta star denotes the true parameter or the signal. And this is of course unknown. And we have some additive noise of variance sigma squared, and I'll make some mild assumptions on the distribution of the noise. So the features are going to be centered, mean 0, and I denote by sigma the covariance matrix of the features, and this is a quantity that will pop up a few times through this talk. So for a lot of the theoretical results that I will describe, I will also assume that these features are either Gaussian or sub-Gaussian with independent components across them, and this is just really to facilitate a lot of the random matrix theory in the analysis to work. However, a lot of the same phenomena can also be shown for more general cases where the feature maps are structured and high-dimensional lifting of a low-dimensional data, and this is typically what you would see if you were to go to a kernel method instead of a linear model. And I also like this case of structured feature maps because this is a case where you can actually visualize a lot of these phenomena even on one-dimensional data. For example, if you were to choose a polynomial basis or the Fourier features as a basis. So as we go through the talk, a lot of the theoretical results will make assumption 1, but I will also illustrate the same results using model 2 so that you can actually visualize what the functions look like in function space. So this talk will operate predominantly in the overparameterized regime in which the number of parameters or the number of features D greatly exceeds the number of samples. So as we know in this setting, as long as our training data matrix is full rank, which is a very mild assumption for these purposes, we can perfectly fit our training data, that is get A beta hat equals Y. And this is an underdetermined setting for D greater than N, meaning that there are infinitely many such solutions. So motivated by the fact that we are looking at solutions induced by gradient descent, the solution that I will focus on today is the solutions with a minimum 2-norm bias, and in the case of regression, this will be the minimum 2-norm interpolator. That is a solution that minimizes the L2 norm subject to this constraint of perfectly fitting training data. So in this setting, remember that we are fitting signal and noise, and this is really the only place in the talk where I'm going to really bring up harmless interpolation of noise. And that's just to mention this really nice property of these types of solutions, specifically with a minimum 2-norm bias, which is that if we were only fitting noise in the data, we can actually show under pretty mild assumptions that the test error would become smaller and smaller as we over-parameterize more and more. And the plot here simply shows the result of the test mean squared error if you were to kind of get this minimum 2-norm fit of just pure noise. So there's no signal in the problem in this particular plot. And in particular, what you can show here is that you can actually show this very precise scaling on the order of the noise variance, which is sigma squared, multiplied by the number of training examples divided by the number of features D. And this is all for the case of a regression task. And once you start adding in signal, actually the picture becomes a lot more subtle. And this is actually something I'll return to later on in the talk. But from the point of view of the residual effect of overfitting of noise, what this result shows is that overfitting effect is very, very benign. And this is the origination of this term, the benign overfitting, that some of you might have also heard. So at this point, these results were derived in a bunch of concurrent works in 2019 for the case of regression. And what we will address today is, well, what happens for classification, test error. So what happens if you evaluate all of this with the 0-1 loss and you add back in signal? And also what happens if instead of looking at this type of solution, what if you trained using classification-oriented losses, such as the cross-entropy loss? So with that motivation in mind, I'll next describe our setup for linear classification. And as you can see, a lot of the framework kind of carries over. The only real difference is that my labels are going to be binary valued, that is plus or minus 1. And I'm using this kind of random label noise model. So I still have a linear model parameter, and mu is my label noise probability. I'll also note that we don't strictly need to assume this model. We can have much more flexible models for the label noise, including logistic models and other link functions. But this is one of the simpler cases to describe. So unlike in the case of a regression task, the solution that one tends to look at, motivated again by what you would get from gradient descent, is not actually a solution that interpolates the training data. It is instead a solution that we can think of as the minimum two-norm separator of the training data, and that's just what I've described here as the hard margin SVM. So this is a solution that also has this objective function of minimizing the L2 norm of the weights in the model. But the key difference is that this is no longer interpolating training data, it is merely separating the training data. So this is quite different, as it turns out, from the interpolation, and there are many, many special examples you can construct where the solutions will in fact look quite different. And most importantly, analysis for the MNI, if you look at any of the aforementioned regression analyses, the very, very first step is to get a closed form expression of the solution, which would essentially not be the case over here. So now that we have an idea of the setup, and also I would add that I'm happy to take questions about the setup at this point if anything was not clear. So please don't hesitate to stop me at any point, just raise your hand. But I'm going to assume that the setup is clear to people if I don't get any questions at this point. So with that basic description of the setup, I'm going to move on to talk about our first set of results, which examines the role of the loss function at training time. So before I really get into our results in the over-parameterized regime, I'd like to start with a quick contextualization of how people have both traditionally thought about loss functions and also a little bit more recently. So as I mentioned, the kind of traditional perspective on loss functions was to construct these continuous convex surrogates to the 0-1 loss in the case of classification. And actually, if you really look into this literature on convex surrogate losses, a lot of the results there actually imply an approximate equivalence between these different types of loss functions. So in other words, the way this kind of works at a high level is that you can relate the test evaluation according to different loss functions within constant factors to each other. And because in the traditional under-parameterized regime, we can typically relate training error and test error in a very direct way, this automatically implies that, well, any of these training loss functions, as long as it is convex and a good surrogate to the 0-1 loss, will give us the same type of result. And all of this very classical theory really implies on this, really relies on this tight connection between the training error and the test error. And as we're seeing in high dimensions, none of this is true. I mean, we get a training error of 0, very unclear what that implies for test error, and it really depends on the type of solution. So there's kind of this classical theory that's very nice, but essentially only works in very low dimensional regimes. So moving to the more high dimensional setting, the impact of a loss function really needs to be considered in conjunction with the optimization method that is used. And in this talk, we're focusing on the case of gradient descent and linear models. So for this case, we by now have a pretty mature characterization of what the impact of loss function together with gradient descent will look like in the case of linear models. So with the squared loss, well, there's a very folklore result, goes back 30 to 40 years. For cross entropy losses, we can actually show this link to the SVM. And there's even characterizations for the Genzel loss. But at a high level, what turns out to still be kind of tricky and unresolved from this theory is that all of these characterizations turn out to be connected implicitly to solutions of convex programs. And well, except in the case of the squared loss, where it turns out to be interpolation, none of these convex programs have a closed form solution, not in Genzel. So this characterization is really nice. We can compute it, we can evaluate it, but usually it is pretty difficult to get any analytical traction into these implicit bias characterizations in the worst case. And that's kind of, this is going to be a jumping point for what I'm going to talk about in a bit. And I also do want to call out a kind of complementary perspective to a lot of what I'll discuss today, which is these end-to-end error analyses that you can do when the dimension is greater than the number of training examples, so D is greater than N, but D is actually proportional to N, and you kind of grow D and N together to infinity. And these are these so-called proportional asymptotics. I think there have been a few talks at the conference that kind of operate in this regime. And these take a somewhat different perspective because you can actually precisely evaluate the error directly arising from various loss functions. But we will operate in a somewhat different regime where the dimension is much greater than the number of training examples, and we'll generally want to get non-asymptotic characterizations. But I'm happy to talk more offline about comparisons between these two paradigms, especially if you haven't seen both of them before. So now let's kind of get into this question of the role of training loss functions in a bit more detail, starting with the case of binary labels. So I mentioned a bunch of implicit bias results on the previous slide. I'm now going to unpack them in a bit more detail. So starting with the case of logistic loss, which is the first natural starting point to ask this question. Note that the logistic loss is in fact the cross-entropy loss, just specialized to binary labels. We have this nice set of results from Saudi et al. And G and Telgarthi from about 5 years ago that shows that gradient descent done in the logistic loss converges to precisely this SVM formulation. On the other hand, if we go to the squared loss, there's actually a much simpler linear algebraic argument that can be shown to show that gradient descent would now converge to this type of interpolation, where note here that the interpolation is on binary labels. So I'm using the fact that labels are plus or minus 1 valued. So we can look at these side by side and note that there are actually a lot of differences in the characterization over here, at least in a worst case sense. So starting with the logistic loss, as we noted, this is in general not going to have a closed form expression, unlike the MNI. And also the justification for logistic loss is really linked traditionally to maximum likelihood estimation under logistic noise. So that's kind of where I think this is a big reason why people like to use this loss and have persisted with using this loss. And also on a more technical side, this result is actually insensitive to initialization. So it doesn't matter where you initialize your method, you'd always converge to the solution. And on the other hand, if we look at the case of squared loss, as we mentioned, this is a closed form solution. And this has a very different link to that is more rooted in regression because you're looking at maximum likelihood estimation under additive noise. And finally, kind of returning to that more technical point, this result is sensitive to initialization. And in particular, you need to initialize the solution at exactly equal to 0, and only then you get this particular characterization. So looking at these side by side, we see that these really look very different, and we would not expect a priori a similar characterization. However, empirically, if you do a comparison between these two different losses, you actually do observe very, very similar performance. And these are plots actually taken from this nice paper from a couple of years ago by Hui and Belkin. And what they did was they did this very large scale comparison of end-to-end training of deep neural networks on various domains. Yes. Oh, this is all theory. Yeah. So these are all theoretical results. Yes, that's a good point. So as far as I remember, all of these results were done with random initialization. So yes, this is a deep neural network setting. So it's very, very different theoretically from a linear model. Yes, so that's a good question. So in practice, we actually see this similarity, at least from the point of view of eventual test accuracy between these two different loss functions. And again, these similarities are actually very pervasive. You can observe them across neural networks and also more classically in kernel machines. So again, motivated, yes. Sure. Oh, yeah. So here, the greater than equal to 1, this is essentially just a kind of separation constraint. I'm basically saying that I'm achieving this kind of minimum margin of 1 on the training data. On the other hand, if you look at the right-hand side, if you were to multiply both sides by yi, you would just get, you would basically get back your interpolation constraint. Yeah, so that's a good point. The way I've written it here is very specific to binary labels. Cool. Okay, so we see this similarity, empirically at least, between different loss functions on neural networks. And kind of keeping in theme with the content of the talk, we wanted to use this empirical observation and see if we could prove a similar equivalence under our mathematically very different setting of linear models. And well, this is essentially what we were able to do. So here I'm actually visualizing the solution obtained by the MNI and also by the SVM in function space. So here I have one-dimensional data, and I'm doing linear regression or kernel regression with these types of Fourier features, where I take 32 training examples and I take 1,000 Fourier features. So D is greater than N here, and this is very, very much over-parameterized. And at the very start of this whole project, a couple of years ago, we actually ran these experiments as a starting point. And we thought we may be able to show approximate equivalence at least. And what we saw was something even stronger, which was exact equivalence. We literally saw that these functions were exactly on top of each other. And in fact, this is the type of result that we were able to show. In particular, we were able to show that as long as the effective dimension of the covariance matrix greatly exceeded the number of training examples, then in fact, the solutions would exactly coincide with high probability, meaning that this result holds a probability that goes to 1 as N and D go to infinity. So let's unpack this result a little bit more. Just to recall that the spectrum lambda is basically our spectrum of the covariance matrix sigma. So this is literally these two quantities have an interpretation in terms of effective dimensions. So to see this really, really clearly, if we consider the special case of isotropic covariance, this result would hold as long as D, that is the linear model dimension, greatly exceeds N log N. So this is the isotropic case is maybe the simplest case where you can actually see this type of result. So just very directly as a product of this implicit bias characterization, which I spent a few slides talking about, comparing the logistic and squared loss reduces to comparing the SVM and the interpolating solution. And because we have shown this equivalence, we have shown that at least when you're considering linear models and gradient descent, logistic and squared loss give exactly the same solution with high probability. So I do want to say a little bit about just the proof technique and how we did this. I'm not going to give you a full technical proof, but maybe a bit of intuition as to why you might expect this to be true. So I've said a lot about how different these solutions look, but you notice there's one key similarity when you look at these, which is that the objective functions are exactly the same. And even the constraints really do not look all that different. The only difference is that you have an inequality up here and an exact equality here. So because these are both convex programs, you can just use duality, like basic duality theory, and say that, well, what we could do is we could look at the solution here, note that it has a closed form expression, and check for its strict dual feasibility under this convex program. And that would essentially be both necessary and sufficient for these two solutions to be exactly the same. And we can also use this very classical characterization of the dual of the binary SVM, and the fact that the dual variables in the SVM basically denote the proportion of support of each data point in the eventual solution. And we can also use the fact that the MNI is a closed form expression to essentially characterize what its dual certificate would be in closed form, which has this nice characterization. And when we move to showing that this solution is in fact dual feasible, that also reduces to this very nice closed form condition, which is something that we can actually check. So this is all completely deterministic. This is just classical duality theory applied to the SVM convex program. Now when we look at what we need to be satisfied in this case, notice that this is essentially our n by n datagram matrix, and also that we are operating in settings where essentially the training data is very high dimensional. So what will end up happening, and this is actually the mathematical phenomenon that underlies a lot of all of these results on harmless interpolation, benign overfitting, whatever you want to call it, which is this idea that, well, when D greatly exceeds N, this matrix starts to become approximately diagonal, in fact, approximately orthogonal. So this starts to become really, really close to diagonal. And you notice that when this becomes diagonal, this would just become like an element-wise product between y and y, and then it would become all positive quantities. So that's the kind of intuition for why we might expect this type of a result to hold. And it turns out to get, kind of all of the sharp dependencies we have to do a little bit more work. It doesn't just directly follow from plugging in random matrix theory here, but this is kind of the intuition for why you might expect this type of a result to hold. So we had this result for this kind of very simple case of binary labels and linear models on data and under these kind of strong assumptions. So I'll also say now a little bit about more general settings in which we were able to show this similar phenomenon of equivalence of losses. So starting with the multi-class case, which underlies pretty much any real-world machine learning setting, you're always going to have more than 2 classes. So a lot of the linear model framework naturally generalizes here. You just consider k classifiers instead of just 1. And you also can write your labels in this plus or minus 1 space, but just with a 1-hot encoding of each of the classes, where you basically put a +1 if it's the true class and 0 otherwise. And we also denote our true label by mi. So here our decision rule is just going to be, we're going to take these k classifiers, take each of the inner products, and just take the max of them. And that's kind of what happens in the case of multi-class classification. So just as in the binary case, we still look at this kind of minimum 2-norm interpolation. And now because we have, we essentially have a matrix because we have k columns and each of these are of dimension d. So we can write all of this compactly in terms of a Frobenius norm of the entire matrix, but essentially this is still L2 minimization. So what's technically interesting in the multi-class setting is that there are actually 2 types of support vector machine formulations that have existed in the literature. One SVM is kind of the so-called one versus all or one versus rest formulation, and this essentially thinks of multi-class as just k different binary classification problems. And this is really, really very similar to binary, but interestingly, this does not have a direct link to any iterative optimization method, at least not one that I know of. On the other hand, if you were actually to use the cross entropy loss, which is the loss function we use in practice, you would instead get this multi-class SVM formulation, which has a slightly different interpretation of doing these types of pairwise comparisons between the predictor given by the true label, that is mi, and the predictor given by a different label, which was not equal to mi. So lots of notation here, but the high level thing to notice is that the multi-class SVM is the one that actually arises from cross entropy loss, but this is not the same as just binary SVM problems. And in fact, interestingly, you can find examples where these solutions look different. So as in the binary case, our goal is to compare both of these solutions, and especially this solution of interest, to a solution that would interpolate the 1-hot encoded labels. And again, this would arise from optimizing the squared loss. So in this setting, we were actually able to show this type of equivalence with the caveat that you end up not directly interpolating these 1-hot encoded labels, but instead you end up interpolating this kind of adjusted label vector where you subtract off a factor of 1/k. In the next slide, I'll talk about what this adjusted training label vector may look like and some connections to other types of results people have shown recently, but this is what I have for now. And in this setting, we were able to show that kind of under similar types of high dimensional assumptions, we actually have not only that all the constraints are active in this case, but also that the SVM is actually exactly equal to the interpolating solution. And kind of as a technical point, something I wanted to mention is that interestingly, unlike in the binary case, 2 does not directly follow from 1 here. So it turns out to no longer be sufficient to just show that the complementary slackness in the case of multi-class SVM, you actually have to do a little bit more work and kind of work with the dual of the SVM a bit more carefully. Again, happy to talk about that more offline if people are interested in knowing the details. So for this kind of multi-class result, I'll just quickly mention a geometric interpretation of what these adjusted labels really look like. So we can actually see that the type of interpolation you get in this case would be of kind of k minus 1/k if you were at the true label and minus 1/k otherwise. And this actually, so we can actually visualize the phenomenon over here. And interestingly, this kind of has a very natural connection to the simplex structure that you tend to observe in this phenomenon of neural collapse. And we were also able to use this link to show that even if you did not actually have over-parameterized linear models, but you just had features that had collapsed in that specific way, this would also be a condition under which you would actually perfectly fit your training data. So we showed a kind of interesting link between this phenomenon of neural collapse and this type of equivalence between the SVM and the interpolating solution. Now I'll kind of more briefly mention a couple of other generalizations of this type of result that we were able to show. So first, for the case of kernel methods, more generally, we were able to show that under similar conditions of increasing effective dimension of the kernel integral operator, you can show these types of equivalences. And interestingly, the proof technique actually looked quite different from everything I showed you before. So everything I showed you before would have actually worked for any labels. You did not need a probability model on the labels. But the results we showed here actually still, now we needed to actually use a generative model for the labels. And it was a very different proof technique. And the other kind of more recent piece of work that we've been doing, and this is joint with my student Kuowei, is this question of like what happens for other types of loss functions. So the preceding theory really showed us a lot of nice stuff. If you were to compare like the cross entropy loss and the squared loss, or more generally exponentially tailed losses and the squared loss. And this left open the question of what would happen if you used other types of loss functions. So in this case, the picture becomes quite a bit more complicated because, well, the implicit bias is really only characterized in the limit as the limit of a solution of various convex programs. But here we were actually able to work more directly with a trajectory of gradient descent and show not an exact equivalence between the solutions, but a more type of approximate equivalence between the solutions. And in particular, what we could show was that the solution you would get from a general convex loss, and this is unit normalized, minus the unit normalized version of the MNI, and you take an L2 norm between these. So this is just like looking at the difference in the directions, the error in the normalized versions. And we showed that this would also decay in a way that depends on n divided by the effective dimension. So just as before, if you're very over-parameterized, the solutions of these will look more and more similar. And in fact, as long as you are really in this ultra-high dimensional setting, that is, these greatly exceed n, then these solutions would coincide as everything goes to infinity. And like I mentioned, this was a case where we actually worked more directly with the iterative gradient descent, and we used this really nice mirror descent characterization in G and Telgarsky. And this was a really nice paper, so I recommend checking it out if you want to learn more about kind of how you would do all of this for very general loss cases. From a more applications perspective, I'm quite interested in looking at these general loss functions also because there's kind of been a nascent body of work showing that you can use loss functions outside of the exponentially tailed loss if you want to combat problems in robustness and out of distribution generalization. So I'm interested in using this theory to kind of characterize robustness in the future as well. So with that, this kind of brings me to the end of the first part of what I was going to talk about today. And the very, very high level implication here and the main takeaway is that in this case of linear models, if you train with gradient descent, all losses essentially, at least approximately, would lead to this type of interpolating solution. And there are many, I think, ways in which you could interpret this type of a result. First off, this does imply like a type of equivalence of the training loss functions in the very high dimensional regime. And I think what this does is it provides a nice complement to classical perspectives we had in low dimensional settings where the loss functions also lead to similar solutions, but really for very different reasons. And I think the implication of this that I am personally most excited about, and I want to see if I can show in the future also for nonlinear models, is kind of the fact that from the point of view of error analysis, all of this theory implies that really we just need to analyze interpolating solutions. And because of these connections, we can kind of get all of our conclusions for interpolation and translate them to solutions derived by all of these training loss functions. So in a nutshell, it suffices to analyze interpolation. Yes, I see a question in the back. Yes. Yes, so this is a structural result. I'm saying that you find the same solution when you train with gradient descent and all of that. I'm sorry? Oh, yes, yes. So, I mean, just to give you a picture on the previous slide, so these results actually cover like loss functions that are like kind of polynomially tailed and not just exponentially tailed, and there the geometry is super different. And then the squared loss is different from all of these. And of course, this is not a worst case result. You need stochastic data to show this result. Okay, so that was kind of what I wanted to say for my kind of first part of the talk, looking at the role of training loss functions. And again, the major payoff that I'm going to now exploit in the next part of the talk is that it suffices to analyze interpolation. This is a lot easier to provide sharp error analysis for, and that's what we're going to see next. If there are any other questions, I'm happy to take them at this point. Yes. Yes. Yeah, that's a great question. So it depends on what you mean by nonlinear. If you were to look at kernel methods or like NTK, then a lot of this does generalize. Like it kind of just, from a technical perspective, the random matrix theory becomes more complicated, but the results are the same. If you were actually training nonlinear dynamics, that's like if you were to look at a neural network or even a deep linear network, that becomes a much more subtle question. I believe that the equivalences to interpolation could ultimately be shown, but there are some other more subtle differences in the dynamics of loss functions. So if you look at NTK, it's like a squared loss phenomenon, and you don't see it for log loss or anything else. So I don't believe the equivalence in training losses actually holds for neural networks, but I think this connection to interpolation could be more general. It's a bit subtle, but happy to talk offline. Okay, so yeah, thanks for all the really nice questions. So I'm going to move on now and shift quite a bit to error analysis, and I'm going to look at the role of the evaluation loss function at test time. So here's just a quick refresher on our basic setup under which we will do this. So we have a classification model, and now I'm going to make this generative modeling assumption on the label, which is of random label noise. And just because of the preceding set of results, we are going to only look at minimum L2 norm interpolation. And remember, this has this nice closed form expression and is very, very interpretable. So we're going to look now again at loss functions, but more from the lens of what we would do at test time. So in the case of regression, as mentioned, we would look at the test mean squared error, which would just be, well, what are your predictions and what is the difference between the two values, and basically looking at the squared error function there. But when we look at classification, well, we don't care about any of this. We don't actually care about parameter recovery. And this is going to be very central for the results I will now talk about. We only care about getting the sign of the prediction right. So this is what I mean when I say that for classification, we use the test 0-1 loss, and for regression, we use the squared loss. And when I say good generalization in this talk, I'm really formally referring to statistical consistency, meaning that when I think of d being much greater than n and sending n and d to infinity at the same time, like together, what I really want is for my error to go to 0 as n goes to infinity. So as before, I'll just give you a kind of very quick overview of kind of recent perspectives on this entire problem. So as I mentioned at the start of the talk, we have a pretty good understanding of the MNI in the case of linear regression. And the focus of what I'm going to talk about now is classification, especially in relation to regression. So the perspectives that I'm going to talk about in today's results will be very non-asymptotic. So I'm thinking of d being much greater than n, and I want to get these finite sample error bounds that depend on d and n and are tied up to constants. And these are nice because these are bounds that are very interpretable and in terms of spectrum and all of these nice kind of notions. As I alluded to in the first part of the talk, there's also this very nice complementary asymptotic perspective where you assume specific signal models and kind of covariances, and you can get exact expressions for the error. And that's not a perspective I'm going to touch upon today, but again, happy to talk about that more offline. So when we look at analyzing L2 minimization solutions from the point of view of test error, it's actually really, really important to have some type of special structure in the covariance matrix. And in particular, if you were to use just isotropic covariance and do L2 minimization, even if there was no noise in the data, then this solution would in fact not generalize well. And the reason for that is essentially that, well, if you had signal, then that signal would completely spread out across all the features, and then that's actually not very conducive to good generalization. So it turns out to be very important when we study the generalization of L2 minimizing solutions to have this special anisotropic structure in the covariance, where the top components of the covariance are actually much kind of amplified relative to everything else at the bottom. So to really capture to give a formal framework in which we want to show our results, I'm going to introduce this ensemble of what I call bilevel covariance, and you'll actually see this in many other papers on the topic as well under various different types of names. And the idea here is that I'm assuming the specific type of bilevel data covariance, where the top S features are much higher in terms of the eigenvalues, and the bottom D minus S features are quite a bit lower. So there are kind of three important parameters in this model. First, the effective sparsity level, or like the number of prioritized features, which I'm going to assume to be sublinear. The number of actual parameters in the model, that's D, which is going to be much, much greater than N. And finally, the ratio between these two values. And when I say that my model is anisotropic, what I really mean formally is that I want this ratio to also grow at some rate as a function of N. And what is the intuition here? Well, if your signal actually lay in one of these, if your signal was primarily comprised of these top S features, then because the proportion of the eigenvalues is much, much higher, then you can actually show with L2 minimization that most of the signal here would be preserved. And in particular, parts of the signal over here would in fact not be preserved at all. So that's kind of, this is a lot of what I'm saying kind of follows from the regression theory for this setting. And that's kind of, a lot of that, as we're going to see, carries over to the case of classification. So I will also mention a few connections of this type of anisotropic model and maybe a few lenses through which you can view this. So a lot of the types of random feature models that people tend to consider for this type of double descent behavior, essentially, if you look at the eigenvalues of the ensuing data covariance, you will see this type of structure. And this again has this kind of feature where you're doing linear regression with noisy copies of an underlying function, and your true function was also kind of sharing that structure. And this is actually a setting where if you kind of looked at this, looked at the covariance and analyzed its spectrum, you would very much see this type of structure. Another very relatable example to me is this setting of the Gaussian mixture model, where now you have your features which are just kind of plus or minus 1, and then you have a mean vector and you have some noise. So you have Gaussian, like binary Gaussian mixtures. And here actually the ratio that I'm describing here turns out to take this very natural interpretation in terms of the ratio of the signal strength, that is mu squared, divided by the variance of noise, which is given by nu squared. So if you want to think of example 2 as a kind of running example for a lot of this, then it's a good example to visualize these results through. And just more generally, if you think about what's happening in a kernel method, any real world kernel does have some sort of eigenvalue decay. I mean, you're not going to have all the eigenvalues at top. And your true function is also going to have a bounded Hilbert norm, meaning that a lot of its true kind of energy is going to really lie within these higher valued features. So spiritually, a lot of what I'm describing here is also what you see in other high dimensional ensembles when you're looking at L2 minimizing solutions. So under this ensemble, we showed that, well, so a lot of what I described was kind of very classical for the case of regression, like essentially for, going back to this, for good generalization here, you would, sorry, there's a bit of a lag. So for good generalization here, you would basically need S to be much less than N, D to be much larger than N, and for the ratio between these two to grow at a certain rate. And that's what I'm going to show in a little bit. So at a high level, what we show is that for classification, qualitatively, you need the same type of phenomena to hold, but there's actually a gap. And there are much milder conditions under which classification would work. So with that, I'm going to describe the result a little bit more formally. So coming to the case of classification and regression. So starting with the case of regression, what some of the recent results on analyzing the MLI actually showed was that this ratio between the two features, as long as it grew greater than d over n, remember that d is greater than n here, so this is a stronger condition, you can actually show that, well, you would have exact parameter recovery even though you're using L2 minimizing solutions, and regression would in fact generalize well. So what we were able to show is that under this much milder condition, where the ratio between the higher and the lower level eigenvalues grows at a slower rate, just greater than square root of d over n, we end up in this intermediate scenario where regression would clearly not work. And you can see that from the plot of the recovered function, right? You can see the recovered function is really, really far away from what the true function value would have been. But yet, if you only care about getting the sign right, then this is still a pretty good situation. So we were able to show that in this intermediate regime, classification would generalize while regression would not. And finally, our analysis was in fact tight, and we were able to show that, well, what would happen if we were kind of to the left of this regime? So if the ratio was less than square root of d over n, well, this would lead to this bad scenario in which neither of the tasks would actually work well. So in a nutshell, our work showed the existence of these three regimes. On the right, only like both regression and classification would work. On the left, neither of them would work. And in the middle, we had this strong separation where regression would not generalize, but classification would in fact generalize. And just as a technical point, I will also mention that there has been some historical evidence of a separation in the tasks, but this was typically not explored in high dimensional settings. This was more commonly looked at in low dimensional settings, and the differences were typically in terms of rates of convergence of error, rather than these strong separations in generalization between the two tasks. So this is really quite a striking phenomenon that you observe, and it's really because we are in high dimensional settings. So I'm guessing I have about 10 to 15 more minutes, which maybe gives me time to talk about why we can get this type of separation. So I'll try to give you a very bird's eye view of why we expect the separation between the two tasks. So starting with the case of regression, we can consider a super simple situation where we have this type of bilevel covariance. And let's assume that we have signal that is only, that is maybe one sparse, that is only present in one of these feature components. So over here, when we look at what how we would want to analyze either regression or classification, two components of the recovered signal become important. The first is, well, what is the proportion of the true signal that was preserved? And that's kind of what I'm denoting here by this fraction of survived signal given by SU. So clearly you would want this to be as high as possible. You'd want to try and preserve as much of the true signal as possible. The second important component is how much of the recovered signal is actually in these spurious features, or these features that you don't actually want to recover. And this is what I'm calling essentially contamination. So in the case of regression, well, there's a very elementary expression you can get for the error in this case, which would just be, well, what is the difference between this fraction and 1? And you ideally want this to be as close as possible to 1, plus the overall fraction over here. So just the sum of the squares of the magnitudes of features along all of these components. So this is just follows directly from the expression for the mean squared error in the case of regression. Sorry, there's a bit of a lag in the Zoom. I apologize for that. So it turns out that you can just kind of use this along with these feature by feature characterizations of the MNI, which in turn follows from the fact that the MNI has a closed form expression, to really show the type of result that I showed that I displayed on the previous slide, which is that the MSE would in fact go to 0 as long as this ratio is sufficiently large, that is greater than d over n. So moving on to the case of classification, a lot of this picture is actually mathematically similar. These quantities still turn out to matter. You still need to look at the fraction of the true signal that survived as well as the contamination variance. But the key observation here is that we no longer need the true signal to be fully preserved. All we really need is that the ratio of the survived signal is sufficiently large with respect to the magnitude of the signal, the kind of recovered signal that goes into these spurious features. So mathematically, it turns out that earlier, remember, we needed this to be close to 1 and we needed this to be close to 0. And now all we really need is that the ratio between these two quantities is growing sufficiently large. So notably what this means is, well, you could even have situations in which the recovered signal in terms of its true component is completely attenuated and you go all the way to 0. And this is what you actually saw in some of those function evaluations and visualizations on the previous slides. And we can actually deal with situations of that type as long as this is going to 0 at a slower rate than the rate at which our contaminated part of the recovered signal is going to 0. That is, all of the proportion of falsely discovered features should be much, much smaller than our proportional of recovered signal. So at a high level, you can tolerate this attenuation of signal and lack of signal recovery that, by the way, is not new to any of this work. You actually see it very classically in signal processing and statistics. But we can tolerate this for classification provided that the proportion of falsely discovered features is comparatively really, really small. And really, as a kind of result of this observation, this is kind of really what underlies our final result, which is that the test 0-1 loss is in fact consistent as long as the ratio exceeds square root of d over n. So I'll actually conclude this with a bit more of a high-level implication for the separation in tasks and what all of this really implies. So remember that we looked at this example of bilevel covariance, that is 2 eigenvalues, and we showed that there's this intermediate regime in which regression would not work, but classification would work well. Remember, we showed this for the case of the minimum norm interpolating solution, which you'd get from the squared loss. And as a direct product of the first part of the talk, where we showed these equivalences between training loss functions, all of our results directly carry over to the support vector machine and to more general classification-oriented training loss functions. And what's interesting about all of this actually is that you can actually go back and look at whether data-dependent generalization bounds from the learning theory literature would explain any of these findings. And at least as of now, I do not know of any generalization bound that would explain this type of behavior. I think it's a very interesting direction to think about whether we can derive sharper generalization bounds that might hold more generally, but also be able to explain regimes like this one. So that was kind of most of what I wanted to say from a technical point of view. So I'm going to leave you with a few broad takeaways from everything I discussed today. So in the very first part of the talk, we saw that at least for linear models and gradient descent, the training loss function might not matter all that much. And in fact, there's this very direct connection between the solutions of very geometrically different training losses and this very particular solution of interpolation of either binary or multi-class settings. And again, I think the way I view this is really through a powerful analysis tool, because what it means is like maybe it might just suffice to analyze interpolating solutions of this type. And in the second part of the talk, we saw that you can really exploit this behavior and connection to interpolation and do a sharp error analysis for classification tasks. And in the second part of the talk, we saw that it is possible to identify high dimensional regimes in which regression would not work, but classification would. And the thing I want to emphasize in this model is that, in fact, we showed that classification will generalize well despite many ingredients going against it. I mean, we had ultra high dimensionality, we had interpolation of noise, like we were fitting the noise in the data, and also, most surprisingly, you're not recovering the signal. Like there's really poor signal recovery and there's attenuation of signal. And despite all of this, we saw that it is possible to show that classification would still generalize well. And I'll also leave you with some current research topics that my group and I are really currently working on. So I'm really interested in using some of this theory to think a little bit more about adversarial error and also auto distribution error. And I'm really interested in seeing, like, can we play around with loss function design a bit more, both in theory and in practice on deep neural networks, to think about whether we can design new loss functions and maybe optimization methods to improve performance along both of these axes, which I think remains empirically quite an open direction as well. I'm also thinking a bit with my students about accelerating optimization methods through a more online learning perspective. I didn't really get into that in this talk, but again, happy to discuss that offline. And more recently, I've also been thinking about the role of other types of non-traditional regularizers, such as data augmentation in generalization. And of course, the big open hole in everything I discussed today is that all of this was for linear models. So I'm really, really interested in seeing how much of this translates over to deep neural networks. So with that, I'd like to thank you all for listening and for the great questions in the first part of the talk. I have a last public service announcement, which is that we will be giving a tutorial on some of the more basic aspects of overparameterization and interpolation. So a lot about the regression setting as well at NeurIPS 2023 on December 11th. And yeah, my presenters will be Spencer and Fanny, and we have a bunch of wonderful panelists and speakers joining the event. So yeah, with that, thank you again for your attention.
Great talk. Thank you so much. So given that you have mentioned that this is one of the interests of trying to come up with corresponding theory for neural networks and stuff. So if we are to think, because I'm just busy, right now I'm using a variational autoencoder model in combination with contrastive learning and stuff. So I'm just like curious if we are to think of what to do with this model, and if I want to explore contrastive loss or triplet loss or any other related ones, where would you start? And are there people who are currently actually trying to study that already that you know of?
Yeah, that's a great question. So for the case of contrastive loss, I would actually say a lot of the questions we set up today are not very maturely understood, even if you look at linear models and kernel methods, actually. So I would even start there. And if you look at contrastive learning, the types of loss functions people use are also quite different in nature. Like if you look at the info NCE loss and all of these. So I would actually start like even with basic questions, like what is the implicit bias of info NCE in like high dimensional settings, and what does that look like? In the case of deep learning and supervised settings, which is kind of more what I was referring to. I mean, from my point of view, like I said, I don't expect the same broad similarity between training loss functions to really hold. What I do think may be possible is this connection to interpolating training data. So there's a kind of distinction there, because like, I guess if this is maybe going into too much detail, but if you look at like kind of what happens with the squared loss and neural tangent kernel, that's more of an L2 type of bias. But if you look at say log losses and other types of losses like people use in practice, there's a better inductive bias that you get using those losses. And over there, I'm still kind of curious about, like, basically, can we connect the solution to the type you would get if you were doing that with a regression method instead? I guess my short answer to that question would be, for the case of contrastive losses, I would actually start with simpler models there as well, just to see what we understand, and because the loss function used in contrastive learning is really, really different from any of this.
Any other questions?
I think there's a question in the back.
Thanks, that was a really great talk. I have more questions for you offline, but online, doesn't your work indirectly address deep neural networks if you just treat them as frozen nonlinear feature extractors that can spit features out of arbitrary dimension, and then you just apply your linear model theory on top of that?
Yeah, absolutely. Okay. That's actually something we're trying to exploit in terms of, like I mentioned, some of the detections about adversarial, like auto distribution robustness. So there's like an increasing practice where people do a lot of just retraining of frozen features with the idea that the learned features already have a lot of good information in them, and it's just you might kind of want to fine tune them or kind of improve them further. And that's a place where we're using this connection quite a bit, and we're trying to connect theory to practice. Yeah. Right. Yeah. So the centering of the features is a pretty mild assumption. I mean, you can typically just recenter and make that go away. The assumptions on diagonal covariance are stronger, and I mean, it's a reason I wanted to actually move to this more general kernel methods theory and try to get rid of some of those assumptions. But I think the characterizations here are very clean, like they're in terms of spectrum of covariances, and at the least we can test out those conditions in practice and see.
All right. There's no other questions. Let's thank video one more time. And now will be lunch, and then we'll reconvene for the afternoon.
Okay, so we're about to start our afternoon or after lunch session. I'd like to welcome Genghis Pelham from Harvard University. Genghis did his PhD at Brown University and after was a postdoctoral researcher at Harvard at Janelia Research Campus and then at Flatiron Institute before joining Harvard. His research is on theoretical neuroscience and on the theory of neural computation in artificial and biological networks. And today he will tell us about things. So he'll tell us things now.
Yes, I'll be talking about this. Okay. Well, thank you very much for the invitation. It's a great pleasure to be here. If I'm not coherent, I came out of a red-eye flight, so forgive me for that. Okay, so this is DeepMath, and we are interested in mathematics of deep learning. So what do we want to achieve, I guess, like from a mathematical understanding, or let's call that a theory of deep learning. And we might all have different ideas. So here's a wish list from my side. We are obviously nowhere near this, but I guess that's what we might want to achieve. You probably want to have an analytically tractable or efficiently computable theory, right? I mean, you don't want to have a theory that's so, uncomputable. It's very hard to get sense from it, which replaces deep learning. So that's just not something you don't want. You might want to have, from this mathematical theory, some interpretations. So I call this mechanistically interpretable. By looking into these equations, theorems, whatever mathematical sort of framework you use, you want to get some insight that wasn't obvious by looking into simulations or graphs or just equations that define a feed-forward neural network, for example. We obviously want this theory to be accurate, right? That it does describe something in application or practice relevant situations, right? So if it's not accurate, it's describing the thing, that's probably not a good theory. The next one is I find interesting. So, I mean, deep learning is, used in many different fields for many different purposes. And what you want to understand about deep learning might be different depending on the application. For example, I mean, I'm a computational neuroscientist, so one way neural networks are used in that domain are as mechanistic models. What that means is you actually care about what happens in between input and output. For example, you might want to make associations about neurons in a particular brain region and associate that with a neuron in a particular artificial neural network. So therefore, I mean, to be able to make these associations or use an artificial neural network to explain the brain, you do need to understand what happens in between all these representations, their evolution, and so on and so forth. Right, so basically, you have to also answer domain-relevant questions. And finally, practical advances, right? So you want sort of this theory to help you discover new tricks to make your maybe optimization run faster, build smaller networks for inference, and so on and so forth. And of course, you might want to have all of your sort of other wishes and things to add to this list, or maybe there are some things that you don't care. Now, it's a great list, and I don't claim that at least in my work, I'm near anywhere in any of these sort of things, but I just want to tell you about the story of where we are. And basically what I want to start by is pointing to, the closest we have come to a practical advance. Right? So this is basically the next figure, okay? I'll describe what this is, and then I'll describe you the story of it, which is going to go through all these theoretical stuff that we've been doing for the last few years. So this is a story, this is a concept called hyperparameter transfer. The idea is the following. When you're training a large model, you want to optimize hyperparameters, say learning rate, right? So what you might want to do is basically do a sweep over learning rates for a small number of epochs or something, and choose the optimal one, and then and then run on it. Of course, I mean, if the model is large, it's basically the compute that you need to put into this is grid size times the model, so that's not good. So wouldn't it be nice if you were able to do your sort of learning rate sweeps at a shallower and sort of shallower and narrower, okay, these are the two sides, network, and just copy that parameter, whatever you found, to the larger network, and that way you would be cutting a lot from compute. So this is what's exactly been done here. So what's being shown here is the following. So each of these curves are a different sort of ResNet with different sort of depths and widths. So dashed means it shows a depth difference, and the colors are refer to depths. Sorry, dashed is width, and colors refer to depths. So we train a ResNet on this data set for sort of a certain number of epochs. I forgot what it was for this particular figure, but you stop at that epoch and plot the test loss for all these different sort of aspect ratios, architectures. And then the point I'm trying to make is basically, the learning rate, the optimal learning rate for this particular epoch at least, across all these architectures are the same. So basically you could go to this model, which is the sort of the shallowest and the narrowest model, do your sweep and find that point and directly jump to this line over here, and you do your training, which is going to cut you a lot of compute. Okay, we're on the same page here. What do I mean by hyperparameter transfer? Okay, cool. So now what I'll try to explain is basically the story behind this figure. So how did we come here? And basically, it's all started by a few years ago. We are thinking about looking for some reduced, simplified description of deep neural network dynamics. Obviously, this is very complex. So I'm trained in physics, so my mind thinks like, okay, there must be a simpler model, a toyish model, or some description, reduced description that captures the main aspects of what's happening, but something that I can attack with paper and pencil. And at that time, basically, this large network size limits were becoming fashionable, and it still is I think, a very sort of fruitful thing to study. And in particular, so there's a delay between this and this, so that's why I'm stopping in between. I'm sorry about that. There's a particular influential limit, the so-called infinite width limit, and the neural tangent kernel that arises from it was very sort of popular. And just to make sure we're on the same page, by width, I mean how many neurons you have per layer, and you're going to keep increasing this until you hit infinity. Now, when you're taking something to infinity, of course, you have to care about how you scale other things when you're taking that thing to infinity. For example, you want to make sure that these weights are scaled in the correct way such that the total input that comes into this unit over here, or its variance, doesn't blow up or doesn't go to zero, stays something meaningful. And that's why, for example, you might want to scale the initialization of these weights by 1/square root of it. And of course, this is a known story. I just give you, just to remind you, I'm not going to say, this is not going to be the main point of my talk, but just to tell you what the background here was observed by several authors, famously by Jacquot and colleagues, that basically in this particular limit, what happens is the model becomes linearized, or basically a kernel model. What that means is you will take inputs, pass them through some static nonlinearities. So this should have been a theta 0, and theta is the parameters here. So the features are defined by the gradients of the network's output with respect to parameters. And then on top, basically solve a linear problem. And this training a neural network would be equivalent to solving this problem. And if you're familiar with kernel machines, you'll realize that this is the feature map that defines the kernel in this case, which is called the neural tangent kernel. Okay, so that's the well-known story. And of course, everybody likes kernel machines because there's tons of theory that you can do with it. These are essentially linear models with complicated feature spaces. So we had our own versions of it. So basically, okay, just to point to one paper over here. So we were able to use some physics tricks to be able to develop a so-called theory. So what does that mean? What do I mean by this? Here I'm plotting basically the test error. Okay, so this is on some scale we can talk about. Solid on training a 3-layer neural network on MNIST, for example, with width 800 is an MLP. The solid line here is a theory that we developed, some equations that we developed that basically just takes in as input the infinite with NTK. And then on the x-axis is this number of samples that this network sees. And all these points that you're seeing are simulations. For example, the triangles are directly doing kernel regression on that data. And the circles are neural network experiments, and the variance that you see is coming from the variance in initializations. And basically you see a very nice fit. That's great. Also, you do see some deviations over here. And actually, when we wrote this paper, we thought this was basically it shouldn't have been there, but I now understand why it's there, and I'll tell you about it, why it's there at the end. But basically, this was possible. And look, studying this limit, also you could come up with other sort of interesting stories about, like, for example, some kind of a spectral bias, meaning the fact that these kinds of models try to explain data or first learn simple explanations of data. And what simple means is basically defined by a diagonalization of this kernel in terms of its eigenfunctions and using this Mercer decomposition. So here, this k would be the NTK. P of x here refers to the data distribution. So this can be a direct distribution over the data. And this phi is referred to the eigenfunctions that comes out of these decompositions. And the idea is basically, if the function that you're trying to learn in data has an expansion on these eigenfunctions, and if the components corresponding to higher eigenvalues are high, it's an easier function. Otherwise, it's a hard function to learn. An extreme example of this is plotted here. So this is actually a very clean example you can explicitly work out. So this is a target function that's composed of spherical harmonics. So basically, you take a high-dimensional sphere and you define functions by combinations of spherical harmonics over there. This is the function that you're trying to learn. And examples come from sampling uniformly on the sphere, and basically that's the input, and the outputs are basically calculated by this function. And spherical harmonics have two indices, k and m. So one is called the order, and the other one is called, I forgot what it's called. I always mix, but I'll just call them k and m. So you fix the first guy, and the second guy is basically like, can be any number of these second guys can be contained in this target function. And the result is, and you can think of this as some kind of a frequency content. As k is higher, this becomes higher and higher frequency looking functions. So the result that you can recover from this is basically, you'll need, so suppose your data was living on d dimensions, you will need about d to the k samples to be able to learn this function. Okay? So what that means is, so this is exactly what's been plotted here. This is the test error on, as a function of number of samples that you're seeing. P is the number of samples in my notation. And these different lines are different sort of targets that contain different sort of k content. And you see for k equal to 1 function, you need about 15 samples. And for k equal to 2 function, you need about 15 squared samples and so on and so forth for these curves to start falling down. And this guy is a k equal to 7 function. So you would need about 15 to the 7 sort of samples. Actually, in this case, you'll see that this neural network will never be able to learn this in this particular limit. So that's, for example, one fact sort of that was understood using this kind of theory. The other one is basically scaling laws, relates to the scaling laws. You can also show the following. Now, in a lot of data sets, so for example, you can plug in things like CFAR10 and so on and so forth here, choosing k to be NTK and calculate these eigen values. You'll find that they fall like a power law. And also, you can construct the target function. Let's say the target function has some classification labels, okay? And then all these target functions can also be expressed in terms of these functions. And those coefficients also, turn out to fall like a power law. And you can figure out from, again, this theory that if these two things hold, the test error that you're seeing should be falling as a power law in terms of sort of samples. And these power laws turn out to be non-fractions. So they're not like 1, 2, half or something. So basically, this is also the one result out there that captures some non-power law fraction in these generalization kind of scenarios. And basically, you get a scaling law out of it. Okay, so these are some results that you capture from this kind of a limit. But of course, the problem with it is it has static internal representations. What that means is the following, right? So basically, these features over here, they don't adapt to data, they're fixed. So therefore, it doesn't sort of capture the fact that the intuition we have that deep learning is learning some features that adapt to data. That's why it's useful, okay? So what's the way out of it? So one way out of it is basically, just going not to the infinite width limit, but a little bit sort of large, but not infinite. So you can use some analytical techniques like perturbation theory kinds of things from physics, basically series expansions in 1 over width to try to capture that sort of aspect of it. So that's one approach people have been taking. We've done some of that. But today I want to sort of talk about another approach, that sort of try to build in efforts to build a theory of sort of these neural networks and their training dynamics that captures sort of this representation learning aspect. So we're going to ask the question, are there other weight scalings for a consistent infinite width limit? Okay. So here's what I mean by this. Let's just be a bit more careful about like what we're doing and how we're scaling things. So in this plot, what I've done is the following. So basically, I've taken a feed-forward neural network, okay? And H's are my pre-activations, L is my layer index. So these are vectors, meaning, suppose you have n units in a particular sort of layer, so they're n-dimensional units. And mu refers to a data, so it's x mu that goes in, and f mu is what comes out, okay? And phi's are the activation functions, w's are the weights, and so on and so forth. So we're gonna, for the rest of this talk, for most of this talk, we're gonna basically stick to a particular loss. It can be anything, and some data set on which this loss is trained, some XY pairs, and then the training will be done by gradient flow. All right, cool. So what's happening over here? So what I've done is basically I've introduced factors of n and their sort of powers in every place I could imagine to put them. Right? For example, when I'm initializing this network, I could put a factor of n in terms of the function that relates, w times a phi's to the pre-activations. I've put factors of n and their powers into the way I initialize these weights. I put factors of n in the learning rate, and I've put a factor of n in basically this map between last layer's pre-activations and the output. So you can equate them. You can think of this as f and h as the same thing. I just want to introduce another factor of gamma here, which is going to be important in what comes out. All right, and this d is basically the input data size. I'm not going to take that to infinity, so that just stays there for good normalization. So the question is the following: how can I take these, like as I'm scaling n to infinity, how should I choose these a's and b's and c's and d's in a way that this network behaves in a reasonable way, right? Because if you don't get it correctly, you might easily run into a situation, basically, all these pre-activations die, or they saturate, or like they go to infinity. They're all possible. So you have to be careful about how do you take these things to infinity. For example, if you don't get the scaling of the learning rate right, as you're taking things to infinity, this training might be too slow or too fast. These are all things that you need to care about. Okay, so how can we do this? So basically, what you can do is come up with a set of, let's say, principles that you're going to demand from your network in this particular limit, such that, and ask what the consequences of these principles would be. So here are three things that I think are reasonable. Okay. First, you want pre-activations H to be order 1, meaning that they don't go to infinity or 0, right? At least even for practical engineering purposes, this is a good reason, it's a good thing to do. What we want is basically some kind of trainability, meaning that the outputs evolve in order 1 time, meaning as I'm scaling things, the training time doesn't go to infinity or go to 0, it stays sort of, like basically doesn't scale. And so this third option is the one that's going to differentiate this particular thing with the NTK idea, that basically the H's themselves, the pre-activations themselves also evolve. So they don't stay at initialization what they were, but they also change in some order 1 training time. Okay? So you can put all of these three things together and then basically do some back of the envelope calculations, or you can do more rigorous calculations depending on sort of your comfort with mathematical rigor. And then you're going to come up with basically this set of conditions. Okay, so basically this is the idea. So all these things give you some conditions on how to scale these A's and B's and C's and D. Okay, so this is basically a set of conditions. So one thing, if you stay into these equations, that you'll notice is actually they don't specify all A's and B's and C's and D's. There is 1 degree of freedom left. Okay, and then you have a choice in basically choosing what that degree of freedom is, but they all correspond to the same sort of network dynamics. Okay? This was first worked out by Greg Yang and colleagues in this tensor programs paper. We have our version of it in using sort of similar but different considerations in a New York's paper last year. Okay, all right. So, but the point is the following. So what happens in this particular limit is interesting. So now we are starting to see something different than basically what NTK is doing. Okay. And just to make sure that we're on the same page, we're going to put everything onto a figure again. Okay, so the difference will be the following. Okay, basically, the difference between the standard kind of scaling and then here will be, instead of scaling all these weights by square root of n, we'll still do this in intermediate layers, but in the last layer, we're going to basically scale everything with 1 over n. And also, we have to adjust the learning rate appropriately to be able to be in this limit. Just to make sure we're on the same page, what I must say is that, I mean, even though I'm showing here a network with 3 layers, actually this applies to much deeper or shallower. Towards the end of the talk, I'll also take depth to infinity. So this is a general statement. Okay. All right, so what happens in this limit then? So now we found a consistent limit, meaning that things are well behaved. Can we explain sort of what happens in that field, in that limit? So for that, we're going to use basically this sort of technique called mean field theory and try to understand what happens in that particular limit. So we explain these things in these 2 papers, one from last year and one from this year. I just want to point that similar limits were considered in 2-layer networks, not any depth, by Rotzkopf and Wanden Agenden, I suppose, and then May and colleagues and Montanari. So these were 2-layer networks, and the difference between 2-layer networks and here will be, I'll point to this in a second. The mean field description there was basically a description of the measure on weights. Here it will be something different, and basically, and also the deeper version has been worked out in tensor programs, and I'll point to you basically where we get similar results and where we differ as we go on. Okay, cool. So the reminder, basically, this is what we're going to consider. Okay, so this is the network architecture we're going to consider. Now I put all the scalings everywhere they should be. So I also introduced a sort of order one. The thing doesn't scale, basically a factor here. And then if you know the literature, you might sort of remember that this is a factor that controls the speed of representation learning, meaning that if you take this to 0 or infinity, it has infinity means a lot of representation learning, and 0 means little representation learning. We'll talk about that in a second. So, but this is the architecture we're going to do. We're going to take n to infinity and basically study what's happening. So to describe the result of that limit in words, so what's going to happen is the following. The training dynamics, okay, in that limit we will be able to describe it by a stochastic process. So we'll replace the whole neural network with a stochastic process. This will be a non-Gaussian stochastic process. We'll have complicated, cumulants and so on and so forth. And the stochastic process will be over single-site pre-activations and pre-gradients. So we'll define what pre-gradients are, but pre-activations, I mean the following. That's what's going to happen is we'll think of every pre-activation network, especially in a particular layer, as IID draws from the stochastic process. So they will be just described by the same statistics, but IID draws. So that's basically what happens in this limit. Okay, so how do we come about basically this limit and what are the key quantities there? So to be able to see what's happening over there, you have to do some mathematical sort of manipulations. And especially notice that all of this gradient flow can be written without or very little access or to weights, purely in sort of feature space. What do I mean by is the following. Now, the key quantities are the following 2 sort of kernels. Technically, they're not kernels, but I call them kernels. Okay, so here's what these constructs are. We're gonna take all the neurons, all the units in a particular layer in responding to a particular input mu at a particular training time t, and dot product this vector with the same layer of activations, but for a different input and for a different sort of time. You have a question? Yeah, so I mean, in the next slide, I'll write the full dynamics. You'll see what's happening. But you're right. So basically, this is exactly what we talked about just a second ago. Basically, the map between these things and the weights are not one-to-one. And these are the relevant sort of quantities that I'm saying is actually for the global flow. But yeah, but you're right. Okay. All right, so this is an object. So you can also construct another object, a similar kind of a dot product object from the back propagation signal, because this is training, right? You have to have the features and the back propagated signals. You have to consider their dynamics. So the analog features there is basically the gradients of last layer with respect to intermediate sort of layers. Right? So these are some vectors whose dimensionality is intermediate layers. So you can sort of construct these objects, again, of the same indices using these G vectors. So I'll call these guys gradient kernel and these guys feature kernel. And one way you can see that these are fundamental is the following. So if you were to write down the evolution, the time evolution of the network's prediction, okay, so this is the network's output to a particular input, okay, so across training, you'll find that basically this whole thing or its dependence on weights is fully captured by these objects. So nothing else enters. If you know these guys, you know the network's output evolution. Okay, so that's why they are like fundamental objects. The other delta that enters here is basically the just derivative of the loss with respect to network's output. So if this was a square loss, for example, that would be just a linear function of f, and so on and so forth. Okay, so these are the fundamental features. And so the next slide is just to show that, I mean, we don't have to go into the details of it, but basically this is gradient flow rewritten only in terms of activations and these objects, okay? The only place weights appear here is at initialization. You can't get rid of this because when you initialize, you introduce basically something about this network. So basically, so the initialized weights appear as some functions here, and the rest is basically described by these evolutions of pre-activations and these gradient sort of signals, and no weights appear anywhere else. You don't have to understand this equation. I just want to show that there's actually a set of equations. Okay, so but here's the trick. So what do we hope to see in the limit of width going to infinity? And then, okay, so here's what's going to happen. So these feature and gradient kernels will concentrate, meaning, you know, they were random numbers because there's an initialization randomness coming at finite width. But as you take width to infinity, they just become, you know, variance zero objects, scalars, they concentrate, okay? This is like the NTK limit, basically the kernel concentrates. But the difference here is that they're time dependent. They will evolve in time, training time, okay? The other thing that's going to happen is, so there will be a distribution of these H's, pre-activations, and these gradient fields over sort of layers, across sites and layers. And we can think of a probability distribution that sort of defines this sort of joint density. And we'll see that they'll basically factorize, meaning we'll be able to think of every site as an IID draw from some distribution. And basically, so this is the idea of a mean field limit, by the way, the idea that you can think of like basically these things as IID draws. And of course, as a function, just because you're sort of these things are concentrating, it's also the fact that basically these population averages, meaning averages over like all these layers, dot products, will be sort of replaced by averages over these probability distributions. So that's what's going to happen in this limit. Okay. So just a few slides about how do you actually derive this, okay? So, the trick that you use to derive this comes from statistical physics. It is a path integral formalism, so-called, okay? And it goes with the name Martin Sigiaro's formalism, okay? So what you do is basically the standard physicist trick of the following. What you do is you define a so-called a moment generating functional. So what does that mean? So this functional basically, it's a functional in the sense that you introduce some source fields. These have indices of layers and time and basically data points. And by calculating their derivatives, you can calculate averages over some of these stochastic quantities that we have described over the full sort of evolution of this time. And then what you do is basically you try to calculate this average with respect to the variance introduced by initializations. And you can do this because the way we wrote gradient flow, all the initial points was explicitly accounted for. If you were to do this for like standard gradient flow in the weight basis, you wouldn't be able to do this because the initialization is a part of the full evolution to be able to separate this. So I'll skip the details of this. So basically, but at the end of the day, here's basically how much comes out. So you do this calculation, and it boils down to a saddle point, and you look at the saddle point, and then here's what happens. Okay, so this is what's being shown in this slide is a stochastic process. Okay, it's complicated. But my claim is basically if you simulated the stochastic process and calculated the network's predictor using the stochastic process, you'll get exactly the same result as training a neural network. Okay, so what's happening here? So let's look at this line. So we don't really have to understand everything that's going on here. I'll show you simulations, but just to give you a gist of what's happening. So this guy is basically describing the pre-activation at a particular layer L with respect to a data point mu across training time t. Notice that this is not a vector anymore because it's a random number. And in a real network, every site in a particular layer will be different samples, different realizations of this random number. The first term over here is a Gaussian process. This Gaussian process has basically a covariance sort of kernel that's defined by the activations or the feature kernel of the previous layer. This is like the NNGP-like construction, if you're familiar with this case. Okay, and the rest here is basically the non-Gaussian part. This is everything that includes sort of other kinds of gradient signals and non-Gaussianities coming from everything here. So we don't have to go into the details here. And the second equation here is basically doing the same thing for the gradient signals. Again, you can think of gradient signals as IID draws. And notice that basically to be able to define these Gaussian processes, you need to have access to these kernels that I introduced. And again, these are feature kernels that you need to calculate. Okay. So this dynamical mean field theory result, so we derived it. And if you're familiar with the tensor programs literature, they're studying the same limit using different techniques. And basically, if you compare these approaches in the relevant limits and settings where they should match, they match. Okay, so basically we got similar results. The thing that I wanted to say about this is, okay, so it's a complicated process. Just to give you a set idea of how you would simulate this, it's hard, okay? So you would first guess a kernel here, sample a Gaussian process for these guys, plug them in, run these stochastic processes forward many times, okay, sample a lot of trajectories. From them, calculate these kernels again, plug them back in, do the sampling again, do the forward runs again, and so on and so forth. It's a complicated dynamical system. Sorry, basic Monte Carlo procedure, but you can do. Okay. So before now showing you some simulations comparing the results of this to data, I also want to show you one more generalization of this. So I'm probably having like another 20 minutes ish, right? That's like, sounds right. Okay, cool. All right. So I just described you a version of this for backpropagation. So some people worry that basically this is not biologically plausible, and people have come up with other versions of training sort of layered neural networks, and they go with the names feedback alignment, direct feedback alignment, or Hebbian learning, and so on and so forth. Just to tell you, the idea here is like in backpropagation, the weights in forward and backward passes are transpose of each other. There's reasons to argue that this is a biologically implausible sort of situation. And it's called the weight transport problem. So people try to solve this by basically decoupling these weights, for example, by setting them to some just random matrices and keeping them frozen. Okay? So the point is you can do the same procedure for all of these different learning rules and get basically another sort of DMFT for it, and basically get a similar sort of stochastic process for all of these things. And here is basically comparison of these to some simulations. Okay. All right, so what's been plotted here is the following. So this is a simple, small neural network, depth 4 with 4,000 tensor activations. Some data set we made up, so it's like the whole data is at 20 points or something. And these are the simulations of the results of our DMFT, the stochastic process, the dashed lines. And the solid lines are basically the loss curves for gradient descent trained, the feedback alignment trained, and all these kinds of trained neural networks. Okay? So I want to point that these are all away from the NTK regime. If I were to plot the NTK predictions, they will be totally off. So these predictions not just hold for basically this quantity, the loss, they hold for basically more interesting things like, for example, these distributions of pre-activations. So what I'm plotting here is like, I'm collecting sort of all the pre-activations in a layer and making them into a histogram. My stochastic process basically describes that statistics. And I'm comparing them to the prediction coming from the DMFT, and for all these different learning rules, and you get a very good match. And this is basically, again, comparing the theory predictions of the kernels themselves to network training, and again, basically, you get a good match. Okay, so that's great. You can also compare DMFT predictions to sort of other approximation schemes. So this is, you know, the NTK curve that I was just talking to you about. This black line is the neural network training, and there's other kinds of approximations you could do. All of them fail. DMFT works. It's a bit cheating because we put the network in a regime where everything else should fail, but that's the point. So DMFT doesn't fail, but it will also catch everything else. And basically, again, showing, you know, other things don't work. So here's sort of one insight that you can take from this kind of theory. Here's what happens. So let's focus on this training with direct feedback alignment. In this case, basically, the feedback weights are random. Okay, so they are not tied to the forward weights. And you might imagine, how is this even possible? Because now they're not carrying gradient signals, and how can the neural network learn if they don't have good approximations or good sort of, yes, basically estimates of gradients. So here's what happens. So there are different curves, loss curves, and what you're doing in these different loss curves is you're increasing feature learning. So basically, you're making the last layer sort of smaller and smaller, allowing the network to learn faster and faster representations. And in that case, you see that the loss falls faster and faster. And why does that happen? So you can plot the following quantity. So this is the correlation between the true gradient. So if I were to backpropagate the true gradient to a particular neuron or particular layer, and the correlation between that and this gradient signal that is carried by these random projections. So in the beginning, these guys are orthogonal because these matrices are just random matrices. But as you're learning more and more features, you find that basically these sort of the features are such that they align the gradient signals to the pseudo gradient signals, and therefore basically you get a faster sort of training in small representation learning regime, basically giving a mechanism for why these sort of biologically plausible approximations to gradient descent might work. Okay. All right, so these were just some simulations to show you that this DMFT works under sort of when it works, okay? And also we can, within this formalism, we can sort of recover previous results. For example, for the two-layer networks, we can get a PD description like the previous two-layer network, two-layer DMFTs that have been derived by May and Montanari and colleagues. And also you can commit to linear sort of activation functions, and basically you can sort of recover again previous results about linear networks, all here. Okay, so what can we, okay, so good. So I just told you basically a bunch of a theory, some simulations verifying the theory works in the way it's supposed to work. And can we get some more insight from this? So there's an interesting insight, basically, that was not obvious to us from the beginning. So all these different learning rules now, within our theory, okay, you can sort of take a lazy limit of them by playing with this gamma zero parameter and making them sort of very, very small. Okay? And in that case, basically you recover that gradient descent training should converge to a basically training with a neural tangent kernel. But all these different learning rules again have kernel regimes, but they actually are described by different kernels. And they're very similar to neural tangent kernel. They're like NNGP kernels. So if you know the difference, they're like epsilon different from each other. But basically, it also shows that basically in these, you get like a different limit from them. And also you can do sort of other extensions of these methods to that I described to gradient descent, knot flow, Javan dynamics, weight decay, multiple outputs, CNNs. All these things are described in the paper appendices. Just to give you an interim summary of everything. So what I've described so far is there exists a limit, okay, in which feature learning networks exist. The training dynamics of this network can be described by a stochastic process. But the question that you should be asking me, is this the right theory for practice? So when you're doing, let's say, ResNet or ImageNet, is this actually the right theory? Okay. So ideally, I would like to plot you a training curve with ResNet or something, or ImageNet, and on top, plot this DMFT curve and show that they match. It turns out that simulating the DMFT is computationally very expensive, so I won't be able to do this, okay? Also, you might be there are some assumptions in deriving this theory that goes into it that has to do with depth and data set size. You assume, for example, that the data set size is smaller than the width and so on and so forth, and this may not be realistic, okay? So these two things might give you doubt, basically, that this theory may not be the right theory for practice. So what I want to do is basically, I want to show you some simulations and things that we've done to test these ideas. And the other thing you might ask is if there's any practical benefit of this approach, and that was basically the first thing I've shown you, this hyperparameter transfer, and I want to tell you a bit about that too. Okay, all right, so since I cannot plot basically a theory curve, which is computationally too expensive, students are working on this, hopefully we'll solve it at some point, we can actually do test another sort of prediction that there's consistency. Perhaps networks that are behaving, given good test performance, are near an infinite width limit. And the way that you would test this is by basically, by scaling up these networks and see, if they just behave similarly. So we did these experiments and we found some surprising results. So this is a ResNet trained on C5M, online training batch size. So what we're plotting here is basically a test error as a function of training steps, as a function of width. So as width are increasing, you're seeing a pretty sort of similar learning curves. Okay? And the way this is done is the data is presented in the same order, so it's a comparable plot. So this is just looking at the just global metric, test error. So here's a more fine metric. So this is the logit value of just one of the logits at a particular test point. So you give at any point in training the same input and look at the logit and plot that, okay? And again, across different widths, you do see like pretty sort of similar behavior, right? I mean, as the width is increasing, you get like, again, some consistent kind of a behavior. Even all these like, jumps and sort of discontinuous looking things are repeated across different data sets. Here's even a more, I think, interesting comparison. So here's what in the next slide, okay. So what we're gonna compare is basically histograms. Histograms across these layers, okay. The thing that I should say should concentrate for, again, pre-activation histograms at initialization and after training for networks with different widths. So this is a log scale. So in initialization, this should be a Gaussian. So therefore, it should look like an inverse parabola. It does, and the Gaussian sort of, the simulations also hold. And finally, after training, so this is the best up Gaussian fit, but basically, you get some non-Gaussian statistics, and still, you see consistency. And so this one is another. It's coming with a delay. So you can also look at, for example, layer similarity matrices. This is the last layer similarity matrices dot product. So these are images by images. Okay. Again, across different sort of widths, you see pretty sort of consistent behavior. And we have tons of more experiments sort of in the paper that's coming. But basically, it's telling me that even at scales, at least for these kinds of data sets that we're looking at, that you practically operate with, networks are already behaving in some kind of a near and infinite width limit. Now, whether that limit is the one that you've described or not is a question that needs to be answered, but that's consistency. And the second part that I want to address is, yes, you developed all this theory, but is there any practical benefit? What's it good for? Okay, and that brings me to the title of the talk about this hyperparameter transfer. Okay, and so I just showed you this idea. Okay. Okay, so this was the first slide I showed you, the idea that like, you can transfer parameters across different depths and widths. Now, the reason this works is now I'm going to argue why this works, I'm going to take an infinite width limit, infinite depth limit on top of the infinite width limit. And basically, it turns out there are multiple consistent ways to do this. And just to describe you what that is, let's look at basically the simplest residual network we can think about. Okay, so you have the skip connections and the residual branch and so on and so forth. So basically, there are different ways you can initialize sort of the variances of these weights and some factor that you could put in front of this branch over here, and so on and so forth. And the standard way you would choose these weights. The output scale, the learning rate, and weight variance, let's say, in PyTorch is given here. The particular limit that I just described until now, the mean field limit, is basically here, okay? The point with this limit is it turns out if you stick to this limit and keep stacking these kinds of networks, as you go deeper and deeper, basically they'll just blow up. So what you need to do is you need to plug in, a factor of square root of L in this scaling over here, which is going to give you consistent scaling. Now, I should say that we're not the first ones to put this factor here and at initialization to sort of figure out the conditions for well-behaved, I'll say. But I mean, we're the ones who's going to be describing the dynamics of this with the scaling. All right, so we're going to do this little modification. And basically, if you do this, here's what happens. Okay, so here I'm plotting the same plot that I showed you for basically these three different kinds of initializations. Okay, so you see a lot of missing points here. What happened for these missing points is these kinds of initializations did not converge; they just blew up. But basically, with this kind of initialization that we're defending here, you get like not just only a consistent behavior in the sense that things are well behaved. You also get like basically this hyperparameter transfer curve, meaning that like the optimal guy here is the same across all these variables. And this is a more general behavior. So this is not just a ResNet issue. So you can also simulate the same things on vision transformers and basically get similar behavior. So this is like you can do a similar kind of scaling, and you basically find that in these vision transformers, using layer norm or without layer norm, and so on and so forth, cosine annealing, and so on and so forth, in different data sets, you basically all get like these hyperparameter transfer working. All right, so these are experiments, and the reason basically all this works is, again, because there's a limiting process. In the case of both depth and width going to infinity, so here's that limiting process written in a sort of more summarized form, I'll say. Okay. So what we need to do now is introduce another continuous index. This index is basically sort of counts the depth, right? So it goes from 0 to 1, 1 being the last layer, 0 being the initial layer. Okay, so and this H is the pre-activation now. It's again a stochastic process. It has a depth index, a data index, and a training time index. It's given by basically input plus a Brownian motion. So that's a Brownian motion over here, and plus some deterministic operator, which is like a complicated thing, but I'm not going to go into the details of it. All right. So this particular limit itself, I'm just looking at it, it's hard to say something. You can solve this for linear cases and so on and so forth. But just the fact that there exists a limit tells us that there's some consistent behavior, and we know how to scale things, how to scale the learning rates across different depths and widths, and therefore we can do this hyperparameter transfer kind of graphs. Okay, and then just to say about like what is it actually that's causing this hyperparameter transfer? Okay, so here's a conjecture. What you need to have is a well-defined limit. Things go to infinity in a sort of a well-behaved way. And you want sort of these networks to be in a feature learning regime, which means basically asymptotically these kernels and features should be moving independent of with n and depth L. And you also want to be in a regime where you have sort of, you're close to that sort of limit, meaning that, finite size approximation errors are small. So therefore the scalings that you do are more or less optimal up to factors of, or corrections of 1 over n and 1 over L. All right, so I'm out of time. With that, I just want to finish, and I want to thank people in my group and also acknowledge my funding sources. And these are the people whose work I've showed in this particular talk. And my group members are all here. Thank you very much, and I'm happy to take questions.
Thanks so much for the great talk. Any questions?
Not enough to say, oh, I can take this wider net and use the same for the smaller net. You need to pay attention to how you scale the weight
Yeah.
Are there other things, I didn't quite understand, are there other things besides how you scale this that you need to also do, or is that?
Yeah, thank you for that question. I mean, let's think about it this way. So suppose I gave you a network. I don't tell you how I initialize it or something, or just there's a network. And then you want to build a network that's twice its width and twice its depth in a way. So if you knew how to scale this, meaning that, if you're now, let's say, let's fix this aspect ratio. I'm going to multiply it by width and depth. I'm going to just keep increasing along that aspect ratio. It's going to go to a particular limit, right? So if I know basically how to scale things in a way that I'm going to stay on that limit and that I'm close to the limit, I know that I'm going to get more or less consistent behavior. So that's all I'm saying, right? So yeah, so you need to have both things. So first, you need to know how to scale things so you go to a consistent limit. And second, you need to be somehow within the basin of attraction, let's say, of that limit. So therefore, like, yeah. Yeah, you scale how you initialize. Let's go back all the way here. Because that's the only thing, by initialize, I mean, oops, there's some time lag between this and this. Okay, sorry. Yeah, it's not just the weights, but you also, for example, learning rate is a part of this. You might want to scale how the learning rate goes, right? Because that's also a part of the thing. So every hyperparameter here might have a scaling with it, associated with it. Large learning rate phenomena. So that's a good question. I might even have a slide for this. Let's see. So large learning rate actually doesn't kick you necessarily out of this regime. Okay, I don't have the plot here. But so for example, there are large learning rate phenomena like the catapult mechanism and so on and so forth. So you can have those kinds of sort of dynamic behaviors in this regime too. So that doesn't necessarily mean that you're out of the mean field regime that I'm describing to you. We have a paper in NeurIPS this coming. It has exactly that figure in it, so I can point to you if you looked at it. Yeah. Carl, there's I think another question here.
I can just ask.
Sure.
So are there studies on this like consistent limits do we converge to like the solution that's nice, some bias or that generalized?
Sorry, I missed the question.
Sorry, do we have, hello. Do we have studies? So in your presentations, you have shown that we can consistently converge to these nice trajectories in the limits. So how do we know that these are the right thing to converge to? Do they lead to generalizable solutions at the end, or is there some implicit bias that you can show for these mean field trajectories?
Implicit bias. Okay, sure. I mean, so you're asking about, okay, so you worked out this dynamics. Can you say something about like whether these networks, what they learn? Yeah, sure. I mean, so it's true. So this has been a challenge. So the dynamics that you recovered is pretty sort of, it's not like the NTK limit where things are solvable to a larger degree. They look complicated. So looking into them and trying to get insight about like things like generalization have been problematic. So we haven't been able to like come up with a clear sort of way to do this. So, but since you asked, I mean, you could, so one approach is basically you could sort of, since you know the full dynamics, you could try looking at its fixed points and try to characterize basically if the fixed points from the fixed point would be what you converge to and see something from there. So we haven't really pursued that direction as much. We should, because I was more worried about whether verifying this actually is the right limit to study. So that's why we took a detour to run all these simulations. And So I have mixed feelings about this. So I'm not exactly sure this is the right limit for practice, but if I'm convinced, certainly that would be the thing to do.
Any more questions? Okay, let's thank the speaker again.
Thank you very much. Thanks, everyone.
So you're letting them in and letting them share? Speaker of the video. Hmm? It looks okay on the screen. Good to go? Okay, so our next talk is a virtual talk from Yu-Chen Lee from CMU, and they're going to tell us about uninterpretability of transformers.
Hi, can you hear me?
Yeah, we can hear you now.
Okay, cool, thanks. Hi, I'm Yu Chen, and today I'll be talking about transformers are uninterpretable with myopic methods. So this paper is led by Kaiyue Wen, an undergrad student at Tsinghua University. However, it's currently 3:30 a.m. for him, so he can't speak right now. So I'll be presenting instead. And this is in collaboration also with Bin and Andre at Carnegie Mellon. So we know transformers have been applied to a lot of domains in the real world, including natural and programming languages, computer vision, and also scientific domains. However, to reliably apply transformers in practice, we sometimes need some level of interpretability. For example, researchers often look at the attention patterns on images, and also for natural language. So prior works have shown that based on the attention patterns of transformers trained on natural language, they can extract some syntactic trees that align well with human-defined notions of grammars. However, these approaches can sometimes be challenging. For example, sometimes the interpretations obtained through this type of approaches could be misleading, and they often lack formal understanding. So therefore, the question we ask is, can we reliably interpret the algorithm implemented by transformer by looking at individual components? So here, individual could mean single attention patterns or some single weight components. We call these methods that only look at individual components, those myopic methods. Our answer is no in general. So transformers may not be interpretable by inspecting these individual parts. And our approach involves theory and experiments conducted on this synthetic benchmark called DIKE. As a background, what is the DIKE language? So this is also called the language of balanced parentheses. For example, so here's an example of valid DIKE language, and this is an example of invalid DIKE. This is because, for example, a round closing bracket cannot appear immediately after an opening square bracket. So the depth of a bracket is defined as the number of unclosed opening brackets before that. The task of this DIKE benchmark is to predict the type and openness of the next bracket. And this is most naturally processed by maintaining a stack data structure. For example, when we see this sequence of brackets, whenever we see an opening bracket, we push them onto the stack. And when we see a closing bracket, we try to see whether the top of the stack is the corresponding opening bracket. And if so, then we pop off the current stack top to match the newly observed closing bracket. So similarly, we can pop off the remaining opening brackets on the stack. So now the question is, how do transformers process this type of DIKE languages? Do transformers also require some motion of stacks? So in fact, this is conjectured by prior works. So they think transformers learn DIKE by learning a highly stack-like attention patterns. And the prediction can be done by focusing on the last unclosed bracket. For example, this is the stack-like attention pattern constructed by Yao et al. So for example, when you see, try to predict the next sequence after the current position, you observe that you pay attention to this opening bracket, and therefore you predict the corresponding closing bracket right after. And here you observe the round opening bracket, and therefore you observe, you predict the round closing bracket immediately after. So our results show that while the above solution is valid and contains intuitive interpretations, we show, in fact, transformers can learn diverse attention patterns on stack, which are not restricted to stack-like patterns, but a much larger set of possible attention patterns that can achieve near perfect accuracy. So this happens in practice as well. For example, we can show transformers trained on DIKE can learn very diverse attention patterns, not restricted to stack-like patterns. And as a background, we can introduced a transformer architecture by looking at each layer. So this involves a lot of moving parts, but for now, you can just focus on the part involving this sigma in the equation, in the formula. So this sigma is called column-wise softmax operation. This transforms each column of the input matrix to a vector whose entries are positive and sum up to 1. So the sigma output, basically the output of the softmax operation, is called the attention pattern. And it is a matrix. The attention pattern is a matrix of dimensionality sequence length by sequence length. And visualizations of this attention pattern can be either this stack-like pattern in Yao et al. Or a more diverse set of attention patterns in our work. So the full transformer model is the composition of the each layer followed by a projection head at the end. Okay, so given the transformer architecture, what training objective do we use? How do we train this model? So we use the next token prediction objective. For example, when you see this prefix, the transformer may predict this following set of possible next tokens with the corresponding probabilities. Suppose in the training data, the actual next token following the prefix is this round closing bracket. And then you will take this label and combine with the model prediction to calculate the loss at the current position. For our theory, we use squared loss. And for our experiments, we used cross entropy loss, which is standard in practice. And the final training objective is to sum up or average this position-wise loss. An optimal transformer in this setting basically means minimizing this training objective. So we are going to present some properties of transformers that minimize this training objective. And we'll show that for this type of transformers, the attention patterns are generally uninterpretable. So as a prerequisite, we introduced the notion of minimal first layer, meaning that the output of the first layer only depends on bracket type and depth. So for example, I'll give some examples of what this means. So when we see a square opening bracket, the first layer will contain the information that this is the bracket type with depth 1. When we see a closing bracket, will decrement the depth. So similarly, opening bracket depth 1 again, another opening bracket and depth incremented again. So we'll show that. Okay, so maybe before looking at the actual theorem, so why do we care about this type of first layer? In fact, this is inspired by the construction in earlier works that claim if the first layer implements this function, then the second layer can process stack by learning some stack-like attention pattern. So our work basically shows the stack-like attention pattern is not necessary even when we restrict the first layer to learn exactly the same function. So in this sense, this minimal first layer condition makes our result even stronger by removing the flexibility for the first layer to implement arbitrary other functions. All right, so our theorem looks like the following. So any two-layer transformer with the above type of minimal first layer need to satisfy the following balanced condition to be optimal on the previously introduced training objective on DAG. So the balanced condition looks like this. I'll give more intuitions later. So this is both sufficient and necessary under some conditions. So to give more intuition, note that, for example, the parts involving E, so they are the outputs of the first layer under the minimal first layer condition. And this opening bracket at depth D and closing brackets at depth D minus 1, they are sort of the matching brackets. And so the intuition is, so they should cancel out each other in terms of their influence on predicting any other bracket types at any other depth. So to put this in words, the intuition is the embeddings for matching pairs of brackets should cancel out. And our proof connects to pumping lemma for regular languages. We have seen this balanced condition, and to give more remarks, so this balanced condition does not imply interpretability. For example, as a corollary, we prove that Dike can be solved by uniform attention pattern, which does not reflect the task structure at all. And secondly, we can extend this to an approximate balanced condition from finite samples. And the intuition is that if the perfect balance condition is optimal, then the deviation from perfect balance needs to be bounded in order for the transformer to achieve low enough training loss. All right, so empirically, we can verify our claim by observing that balance condition is in fact a very weak constraint on attention patterns. For example, we can see that for transformers that achieve near perfect accuracy on a very diverse set of attention patterns can be observed, and they are often not stack-like. So we also have some results that show balanced condition can improve length generalization. For example, our theory suggests that the attention should be balanced, and we can correspondingly design some contrastic objective that intervene on the attention pattern. So the more balanced condition leads to better generalization. So we have some results that show this contrastive intervention, which makes the balance violation to be smaller, also leads to better length generalization on Dike. So in addition to attention patterns, we also show that single weight matrices are generally interpretable as well. So for example, our theory involves the concept of non-structural pruning, which for some weight matrices, it'll zero out some of its entries. So the flavor of our result is consider any given transformer T and a larger transformer TL with random weights. Then the smaller transformer T can be approximated by the larger transformer TL with some non-structural pruning with high probability. So as a corollary, this basically implies the uninterpretability of single weight matrices. This is because as a corollary, for any single component of TL, you can design two different pruning approaches that share the same component after pruning, but the overall lead to different functions. So basically, you can have different smaller transformers, T1 and T2. They share the same weight component after pruning, but T1 and T2 implement different functions. So by looking at this single weight component, you cannot know what the function that the transformer is implementing, whether it is T1 or T2. So the proof involves repeated applications of certain proofs of like some version of lottery ticket hypothesis, and each layer can be approximated by pruning 4 random layers. All right, as a summary, we claim transformers are not interpretable via myopic methods in general, and we use Dike as a test bed, which is a fully controllable sandbox, and you can prove theories on that. This uninterpretable includes both attention patterns and also single weight matrices. Yeah, thank you. And please let me know if you have any questions. So here's a QR code to our paper.
Thank you very much. Any questions from the audience? We especially encourage questions from students. Okay, so thank you again. We'll move on to our next talk.
Okay, hello everyone. Can you hear me?
Just 1 second, Inbal. Okay, so for our last talk of the session, we have Inbar Sarusi from Tel Aviv University telling us about speed limit for deep learning.
Okay, hi everyone. So first I want to thank the organizer for this great conference and the opportunity to speak. So today I'm going to talk about the joint work with Alex, Moritz, and Zohar, which was great to work with. And what we discussed was about speed limit for deep learning, and I will present our approach and what do I mean by speed limit. So let me start. So the main question that we keep asking is like, can we find some optimal training time for deep learning? We all know that deep learning is extremely costly, and we know that the amount of parameters is growing every year. Just last talk was about transformers, and transformer contains sometimes billions of parameters. And just to get some statistics, just one training run of an NLP model can cost in the order of $1 million for 1.5 billion parameters. So what we will do today is I will phrase the problem of learning as an optimal transport problem. And then I will use ideas from stochastic thermodynamics, which is an emerging field in statistical physics, and which actually describes systems that are far from equilibrium. We think about the learning process as far from equilibrium. And so the idea is that if you have some knowledge about the equilibrium, you want to understand something about non-equilibrium behavior. And at the end, what I will do is I will also define some notion of efficiency of deep neural network. Okay, so what will be our setup? So what we work with the Langevin algorithm, where essentially it's a gradient flow with noise, and eta here will be my learning rate, and this is the gradient of my loss, and I can also have some weight decay, and this is essentially I'm adding some noise to each gradient. And so what we will take is that we have some distribution for our parameters, and the initial distribution is Gaussian. And I'm writing here as a form of a Gibbs measure, which is something that is usually done in statistical physics. So Z0 is essentially a normalization factor, and it's called the partition function. And the final distribution will be essentially the equilibrium distribution of this process, which essentially is the again related to the loss function divided by the final partition function. All right, and next object that I want to define is something that is called entropy production, which measure essentially irreversibility of my stochastic process. So what does that mean? Is essentially the tendency of the process to evolve in a particular direction in time. So how would you define that in a mathematical form? So the way it is defined in a mathematical form is essentially thinking about, suppose that I'm starting from some initial distribution and my process ends at another initial distribution. So now I'm thinking about this joint distribution of that process, of that set of parameters. Now what happens if I flip? I suppose I start with the final distribution and I end up with the initial distribution. So how these joint distributions are different from one another. And it turned out that actually, so this essentially is, you can define it in terms of the Kubler-Leibert arrangement between these two distributions. And this idea is known in this field of stochastic thermodynamics as the second law of stochastic thermodynamics. So it's always also positive. And how is it connected to what we want to study? So in the context of learning process, we actually can calculate this object given this initial and final distribution that I defined. So the final formula that we find is the following. So in particular, ZT and Z0 was my normalization factor, the partition function, and the log of that has this meaning of the free energy at final state, which is essentially related to the maximum work that I could do at the final state, minus the free energy at the initial state, and plus the expected initial loss, which is essentially the internal energy of the system. All right, so that's what is important from this object is that I can essentially calculate that just by knowing the initial and final distribution of my process. And I promised you that I will define the learning process as an optimal transport. So how you would define this distance between initial and final distribution also in weight space? So using ideas from optimal transport, what you will do is you define it via the Wasserstein distance, which essentially will define is the optimal plane in which you can transfer you can transfer the information from this initial distribution to the final distribution. And essentially what you're minimizing overall joint distribution, that their marginal are this initial distribution and final distribution. And a nice properties of this Wasserstein distance is that it's invariant into change scaling time, which we think about change scaling time in the way I define the Langevin process as essentially increasing or decreasing of the learning rate. So what the striking phenomena here is that these two objects are connected. So essentially the entropy production and the Wasserstein distance, essentially Wasserstein distance will be the optimal transport plan, and it turned out that the entropy production is a plan. And so in particular, you can show that gives you essentially a bound on the time, on the training time. And so this is kind of remarkable because now if you plug in our formula for the entropy production, now we can define the bound on the time essentially just by knowing the initial and final distribution of your process. And more implication of this idea is that now thinking, I'm just want to say that one caveat on this is that this is a lower bound. So meaning that if you increase the learning rate, that will mean that you will increase also the entropy production, and that it turn out that it will. So then because the Wasserstein distance is invariant to the learning rate, then essentially the bound will just decrease. But actually, it doesn't take into account the fact that your process can explode, but it's still very interesting bound to look at. For example, what happened in the noiseless case. So in the noiseless case, when I just thinking about a process like a gradient flow, for example, the neural tangent kernel dynamics is an example of that. So actually, the entropy production turned out to be even more simpler object to understand. It's just a difference in the loss between the initial parameters and the final parameters. And so that also tells you that there's actually this limit. There is no like there is no any other better loss. So you just need to know the initial and final loss in order to get the entropy production. And what I will show later is that it's also tightly connected to the neural tangent kernel spectrum, and we'll show how we can also think about ideas of that for future work, how to do some spectral engineering of that. But more importantly, now that at this beta goes to infinity limit, the noiseless case, I can actually compute this bound numerically even. I can, because it's just a distance, Wasserstein distance turn out to be just a distance in the Euclidean distance between the weights. And the entropy production is just a difference between the loss, so I can really compute this object. And so this is what we did. So we computed this object for. So we trained 6 meter 5 CNN on CFAR10 with 5,000 samples, And so we saw that we indeed learned something. We looked at the accuracy. And then when we plotted essentially this time bound that we found, and we plotted, we defined this inefficiency ratio, which was the training time that we have divided by the time bound. So we saw that it has like a large increase at the beginning, and then it saturates. But this large increase means that the inefficiency ratio is essentially about 30. So our bound is really off. So that was so then we were okay. So that means that somehow neural networks are not efficient. Okay, we were expecting that, but is it indeed the case? How can we understand that more theoretically? So we turn out to the regime that we kind of know what to do, which is the infinite width regime. So in this case, I'm really taking neural tangent kernel dynamics. And so in that case, you know that the kernels is essentially a constant due to a central limit theorem. And again, what I want to do now is to just calculate my bound. So so the entropy production is just the difference in the loss. And the inefficiency ratio is, as I said, is just the difference in the loss divided by the Euclidean distance between a parameter at initialization and the end. And so I can now calculate the distance between this Euclidean distance, which it turns out to be just dependent on the residue at the beginning, which is the label minus the output of my network at initialization, and times the kernels. And if you take, for example, a residue that behaves like a white noise, then essentially this object will depend only on the spectrum of that kernel. And now I will use ideas that actually Cengiz already presented in his talk, which is he motivated that already. Use this for the NTK spectrum. I will consider a power of spectrum, and actually we also see that numerically if you plot the spectrum of the NTK. And so I will also, under additional assumption, which is the residuals are also behaving like a power law, which is also, as I will show, can be justified numerically. So under these two assumptions, what we can find is that there is two regimes for this time bound. So in particular, if the residuals are extremely concentrated on a few eigenmodes, then what we found is that the time bound is really not, it's really off, and we are not efficient. But if the residual become more and more uniform, then we are inefficient. Then we are efficient. And so if you, for example, take the case of the white noise, then the residual this delta is 0. Then the neural network will be efficient for a power law that is greater than 1. Okay, so can we see something like that in practice? So what we did here is, we took the experiment and we tried to plot what happened to the residual. And indeed, what we can see, so in blue, you can see the residual at the initialization. And so what you see is that they're really concentrated. So here we projected them on the eigenmodes of the NTK kernel. And you can see that they are indeed concentrated on a few, on this zero, close to the 0 mode eigenvalues, and later they become like a little bit more stretched. And so what we notice that if you after a few epochs and you look at the residuals, you actually see that they become more and more uniform after a few epochs. So then we said, okay, let's plot what happened to the time bound after a few epochs. And it turned out that after this warm, what we call this warm start, you indeed become efficient, which kind of was predicted by our theory, which was for the infinite width, but here you see it also for finite width and one network. And so we relate this inefficiency at the beginning to this fast entropy burn that happens at initializations. Okay, and here I'm going, so that was a theory for what happens at the infinite width limit. So what can we say about beyond this lazy training regime? I'm referring to this adaptive kernel approach, which you also already heard, like a very nice talk about that by Cengiz. And there is also a similar approach to that. We also have an approach that related to this idea. And so the idea is that essentially you that at the end of the wood. So what we think about it is that what at the end of the process you can think about it as also the output of the network behave like a kind of a Gaussian process, and that's kind of related to what I want to know is I want to know the initial distribution and my final distribution. So the initial distribution of your process, you know that it behaves like a Gaussian process, that we already know from this NNGP result. But what we can say is that also at the final distribution of the process can also be approximated by a Gaussian process. So using this type of result, we can also try to calculate at the bound. And essentially, you can also provide what will be the output of the network. And what is important that you have explicit formula for this that really allow you to calculate the bound. Okay, and so that's kind of like for future work how we can do this calculation of the bound for finite width. And so to summarize what I've shown you, so I've shown you that we have this thermodynamic speed limit that we introduced it in terms of deep learning term. And we can provide an analytical expression for this speed limit. I introduced the NTK result, but we also have in the paper linear regression in high dimension using ideas from random matrix theory. And what I've shown is that this NTK, which behave like a parallel spectrum, and if you have like uniform residual, then you're optimal. And if the residual are really concentrated on a few eigenvalues, then you're inefficient. And that kind of extend also we see it also numerically. So essentially that kind of tell you that for future work to kind of understand this inefficiency that happens at the beginning. And so what we kind of, our input for that is that indeed you have this entropy burn at the beginning and that the residual become more and more uniform. Okay, and this is a link to our paper. And with that, let me thank you for your attention.
Thank you, Inbal. Any questions from the audience? Okay, so I'd like to thank the three speakers of the session, and we have a coffee break now till 3:30, when our last session starts.
All right, welcome back, everyone. Thank you very much. So we'll be starting our next session of contributed talks. It's my pleasure to introduce Florentine Guth, who's with NYU in the Flatiron Institute, and he'll be telling us about the rainbow model of deep networks. So please take it away.
So there are a lot of open questions in deep learning, right? That's what makes it so interesting to work on this. There is one question I'm particularly interested in, is what has my network learned? Okay, I train a network, the weights evolve during training, and then in the end I get a network that reaches a good performance on a test set. So there's information that's encoded in the weights in some way. The training data, information about the training data is encoded in the weights, and I want to understand how it's encoded. So this is the question I'm going to focus on today. But what makes this question very difficult is that every time we train a network, we get a different set of weights because of the random initialization. So we get different weights, but every time the performance is the same, right? We don't even think about it. We don't think of training as getting a random network. We think of it as we just get a network that works. So that means that we don't have just one network, we actually have an ensemble of networks that correspond to all the possible initialization you could use. And so the question is, what is random in these weights? And perhaps more interestingly, what is stable? Are there things that are reliably learned no matter what the initialization is? Okay, so if I make this even more precise, the mathematical question is, what is the distribution of trained network weights? Okay, there's a probability distribution, and I would like to make a model of it. So like all models, it's going to be wrong. It's going to be overly simplistic, but I hope that I can convince you that it's useful. So our approach will be to first, very empirical, let's train two networks, same architecture, same data set, but different random initialization, and compare them. Try to see if we see things that are similar in the two networks. So let's start simple with the weights of the first layer. So I have a bunch of neurons for the first network and a bunch of neurons for the second network. Each of these neurons is described by a vector, a weight vector, that I'm plotting here in the plane if I have just two input features. And I have blue neurons and purple neurons that's coming from the two networks. So you could hope perhaps that you can match neurons one-to-one between the two networks. There are some features that are reliably learned, but in fact, this is not what we observe. It seems more kind of random, but actually there is some similarity here, and it's revealed if you train networks that have larger and larger number of neurons, so you increase the width, and you start to see correspondence not at the individual level, but at the global level. So the point of view that I'm going to take here is that the empirical measures of the weight converges towards something that is deterministic, a deterministic distribution that does not depend on the random initialization. This is a so-called mean field picture that has been proven to be, that happens in one hidden layer networks. So my first message here is that we're going to think of neurons as random samples from some fixed distribution, which is also called random features in the kernel literature. Okay, let's move on deeper in the network and now think about the first layer activations. So the output of my first layer. So I'm going to have random feature activations, phi of x. This is the output for the first layer on input x. And up to a scaling factor, this is going to be a pointwise nonlinearity and inner products with the neuron weights, wi. And for the sake of the argument, let's assume that the wi's, the weights of my neurons, are IID samples from this distribution pi. Now, the interesting object to look at is the kernel that's defined by this representation. So you take two different inputs, x and x prime, you pass them through the network, and you look at whether the representations are similar or not. So you compute this inner product, and because of the normalization, you get an average over the neurons. And now if you have lots of neurons, if the number of neurons goes to infinity, this converges toward deterministic limit, which no longer depends on the random initialization. Okay, so it's the same for both networks. So what that actually means is that if I look at the representation, so now what I'm plotting is for every input, I have a vector, that's the activations of the network on that input. I'm plotting that in a space. here that's spanned by the neurons in the first layer. And what this means that this inner product is deterministic is that the distances and the angles between my representations are fixed. Okay, so they are the same in the blue network and in the purple network. So the only degree of freedom that I have, the only transformations that preserve the distances and the angles are orthogonal transformations. Okay, so what this means is that activations are approximately equal up to rotations, and this becomes equal in the infinite width limit. So another way to think about this is that they correspond to a deterministic representation, but that's been expressed in a random basis. Okay, this is how I want to think about networks. They're actually something deterministic, is just we see things in a random basis because the random sampling of the weights of the first layer. Okay, let's move on deeper again in the network and now think about the weights of the second layer. And what I was just telling you about has a very important implication, is that for neurons to do the same things in the two networks means that they actually have different weights. So computing the same function will require having different weights because things are expressed in different bases. So here are my two representations. These are the outputs of the first layer. Now I'm going to think of them as the input to the second layer. And these arrows here are the weights of the neurons in the second layer. So they're going to compute inner products between the representation and the weight vector. And for the sake of the example, let's assume that this second layer is projecting its input on its first principal component. So in the first network, the first principal component is closer to neuron 2. In the second network is closer to neuron 1. So if you compare the weights directly, you would conclude that they are different. But in fact, they are computing the same thing. They are computing the inner product, the projection on the first principal component. Okay, so when we compare weights in the second layer, we have to take this into account. So more precisely, what do I mean? We can compute an alignment A, which is going to be an orthogonal transform that aligns one network to the other. This is what's called Procruste's analysis, if you've heard this before. This is essentially linear regression, but you restrict the weights to be orthogonal. Okay, because you don't need to do stretching, you know that the distances are preserved, so you just need to align things with an orthogonal transform. So this is an optimization problem that has a closed form solution, essentially amounts to computing a singular value decomposition. And you get orthogonal transform A such that A blue phi of x is close to purple phi of x. And now you can use this A to compare weights from the two networks, because this neuron Wi in the blue network, it has an equivalent in the purple network that is not Wi, but AWI. If we want the two neurons to compute the same function, they have to be rotated to similar to the activations, right? So my message here, that neurons are random samples from some fixed distribution. This is what I was telling you about 2 slides ago, but there's a twist for deeper layers, is that this fixed distribution is expressed in the random basis of its input activations. Again, this is very important, and this is why when we look at the weights of networks, we don't really see the things that are meaningful, because things are expressed in a random basis that depends on the random initialization. Okay, so I've done this up to the second layer, but now you can iterate the arguments. Right? If you assume this for the weights of the second layer, you're going to find that the activations at the end of the second layer are also going to be rotated copies of one another, and you can iterate the argument. Okay, so does this actually happen in practice? Let's verify. So let's start by comparing activations. So here I'm training a pair of ResNet 18 and ImageNet from different initialization, and I'm measuring the distance between the activations after this alignment procedure. Okay, and so I'm going to have a distance for every layer, and the color is the layer, and I'm looking at the distance as a function of the width, because we know that as we make the networks wider, this is when the law of large number kicks in and things start to concentrate. And we indeed see that for all the layers, except maybe the last one, this error seems to decay. So it seems like there is indeed convergence on the activations. Now let's talk about the weights. So I want to compare the weights using, again, this alignment procedure. That's very important. And I think of them as distributions. So I'm going to compute moments of these distributions, in particular the covariance. So here I'm looking at the spectrum of the covariance of the weights after training. There are actually 2 lines here that are overlapping. So the 2 networks have exactly the same spectrum for the covariance. we can go a bit further and we can compare the eigenvectors. So here in the x-axis, these are the rank for the first network, the rank of the eigenvectors for the first network. Y-axis, the rank of the eigenvectors for the second network, and I'm computing the inner products between all pairs. And what this means here is that we have very high correlation between eigenvectors at low rank. Okay, so these two networks are actually learning the same weights once you've aligned them together. This part seems to be random, and what we see on the spectrum is that the eigenvalues have not really moved from initialization, so perhaps this is just a residue of the initialization. This is actually not important. And a way to check this is just to do PCA on the weights, and you project all this part to 0, and you see that you preserve the accuracy. So you only actually need here about 40 dimensions to reach the full accuracy. So this part is indeed random and does not really matter. Okay, so the summary up to this point is that basically when you look at two networks, every layer is expressed in a random basis. It's rotated randomly. So if you compare them directly, you don't see any similarity. But when you align them, you see similarity at every layer on both the activations and the weights. Okay, so make things even more precise, we can think in the infinite width limit, there is a unique deterministic network because everything is the same. It no longer depends on the initialization. And finite width network can be seen as a random feature discretization of this infinite network. And now this is how I'm going to make my model of the probability distribution of the weights. So the model is described by distributions for the weights at every layer. And I'm also going to need some representations, phi L infinity, that corresponds to the representations if you had an infinite number of neurons from that distribution. Okay, this is my deterministic infinite width limit. And then I'm going to discretize it in an iterative sampling procedure. So assume that I've defined the activations up to layer L. How do I define the weights for the next layer? So this is my representation for layer L. This is my sort of infinite dimensional representation that corresponds to all the neurons you could have. So what I do is I compute the alignment between these two. Okay, sorry, there's a bit of delay. So I compute the alignment, and then I will sample random features from this distribution pi L that lives in that space, in that deterministic space. And now I'm going to project back these random features to my initial, to my finite width network. Okay, this is how I generate weights on my network. I draw them from some distribution, but then I need to align them to the particular activations that I have. And the theorem that underlies this construction and tells you that it's consistent, is that if you follow this procedure, you would see that the activations of this random finite width network indeed converge towards this deterministic finite width, deterministic infinite width limit when you increase the width, and it's a polynomial convergence in the width. You don't need an exponential number of neurons in the dimension, which is a bit surprising. All right, so let's make this model even simpler to actually use it in experiments and assume that the distributions are Gaussian. So now I just need covariances for each layer. So for the first layer, I'm going to sample weights from a Gaussian with some covariance. But for the second layer, this alignment procedure is actually going to rotate the covariance C2 to make it dependent on C1. So every layer has random features from Gaussian distribution, but they're not independent because A1 depends on W1. Okay, this is what allows you to chain different random features together. Okay, and so the picture that comes out of this is that every layer is described by a covariance. So we call this the rainbow network because we don't use white noise. White noise, when you have a covariance identity, we use colored noise because each layer has a covariance and the covariance gives the color. And these covariances are low rank. So each layer actually computes a low dimensional projection of your input. The network only cares about a few directions. And then they are expanding again using random features. And so you see that the dimensionality in the network is a sequence of compression and expansion, which actually makes sense. If there was only expansions or only contraction, things would be a bit, they would collapse. All right, so let's evaluate this model. So what I'm going to do is I'm going to train a scattering network. So it's a kind of CNN that has fixed spatial filters. I'm not going to learn them. I'm only going to learn weights that apply along channels, so one by one or pointwise convolutions. And the reason why I'm using this model is that this network is that the Gaussian model is a bit too simplistic to cover all networks. But if you apply the Gaussian model only on these channel weights and not on the spatial filters, we can actually make it work. So I train a network, I extract channel covariances at each layer, and then I'm using this as a generative model for new weights. So I can sample new weights from Gaussian distribution with the same aligned covariances. And then I can evaluate the accuracy on the test set without any training. And this is what we get. So the answer takes a little bit to appear. The answer depends on the width. Again, this is a model that works well for wide networks. And so the accuracy of the trained network is 92% on CIFAR10. And if you just sample weights from Gaussian distribution like this, and without any training, you go to 85%, which is still pretty high. If you train just the classifier, just the last layer, you're able to recover most of what you lost. So most of the information from the weights is actually encoded is these covariances. All right, and one last thing you can see with this model is we can look a little bit at the training dynamics. So here, what we do is we train the network, we save checkpoints along the way, we compute the covariance of the weights at the final time, and then we rewind the training movie, we watch it again, looking at things in the basis of the weight covariance. Okay, so this is PCA on the weights, but using the PCA basis at the end of training. So here we're visualizing the spectrum of these covariances. So we know that initialization, we start from identity, so something that is equal to 1. And we see that as training progresses, so the color corresponds to training time, the spectrum is amplified and it's sequential. It's the first principal component that is learned first. Okay, observations have already been made in linear networks. So our picture is that the neurons live on the sphere initialization, and the sphere is stretched, it's amplified sequentially in some directions. And you could wonder whether the neurons, is there internal motion? Do the neurons actually rotate inside the sphere? And so this is what we're comparing here. This is the cosine similarity within the direction of the neurons at initialization and at the end of training, once we account for this amplification. And what's very surprising is in that case, it's really close to 1. So there is no internal motion between the neurons. You could imagine that they rotate and things are quite complicated. What's surprising is there's actually a lot of simplicity. The training dynamics here just seem to be stretching, like global stretching of the neuron population. Okay, and another way to see this is when we project the neuron weights in a plane, you see that the trajectories are mostly linear. So these are the individual neurons that move during training, and the trajectories are mostly linear, and they don't intersect, they don't rotate. So things seems to be actually quite simple. This is a puzzle that we don't have a theory for that. All right, so let me conclude. So my question was, what has been learned? And the answer is that we learn weight distributions for every layer, and sometimes just covariances. So we've been able to extract the mathematical object that is stable, that doesn't depend on a random initialization. So we might have if you want to understand what has been learned, it's more interesting to look at things that don't depend on a random initialization. We have a higher chance of actually understanding what they mean. But there is still, of course, a burning question is that what is encoded in these covariances? I don't have a model for the covariances. And I would like to understand, for instance, how they depend on the training data. What kind of statistics about the training data set is encoded in these covariances? So there's a lot of still work to do. And I would like to argue for treating trained networks as objects of scientific study, a bit like what Tom Gaussian was talking about yesterday, that there is an interesting space in between theory and practice where we look at real-world data sets and we try to understand what is the structure through the lens of networks, right? They're actually revealing things about the training data. And I think it's an underexplored direction where there are a lot of interesting things to do. And finally, this rainbow model, I think it opens many questions, both in optimization, like what is the regime of validity of this model? Can we actually prove that sometimes some of the assumptions that I've made are satisfied? And also in generalization, we're defining actually function spaces. are there interesting properties of these function spaces? Thank you for your attention.
We have time for a few questions. Sol?
Thank you, very nice talk. So does the alignment hypothesis imply that all the learned functions are essentially the same function?
Yes, so not only you learn the same function, but even at each layer, there is correspondence between the two networks, right? It's just a change of basis.
And do you expect that to happen outside the training set?
That's a very good question. So here, actually, when I was showing this, take a bit time to appear. When I was computing this was the alignment distance is computed on the test set. So I compute the alignment, the networks are trained on the train set. I compute the alignment matrix on the train set, but I look at the distance on the test set. So it also generalizes.
Up to like first order or something like that.
Sorry?
Like up to first order, the functions are the same.
Yeah. So yeah.
On slide 9, the blue line.
Yes.
Is that like just like a vanilla network?
Yeah. So this is like this scattering network of like at different width. This is the accuracy you get when you train it. Okay. So this network is actually very robust. Very robust. It's much better at small width than the model predicts, right? This model is here. It seems to be a completely different regime.
Okay. Thank you.
Is there a reason you're using a scattering network there instead of just a generic network?
So yeah, the reason is that I want to fix the spatial filters. Because if you look at spatial filters, let's say of AlexNet, the first layer, they're not realization of a Gaussian distribution.
Oh, I see.
So right. that can't work, right? It's easy to cook up examples where the weights won't be Gaussian. And so the reason I use this architecture is that I worked on it earlier in my PhD. And even though you fix the spatial filters, you're still able to reach accuracies that are on par with ResNet. So it's like a simpler architecture where you still have good performance.
Thank you.
Hey, super cool talk. I have a couple of questions. The first is, you mentioned the covariance that was learned in the Gaussian rainbow network is low dimensional.
Yes.
So how does the final performance change with the lower dimension of the covariances? As in, is there like an elbow at some point, or is it just smoothly improving?
So I'm not sure I understood the question. Maybe this is what this is showing here. So here I'm training the network without like imposing anything. So it learns the covariance that it wants. And then I'm kind of clipping this covariance by making a lower dimensional approximation. So this is how the accuracy changes when you project the covariance to the first few ranks. And what we see is that this number there is nothing universal about this number. It actually depends on the training set. So for instance, if we have some preliminary experiments where if we increase the complexity of the training set, like the number of classes, then this dimension seems to increase, which is, we could expect.
Awesome, makes sense. One more question. So does this analysis extend to, let's say, DAG structured networks that are not necessarily like a linear chain?
Yes, that's a very good question. So I've not thought about it. I think, it seems like there is a principle that is quite general, which is basically this law of large numbers on the kernels, which it seems to be quite robust to things you could change in a network. As long as you have width that can increase and you have things that are more or less independent, you get this kind of behavior where you have only orthogonal transforms. So I would expect this to be quite general, but that remains to be checked. Yeah.
Wonderful, thank you.
Are there any other questions? All right, then let's give Florentine a hand again.
All right, can everyone hear and see me okay?
Yes, we can see you.
Okay.
So to introduce our next speaker, coming to us by Zoom is Stephanie Karp from Google Research, who'll be telling us about provable gradient descent-based learning of decision lists by transformers. So please, Stephanie, take it away.
Thanks. Okay, yeah, so I'm Stephanie Karp, and this is provable gradient descent-based learning of decision lists by transformers. And this is joint work with Pranjal Wasti and Satyan Kale. So for some background, as many of us know, transformers have demonstrated incredible success in a broad range of language and vision tasks since their introduction in 2017. And there's quite a lot of work in the mechanistic interpretability world, which tries to understand how learned transformers actually behave. For example, the induction heads work from Olson et al., and in general, the broad range of work analyzing the attention structures that are actually appearing as transformers solve various tasks. But we also want an understanding of how gradient descent picks up this structure during training on data. And there are some example works in this space. For example, Lee et al., which looks at topic structure and characterizes the optimal solutions under the loss. And Jalasi et al., which looks at spatial structure and characterizes how gradient descent dynamics pick up the positional encodings to solve the task. But in general, there's not too much work in this space, and we definitely don't have a complete mathematical understanding of how this works. So in this work, our goal is to provide provable convergence results for gradient descent on a simple transformer with a simple data distribution that uses attention to solve the task. And I'll provide an example of what this distribution is, or I'll walk through an example and then we'll formalize it. So it's a decision list inspired distribution, and we're dealing with a sequence to sequence task over some vocabulary. And each token in the sequence is handled the same way. So for this example, we'll just look at one token in the sequence, token A, but the same thing could be applied to any element of the sequence, barring the fact that each token in the vocabulary has its own decision list. So on the left here, we see the decision list specifically for token A. And so what we do to generate the output, we look at A's decision list and we say, is D in the sequence? And D is in the sequence. So we output a Q. In the second example, we once again ask, is there a D in the sequence? There's not. So we drop down to G, ask if G is in the sequence, and there is a G in the sequence here. So we output E. In the third example, we once again ask if D is in the sequence. It's not. Is G in the sequence? It's not. Is A in the sequence? And it must be because A is the token itself. And so we output a P. And this feature that the last element of this decision list will always be the token itself is a characteristic of the decision list for all of the different tokens to ensure that there's always a match at the end. So formalizing this a bit, we have our input sequence and our output sequence drawn from some distribution. Each sequence is an element. Each sequence has n tokens belonging to a vocabulary of size L. And each token A in the vocabulary has a corresponding decision list, A1 through AM, where AM is the token itself. And the length of the decision list is assumed to be much less than the size of the vocabulary. In addition, we assume that we have a global permutation function pi, which instead of just being an arbitrary mapping here, as we saw before, we assume that this mapping is determined by pi. And this pi is the same pi across all of the different tokens decision lists, which ensures global consistency, which we'll see is important. So stating this formally, for every token A in the input, it maps to pi of A sub j in the output, where A sub j is the first element of A's decision list that appears in the sequence. And we further assume that our input sequence contains no duplicate tokens, And we also assume that each type of error the model can make, if it occurs with probability at least delta. And by type of error, we mean if A was supposed to be classified as G in the output, but instead was classified as something else, there was a misclassification, that pair AG represents a type of misclassification. A should have been labeled G, but wasn't. Okay, so now I'll introduce the architecture. So we look at a very simple transformer. And one simplification we make is that we collapse the key and query matrices into a single matrix W. We have a value matrix out front. We have no residual connections, no normalization. And in addition, rather than having a mapping to some d-dimensional embeddings, we work with the one-hot encodings directly. And so our V and W matrices are L by L matrices. Further, we're in the realizable setting. And so one setting of the parameters that can solve this task would be setting V, the value matrix, to C times P for some positive constant C, where P is the L by L permutation matrix corresponding to pi, the global permutation function. And the fact that it's a global permutation function is what allows us to be in this realizable setting. And furthermore, if W, so once V is set to CP, if W has properly ordered weights, then we get perfect classification. And by properly ordered weights, what we mean here is that each column of W, because we're working with one-hot encodings, corresponds to a token of the vocabulary. So as long as the elements of W in that column have an ordering that matches the ordering in that corresponding token's decision list, then we get proper classification. So for training, we look at the standard cross-entropy loss with a softmax applied out front. Our two main theoretical results are we train just W with V fixed to C times P. And in our second result, we'll train W and V starting from a well-initialized V, so near CP in some neighborhood of CP. And finally, we'll present some evidence that V can reach a good initialization within just one step under uniform attention. Okay, so I'll state the results, the two theorems informally and flash the formal statement on the screen, mostly for the purposes of the recording. So the theorem for training W stated informally is fix V equals CP for sufficiently large C and initialize W at 0. Run gradient descent on the population loss with sufficiently small learning rate eta. Gradient descent will find a WT that achieves perfect classification on all sequences within a small number of steps. And in the formal statement, we define C, we define learning rate, and we define small number of steps. For training W and V, stated informally, initialize W at 0 and V close to CP for sufficiently large C. Run gradient descent on the population loss with sufficiently small learning rate eta. Gradient descent will find a WT, VT that achieve perfect classification on all sequences within a small number of steps. And once again, we define close to CP, we define sufficiently large C, we define the learning rate, and we define small number of steps. Okay, so now I'll walk through sort of a proof highlight sketch of one of the key components of the proof. And this idea will apply both to the case where we're training W as well as to the case where we train W and V, but with further modifications to account for the fact that V is not actually equal to CP. And we're going to be in a simplified setting here where this global permutation function pi is the identity, and we have V set to C times the identity. And what that will further allow us to do is when we refer to an element of the decision list, that will be the label itself, which will simplify our language in the discussion that follows. So once again, we're dealing with one-hot encodings, which allows us to reason about each column of W separately. Each column corresponds to a token of the vocabulary. And so once again, let's just consider token A. It can be any token, but let's consider token A, and let little w denote A's column in the matrix W. And so as long as the weights of W, of little w, are ordered corresponding to token A's decision list, then we'll get perfect classification in all sequences with A. And this ordering corresponds to the amount of attention that A is paying to different tokens in the sequence. So we want it to pay the most attention to the first element of its decision list that appears in the sequence, etc. So if there's a misordering, then we'll get a misclassification. So now let's suppose that K is A's true label in some sequence. If K is A's true label in a sequence, then the derivative of the loss with respect to W sub K will be less than or equal to 0. And furthermore, if A is supposed to be classified as K, but is not classified correctly as K, then not only will the derivative be negative, but we can actually show that its magnitude will be large. This is good towards showing that we have a large gradient. So the question is, so it shouldn't be obvious why that's true, but we have mathematical analysis working this out, showing that it's lower bounded. The magnitude is lower bounded. So now the question is this enough? Are we done? We've shown that when we have a misclassification, we have a large gradient. And we're not done. And the reason why we're not done, and some of the difficulty here, is that when K can also appear in sequences with A, where K is not the true label for A. So for instance, other elements of A's decision list also appear in that sequence, and elements that are before K in the decision list. And so those will be the true label versus K. But we still have a derivative with respect to K there in those sequences. And in those cases, the derivative with respect to W sub K can be positive. And so in expectation, remember, we're dealing with the population loss. So in expectation, it's hard to argue about what will happen. There can be some sequences in which the derivative is negative and some sequences in which the derivative is positive. And we don't have a guarantee that balances out to give us a large derivative. So what can we do? So instead, we can argue about a certain directional derivative that reduces to the derivative with respect to WK whenever K is the true label and is always less than or equal to 0 otherwise. So this allows us to circumvent this problem that in some sequences, the derivative can be positive, which can take away the contribution of this large negative gradient. So I'll provide a brief example to sort of illustrate what this directional derivative is, or at least the kind of idea of it. So once again, with token A, we had the decision list DGA. And let's suppose that in all sequences where D appears, we have perfect classification of token A. In all sequences where G appears with token A, we get perfect classification of token A. But there are some sequences in which D and G don't appear, where A is misclassified. And so we're basically, what we're doing is we're looking through A's decision list and looking for the first element of A's decision list that yields some misclassification. Here, we're assuming it's A, so it's at the end of the decision list. So we then consider the directional derivative that doesn't just look at the derivative with respect to WA, but looks at these other components as well, the derivative with respect to WD and the derivative with respect to WG. And it turns out that this derivative is actually less than or equal to 0 for all sequences. And in showing that, we crucially rely on the fact that D and G, when they appear, always yield correct classifications. So if instead there had been sequences in which A appears where G also appears and yields misclassifications, then our directional derivative, we would just construct it with these two components, not A. So we're looking for the first element of A's decision list that yields a misclassification, and then we consider the terms up to and including that element of the decision list. And it's that directional derivative that we can show is always less than or equal to 0. But in the case where that last token that sometimes yields a misclassification, in this case A. In the case where A was the true label, that means that there were no appearances of D and G. And so these terms are 0, and we reduce to the derivative that we actually had cared about in these misclassification examples, and that we had shown were less than or equal to 0 with large magnitude. So this general proof idea of looking at this type of directional derivative applies in the case where we're training just W, and it also applies in the case where we're training W and V, but with some variations to account for the fact that V is not actually equal to C times the permutation matrix. Okay, so finally, we have some experiments, just one displayed here, but there are various others that show that after one step of training V under uniform attention, we can pick up the structure that we care about. And you can ignore the details below. They're mostly here for the purpose of the recording. But the key point here is that under uniform attention, we can get very close to this permutation matrix structure that we wanted. And so this presents some evidence, some empirical evidence that it might be reasonable to start out with a V that's kind of near C times P. Okay, so in conclusion, we've introduced and formalized a simple decision list-like data distribution, which can be solved using attention and is suitable for theoretical analysis. We've proved that gradient descent on the population loss efficiently finds a solution with perfect classification when the value matrix is good. And we've showed empirically that a well-initialized value matrix can be recovered pretty quickly under uniform attention. So some future possibilities, extensions of this work, could include weakening the distributional assumptions and maybe moving toward a setting where instead of requiring perfect classification, we allow for some small error tolerance. And also extending these results to a full convergence result, starting with random initialization for V. And the empirical evidence that we showed on the previous slide gives us some hope that this might actually be a reasonable thing to do, because V doesn't have to, with under uniform attention, which is basically a 0 or small initialized W, V can already pick up the desired structure. So that's all I have for today. Thank you so much for listening. And let me know if there are any questions.
Are there any questions for Stephanie? So I had a question. You had in the gory details for the for YouTube, you had this constant delta based on how frequent the failures have to happen. What was the dependence on that?
Yeah, should I just scroll back to the slide or?
Yeah, that'd be great. Yeah, what goes wrong when that gets small?
Yeah, so in just training W, it basically requires us to have a large C effectively. So we have this 1/delta dependence. And you can see that here as well. And it's basically because when we're trying to show that when there's any misclassification, we'll have a large gradient. And so we need, we're accounting for any type of misclassification here. So if you could have a misclassification with a really, really small delta, then that could slide through if C isn't large enough to compensate for that.
Great, thank you.
Yeah.
Yeah, thank you.
Okay, testing. Everyone, can you
All
hear me?
right. Yes, we're good to go.
Okay.
So our last contributed talk of the day is Thien Lee. We'll be talking about the Poincare inequality. Wow.
Yeah.
Please go ahead.
Thank you very much for the introduction. I'm Thien. I'm a PhD student from MIT, and I'm happy to present to you a joint work with Luana Ruiz from Johns Hopkins and Stephanie Jagelka from TUM and MIT. Our project and the corresponding paper is called Poincare inequality and consistency results for signal sampling on large graphs. So let's go into the talk. So this is a very obvious fact that everyone who learns graph algorithms will know, that it scales with the number of vertices. If you do spectral decompositions, you pay at least a quadratic order of time. And since this is deep math, if you train graph neural networks, you pay also at least a quadratic order of time, a quadratic order of the nodes in time. So these are very vacuous lower bounds. But what is not so naive is the observations that in most graph-based learning tasks, the complexity of the of the task does not scale with n in these ways. And in particular, n represents the resolution of the data sets instead of the complexity of the task. And more generally speaking, there are some kind of intrinsic dimension, intrinsic complexity parameters underlying realistic graphs. For instance, there's a small world phenomenon where if you take two people at random, there's a very high likelihood that there's a path of 6 people between them, that's where the edges are acquaintance relations. Or in realistic models of the internet or of social networks, there's a notion called scale-free or power law graphs, where the degree are distributed through a power law distribution. And maybe you cannot see the labels on the axis, but on x-axis is the number of connections, so the degree, and on the y-axis is the frequency. So there's a tail there. That's the small number of influencers, politicians, rock stars that have a lot of influences on the social media, for example. And the vast majority of the rest of the nodes have very few connectivity. So how do we reconcile these discrepancies between our learning algorithm scaling through the number of nodes while the complexity parameters of the task doesn't? So, well, the idea is to subsample a small number of nodes that hopefully will more accurately capture the complexities of the task. And we don't want to just uniformly sample. We want to find the most informative subset of the vertex set, given like a budget of k nodes. And spoiler alert, this will be done through optimal sampling, and sampling in the term of signal processing and not from the usual machine learning sampling sense. And not only that, we also want to not redo this pre-processing step every time we have a new node coming into the network. So every time we have a new users in the social media network, we don't want to redo this subsampling step. And we are going to ask for transferable subsets that is also almost correct when the graph grows in size, according to some process. And another spoiler, this is done through graph limits, and in particular graph forms, the limits of dense graphs. So before we go into details how we can find this algorithmically, let's look ahead and ask, once we have these subsets, what can we do? So immediately we have faster algorithms that scales in this, in k, this smaller number instead of n. And the bulk of the project or the paper tries to understand the conditions, the assumptions for which we can do this with a small decay in performance. And we also show some empirical results. So let's get started. So let's get an intuition of how it's even possible to find a small informative subset. And this comes directly from a very foundational result from signal processing called Shannon-Nyquist theorem. That says that if you have a signal, a continuous signal, and you put a limit on the bandwidth. So the bandwidth is a limit on the bandwidth will exclude functions that varies very fast. So for example, a limit on the bandwidth may exclude the dotted functions there, but still allow for smoother varying functions. And Schoen-Nyquist says that if you put a limit on this bandwidth, then you can uniquely determine this continuous signal just through discrete sampling uniformly at a certain rate. And this you uniquely determined is in norm, so there's no ambiguity there. And immediately using this, we have sampling theory results for 1D CNN. See, and the two statements are almost verbatim. You have if your image comes from some continuous L1, and you have a band limit assumption, and then you take a picture with n uniform pixels. Schoen-Nyquist immediately tells you that you only need k of these pixels to gain all the information there is in the image. So here's a picture. This is the image, not a very good-looking one, but that's a 1D image. Let's do a CNN on top of it, and only the blue nodes are required. And those will contain all the information there is in the signals for you to learn to train your CNNs, for example. And they also put a path between each of the nodes, because 1D CNNs are just GNNs on the path graphs. And this can be generalized and was generalized to arbitrary finite graphs by Vesensens in 2008. And the result is, again, almost verbatim from Schoen-Nyquist, and says that if you have a graph signal, which is a signal processing term for node features, and you put a limit on the bandwidth. So what's the bandwidth of a graph signal? So first you construct the Laplacian, the diagonalization of which gives a unitary transformation, which is the graph Fourier transform. From there you can compute frequencies, and applying the transform into your graph signals give you the coefficients of these frequencies. And by putting a limit on the bandwidth, we simply make sure that high frequencies are not allowed in our graph signals. So Vesensens says that if you put a limit on the bandwidth of the graph signal, then there is a small subset of the vertex set called the uniqueness set that uniquely determines the node features. So knowing the nodes in blue gives you all the information you need for the node features at the other nodes as well. And so if we stop here, then we already have there already exists an informative subset that we can find, but we want to do it in a transferable way as well. And here's the pictures of graph fonts taken from Yufei Zhao's textbook. The graph font is the rightmost pictures, and it's a measurable functions, symmetric measurable functions on the unit square. Informal interpretations is that the vertex is a continuum 0, 1, and you draw an edge if the function w is non-zero. But more formally, we can think of it as a finite graph sampler, where you have, if you ask for a graph of n nodes, you first sample the nodes, and then you put an edge on them with by a Bernoulli coin flips with parameters given by the function values. We use these graph limits in order to give us a framework to define and study transferability. So to actually define transferability, we have to ask under which task and under which architectures and everything. But here's an example. If you want to study transferability of GNNs, let's say, where you have different nodes, where the input graph have different nodes size, m and n, but they share the same parameters. And then you ask how are the functions on the node features different by some metric d. And we say that there's transferability if you can bound this difference with a function that's decreasing in m and n. And under when we say that two graphs came from the same, sampled from the same graph forms, theorem by Ruiz, Chamon, and Ribeiro tells us that the right-hand side, the bound, is at most a small number plus a very strong rate, 1 over m plus 1 over n. And so putting together, the uniqueness set framework of Vesensens give us a way to find informative subsets, and we have a way to define transferability using the limit graphons approach. And therefore, it suggests the path of studying uniqueness sets on graphons. And then we show results for corresponding for those uniqueness sets when restricted to the finite graphs sampled from the same graphons. So this is not a new slide. This is not a new slide. This is from the Bessenson's result, and there is a direct generalization using Poincare inequality. And again, the statement is almost the same. If you put a limit on for a graph signal f, which is again functions that assign nodes to some features, and you put a bandwidth on a limit on the bandwidth, which again can be defined analogously. You have a graphon Laplacian, which is a Hilbert-Schmidt operator. So you have a simple diagonalizations give you a unitary transform, which is called graphon Fourier transform. And you'll have all these eigenvalues. There are at most countably many of them, and there's at most one accumulation point. So you can also put a bandwidth cutoff, which assumes that all the high frequencies features do not occur in the graphon signal. And we also show that if you have a limit on the bandwidth, there's a measurable subset U of the unit intervals, such that knowing the graphon signal on this smaller subset will give you all the information you need on the full interval 0, 1. So that gives you a possibility of the existence of this small subset that contains all the information you need. Let's put it into an algorithm so that we can actually do this in practice. So our input is a large graph G of n, and the output is a small uniqueness set for every graph that has more node than this input graph, but it comes from the same graphons. So first, we obtain an approximation of the limit graphon with this large graph. Then we approximate the uniqueness set of the graphon with the uniqueness set of this large graph. And then we map back the uniqueness set of the large graph to nodes in the larger graph. That's a pretty straightforward algorithm. Let's prove that this actually works. So first, how do we approximate the limit graphon with a finite graph? Well, you embed it into the vertex, you embed the vertex of Gn into 0, 1. And this works because of a very nice theorem by Lovász and Széchenyi that says that graphon space is compact and finite dense graphs are dense in this space. So, so to show the predominance of this approach, the same statement for sparse graph limits is a completely wide open conjecture, and it's have very deep roots in proof theories and everything. But with this, if n is large enough, we can do a good approximation of the limit graphon. Okay, so let's find a uniqueness set for a large graph and also show that it approximates the uniqueness set of the graphons. And to do this, we view a graphons as a kernel. And I'm not going to too much details into this, but it's an example of how graphons can be viewed as a mixture model of random graphs. So you have a graphons that looks like the graph on the left here. Then it almost looks like you're drawing vertices from bimodal Gaussian mixture, and then your kernel is just a L1 kernel, for example. And of course, you can also view this as a single component mixture model with the component being just the bimodal Gaussians, but that's not very nice. And there's a well-fitted measure given by seminal papers by Schebinger, Wainwright, and Yu in 2015. And without going into too much details, we show that if the well-fitted measure is small, if it's nice, if it is well fitted, then Gaussian eliminations performed on the Laplacian of the large graph with certain pivoting, we find uniqueness set with high probability. And intuitively, this is because in Schebinger et al., they shows that spectral clustering embeds the data sets into these orthogonal cones. So performing Gaussian eliminations on the transformed data sets, we've sampled one clean sample from one component of the mixture model, which corresponds to a uniqueness set for the graph, for the large graph. And finally, we show that a consistency result, which says that eventually there's a large number n, big N, such that every node, every subsequent graph after that, which higher number of nodes, the uniqueness is consistent. The uniqueness set of the larger graph is also the uniqueness set of the smaller graph, of the G big N. And we perform a couple of experiments, but here I'll only show one. And here we use the subsampled vertices to compute positional encoding, which are usually just the eigenvectors. So usually you compute eigenvectors on the large graphs, and then you use that as positional encodings to train your graph neural networks. Here we compute positional encoding only on the subgraph, and then we path 0 to get an almost eigenvector. And so this is a result. And we show that there are a lot of decays in the performance between the graph on sample P's and the full graph P's, which is a transferability statement. And then also show that it's better than uniformly randomly sampled, and then compute the P's on the uniform subsampled. So in conclusions, you should find a small subset of the vertex set that better captures the complexities of the graph of the graph learning task. And we do this by finding an informative subsets via sampling theory and a transferable subsets via graph limits. And we derive consistent algorithms that approximate samples, and we tested our approach with experiments. So thank you for your attention. Also open to questions if there are time.
Thank you, Thien. We're a bit over on time from technical delays, so we can refer questions offline. And then we have our last speaker, Holden Lee. is Holden Lee, who is from my own department in AMS. Holden works on diffusion models and generative kind of GAN setups. So please, Holden, bring us home.
Great leap forward in generative modeling. So one area where they've made prevalent progress is in generative AI art. So back in BronyCon, which is the My Little Pony convention in 2009, which incidentally happened in Baltimore, there was a booth where you could pay $2 to get a picture of an AI-generated pony, and these were generated by GANs. And now, fast forward 4 years, we have diffusion models, and they've been fine-tuned on pictures, illustrations of ponies, and now you can get endless amounts of generated pony pictures from the comfort of your own laptop. Okay, so more seriously, the problem that we're interested in is we want to learn a probability distributions from samples in such a way so that we can easily generate more samples. So there's been many approaches to this over the years, which I'll roughly classify into two categories, likelihood-based and non-likelihood-based. So for likelihood-based methods, these are methods which require sort of parameterizing and computing the likelihood of seeing a particular data point. And the nice thing about this is that, if you have the likelihood, you can try to maximize that directly. However, this runs into issues often because you have to sort of evaluate a partition function or normalizing constant, which is intractable. So this often requires MC or variational inference. There's been a lot of non-likelihood methods that try to circumvent this difficulty, including generative adversarial networks, noise contrastive estimation, and the one I'll focus on today, which is diffusion generative models. These also have, sometimes are called score-based generative modeling. And these were, the idea of score-based generative modeling was originally introduced into statistics by Hyvarinen in 2005. More recently, as diffusion models brought into machine learning by Sol-Dickstein et al., and then further developed by Song and Ehrman. Okay, so diffusion models have, have state-of-the-art progress on image, audio, video generation, core component of many of these image generation tools. And if you're on a more serious side, they've also found scientific applications to inverse problems, molecular modeling, can be used in a hybrid form with classical sampling algorithms like Markov chain Monte Carlo, things like that. So the question I'll be interested in is what theoretical guarantees we can obtain for diffusion models. Okay, so I'll first give a quick intro to how these work. So there's many ways we can, many types of diffusion models, but what they have in common is that we first define some kind of forward noising process that turns our data distribution into pure noise. So this could be a stochastic differential equation, but it could also be a Markov process on a discrete space or a deterministic process like an ODE. And I'll note that you can have a general framework for these things. So Andrea Montanari has a nice paper where he makes this correspondence to stochastic localization, which is actually corresponds to diffusion models, but was independently proposed in probability theory for completely different reasons. So now that we have a forward noising process, we can define a reverse or backwards process which turns pure noise into new fresh samples from our data distribution. So we'll focus on the case where we have an SDE, and it'll turn out that this reverse SDE will involve something called the score function, which is the gradient of the log PDF. This is often estimated with a neural network. Okay, so I want to briefly compare diffusion models with some other generative models. So like GANs, variational autoencoders, so kind of like a prior generation of these generative models, we also are trying to transform pure noise into samples from our data distribution. But often we think of the neural network as sort of one big black box that does all the work. So for diffusion models, we actually, what forms the backbone of the diffusion models is this reverse SDE. And we're actually just using the neural network to estimate this particular score function. So what happens is we're actually discretizing this SDE, taking a bunch of steps. And at each step, when we need the score function, we're calling the neural network. So in some sense, I like to think about diffusion models as sort of like a success story for using math in deep learning, because it is very heavily based on modeling with this SDE. Okay, so let's go more in depth into sort of 2 steps to using a diffusion model. So the first thing we need to do is to estimate the score function from data. So the score function is defined as the gradient of the density, the probability density function. And I'll often parameterize a density as e to the negative v. So this will be a negative gradient of v. And the second step, once we have an estimate of the score function, is to then use it to draw samples. And why we think that having the score function might be useful, we can already see this in a classical algorithm for sampling called Langevin Monte Carlo. So it's a generic algorithm for sampling, much the same way that gradient descent is a generic algorithm for optimization, where to sample from e to the negative v, we simulate Langevin diffusion, which is gradient flow plus Brownian motion noise, and then we discretize that to form Langevin Monte Carlo. And in this case, when we're estimating the score function from data, instead of using the known value for this gradient, we use the score function, or the estimate of the score function. We'll actually be using other diffusion processes based on reverse SDEs, which will turn out to work better. Okay, so the first step involves estimating the score function, but it's unclear why we can even hope to estimate the score function from data, because it's this gradient of the log density. So it turns out that there's actually a nice equivalent way to formulate this problem as a supervised learning problem. So that's sort of encoded in this proposition. So this is saying that we can estimate the score function via minimizing this denoising autoencoder objective. So here's how it works. We have our data point x. So we have our data point x, and we imagine the following problem. So we add some Gaussian noise C of variance sigma squared to get y. And then we ask, given y, we want to denoise y and then find our original unnoisy point x. Okay, and then we want to minimize our loss in the squared error. Okay, so this is okay. So so R here is the denoising function. that will turn our noisy point hopefully back into X. And the content of this proposition is that the optimal way to denoise is to move in the direction of the score function. Okay, and so the optimal thing to do is to add sigma squared times the score function. So intuitively, what you can think of this as saying is the score function is pointing in the direction where the probability density is higher. So that is the direction you want to move if you want to denoise your point. Okay, so I'm actually going to give a proof of this proposition. So if there's one computation that you take away from the talk, I think this is a good one to know. Okay, so first I'll rephrase this slightly in terms of recovering the noise rather than the original point. So equivalently, we could say, we're trying to find the noise C that we added to our point. And the equivalent statement is that the optimal estimator for this noise is sigma squared times the gradient of V. I'll note that this is the score function not for P, but for a slightly noisy version of P, which is P convolved with the Gaussian. Okay, and to see this, let's go ahead and compute the gradient of V, which is the negative log PDF of the perturbed density. So this is a gradient of a log of a convolution. So let's write out the convolution as our original density integrated against a Gaussian. And when we take the gradient with respect to y, this whole thing goes in the denominator, and in the numerator we'll use the chain rule, and then this exponent here comes down as y minus x over sigma squared. Okay, so then we can rewrite this thing here. We note that this is the probability density of x, and then this, by our model, this Gaussian is the conditional probability of y, our noisy point, given x, our original point. Okay, so then by Bayes' rule, this thing is actually evaluating a posterior expectation of x given our observation of y, the noisy point, where we're computing the expectation of y minus x, which is the noise that we added. So the outcome of this computation is that this gradient is exactly the posterior expectation of the noise given our observation y up to this scaling. Okay, so what this means for us is, so we have this key identity here, and the proposition here immediately follows from this identity because the minimal mean squared estimator we want here is exactly going to be the mean of the posterior. So the whole upshot of this is that we can actually learn the score function as a supervised learning problem because we can sort of minimize an empirical version of this objective. Okay, so this so returning to the two steps for diffusion models. We are estimating the score function for data, and then we're given samples, we're given the score estimate, we're drawing the samples using the reverse SD. Okay, so this brings up two natural theoretical questions, which is, so I'm going to actually do these in the reverse order. So the first question I'll ask is that suppose we have a L2 accurate score estimate. So I'm saying an L2 accurate score estimate because that is what we can hope to achieve by minimizing the empirical objective that we have. So given this accurate score estimate, what guarantees can we get for sampling from P? And then the second question I'll ask is, how can we hope to get this L2 accurate score estimate in the first place? So I'll note a few things. I'll first address question one. And so there's a whole lot of literature on guarantees for sampling algorithms like Langevin Monte Carlo. And what's different about this from the usual setting is, one, that we only have a L2 accurate score function rather than exact or stochastic version. And also that we are following a non-time homogeneous process. In other words, we're following non-equilibrium thermodynamics. So I'll spend most of the time on this question 1, and then if there's time at the end, I'll say a few high-level things about question 2. Okay, so you might ask why we can't just use Langevin Monte Carlo. Is because Langevin Monte Carlo will run into issues with mixing, among other things. And we are really hoping to be able to model distributions that could be very highly multimodal and ill-behaved. And in fact, this reverse process will sort of act like annealing, which allows us to sample from the multimodal distributions. Okay, so now I'll address question 1. So convergence theorem given an accurate score function. Okay, so I'll talk about 2 works here. So first is how we can get guarantees for very general data distributions without assuming functional inequalities and without assuming smoothness. Here we'll show that we can do this without smoothness because of sort of good smoothing properties of the forward process. And then the second thing we'll try to do is that it's very important here to think about the dependence on dimension and other parameters, because diffusion models are actually very costly compared to other generative models because of the number of steps, discretization steps that we need, which, and every step we sort of call the neural network. Okay, so we can ask, can we get better dimension dependence? And then we show that we can do this using an ODE instead of SDE. Okay, so I'll talk about the first one now, which is joint work with Hongwei Chen and Jennifer Liu. Okay, so I have to first introduce the diffusion model that we'll be working with. So I'll be working with the denoising diffusion probabilistic modeling with an exponential integrator. So the forward SDE that we'll be using is the Ornstein-Uhlenbeck process here, which is you have a drift towards the origin and then Brownian motion. And then there's a generic recipe for taking any forward SDE and turning it into a reverse or backwards SDE. So we reverse time here and we get an extra, so we reverse the sign and then we get the score function from here. Okay, so what we know about the Ornstein-Uhlenbeck process, which is this forward part, is that we have exponential convergence from any distribution to any nice distribution to a Gaussian distribution. So after some moderate time t, we'll actually have this is very close to being Gaussian. Okay, this means that if we now imagine that we're starting at time t with exactly a Gaussian, then we can run the backwards process and get some qt hat, which is hopefully close to P0, the data distribution. So formally we'll use the exponential default way to integrate this is using the Euler-Maruyama discretization for SDE. We'll actually use a slight modification called the exponential integrator, which is based on the fact that this linear term we actually can't integrate explicitly. So this is the discretized version of this backward SDE. Okay, so now I'll summarize the results that we have. So we'll assume that our very basic or minimal assumptions on our data distribution that has bounded second moment, and we have a L2 accurate score estimate up to epsilon score. and we'll give guarantees for DDPM under decreasing smoothness assumptions. Okay, so if we assume that the score functions at all times are smooth, then we can get, so we get a reverse KL guarantee for how close the data distribution is to the output of our algorithm. And the number of steps to get this epsilon squared error will be DL squared over epsilon squared. Okay, on the other hand, we can also make no smoothness assumptions. Here we actually need to compare against a slightly perturbed version of the data distribution P delta. And we show that we can do this, but suffer without this L factor, but suffer an extra factor of D and log of 1 over delta squared. And then we can also have sort of a more intermediate regime here, which I won't go into. But the intuition between these two results is somehow that, we can, if we look at the Lifshitz constant of our score function, it's somehow effectively bounded by square root D, so that, we can substitute square root D in here and get the result without smoothness. Okay, so the idea for our proof is that we'll use Gersonov's theorem to compare the continuous process with the exact score, and then the interpolated process with the estimated score. So this is when we're doing the actual discrete process, but we sort of interpolate it into a continuous one so that we can compare. Okay, so I'll now state this a bit more formally. So the assumptions that I'll make is that our data distribution has finite second moment, and that our score estimate has some average error epsilon score here. And I'll first consider the smooth case where the score is L Lifshitz. Okay, so we can then, we can bound the KL divergence between the data distribution and the output of our algorithm by 3 terms here. And there's a setting of parameters, where the number of steps is what I claimed. And these 3 terms will quantify the convergence of the forward process, the score estimation error, and the discretization error. Okay, so I'll go through each of these in turn. So the first term comes from convergence of the forward process. So we can, by the chain rule of KL divergence, we can break up, the KL divergence at the end by sort of the KL divergence at the beginning plus the KL divergence of the conditional distributions conditioned on the starting point. Okay, and then by the beginning here, I mean that we're treating the forward process after time t pt as a Gaussian distribution, and then running it backwards from the Gaussian distribution, but there's actually some error here. And this is, how the error here is like how close PT is to a Gaussian. So this is actually controlled by the mixing of the forward process, OU process. Okay, so this thing we can actually bound by something that is exponentially decaying in T. So we can make this really small as long as T is moderately large. Okay, so the second part is where we now have to sort of, so we have this remaining term, which is the expected sort of value of this conditional, the KL divergence between these conditional distributions when between the actual backwards process and the discretized backwards process if we start them at the same point. Okay, and also using the chain rule for KL divergence, we sort of compare this by comparing through a chain of processes where we imagine we follow the discrete process for all the time steps versus we follow the continuous process for some time and then take discrete steps. Okay, so we basically go through this chain of of these kind of n different distributions that we get by running the continuous process for different amounts of times. And then for the KL divergence for each of the between each of these pairs, what we can do is for the discrete process we interpolate it, so we can write it as SDE, and then we can use Gersonov's theorem, which will give you the KL divergence between the distributions of two SDs with the same diffusion term but different drift terms, bounded by this expected square difference between the drift terms. And this expected square difference here, we can break this into two parts. So one part is, we're evaluating the score function at, so for the actual process, we're evaluating the score function at the for the actual continuous process, we're evaluating the score function at xt. And for our discrete process, we're evaluating the estimated score at the discrete time tk. Okay, so we can break this up into the score error at the discrete time tk, and then the difference between the scores at the discrete and the continuous time t. And for this first term, this is exactly going to be the score error added up over all time. Okay, so finally, the third term here is the discretization error, and this turns out to be the crux of the proof is in bounding this term. Okay, so note that, well, we can note that this term now is actually, we're looking at xt that's drawn from the continuous process. So this is a statement really about the OU process, okay? And we can split up this discretization error into a time component and a space component. And it turns out that sort of this, it's sufficient to bound this space discretization error. So this is where we're looking at the score function, but at two slightly different points. And essentially what happens is that these 2 points that we're comparing at are the difference between them is a Gaussian of variance s minus t, which is the at most the distance of the discretization step. Okay, so to bound this difference, we can bound this by the Lipschitz constant squared of the score function times the expected value of the Gaussian squared, and so we get this dl squared times s minus t. And so when we integrate this, or when we sum this over all steps n, this gives us our total discretization error. Okay, so that's the case where we have smoothness. So let's see what has to change when we don't assume smoothness. So first, I'll sort of relax what will allow also is that we can allow different step sizes now. And for this, we then, for our score error, we actually look at this weighted score error where we're weighting by the step sizes. And so I won't go into the details here, but what this weighting actually allows us to do is that it allows us to get a good bound even if the score estimate error is diverging as t goes to 0. Okay, and then this is useful because we could deal with a distribution that's even singular, so not that doesn't have a density, and in that case, as the amount of noise you add goes to 0, the score function here could actually blow up. Okay, so this allows it to blow up at this 1/t rate. So if you have this estimate, then you have this epsilon score with with this log 1 over delta term if you stop early at delta. Okay, so what we can get here now is that without assuming smoothness, we get the exact same bound, but instead of L here, we get an extra factor of D. Okay, so yeah, and then you can also get a Wasserstein guarantee from this. Okay, so the intuition here is that our L is effectively bounded by square root D. And to show this, so how to make this precise is what we want to show is that the smoothness of the score function, that is the Hessian of log PT, that we can bound this with high probability. Okay, so we actually get a bound on this Frobenius norm of the Hessian in terms of D. And it's okay to just get a Frobenius norm because we only need the Lifshitzness in a random direction. Okay, when we do the space discretization error, it's between 2 points which differ by a Gaussian. And this 1 over T is okay as long as we take a geometrically decreasing step sizes, then they'll sort of add up to a log 1 over delta term. Okay, so for time constraints, I won't go into the details of this proof. I will note that subsequent work actually by Benton et al. Actually improved the bound on this using ideas from stochastic localization, and they're actually able to eliminate the extra factor of D here. Okay, so this shows the convergence rates for general data distributions. Next, we'll try to look at how to get faster convergence. Okay, so what we looked at was this DDPM, which is the this SDE given by the Ornstein-Uhlenbeck process. And the line of works I mentioned, we show convergence guarantees with order D steps. It turns out that there's also a lower bound of order D for trajectory-wise analysis, even if you attempt to speed it up with this critically damped Langevin diffusion. On the other hand, there's a different ODE formulation, the probability flow ODE, given on the right, which has the same marginal distributions as DDPM. And this you can either see by writing down the Fokker-Planck equation and see the density evolves the same way, or through a Wasserstein gradient flow interpretation. And this turns out to be much faster in practice, even like something like 50 times. But people have observed that it could be less stable and sometimes give lower quality output. So in this work, in the subsequent work, we give some theoretical backing for these empirical observations so that you can, with the ODE, reduce the dependence on D to square root D. But we have to add in corrector steps and assume some smoothness. Okay, so what is the trouble with SDEs? So when we try to discretize an SDE, we get discretization error rising from 2 terms. So one is the drift term and one is the diffusion term. And this score term here you can think of as something on the order of square root D. So for the drift term, the discretization error we get is on the order of h times square root D, while for the diffusion term, because of the scaling of Brownian motion, we get an error of order square root h times D. Okay, so this means that to take the drift term small, it suffices to take our step size h on the order of 1 over square root D. But to make the diffusion term small, we have to take h on the order of 1 over D. Okay, now the probability flow ODE only has the drift term. So we can hope optimistically that this then allows us to take h on the order of 1 over square root D and get a square root D complexity. so this is in fact true. So to state this, we need the same, we make the same assumptions, but now I need to assume that both the score function and the score estimate are Lipschitz. Okay, and okay, so so now we also can get write out all the different sources of error that we get. We have a more complicated expression with more terms, but the important thing to note here is that there's a setting of the parameters, so the step size on the order of 1 over square root d. So we get a number of steps that's L squared d to the 1/2 over epsilon. And I'll note that the dependence of number of steps on both d and epsilon is the square root of what we had for SDEs. And these terms now quantify the same things, except this we have these two terms here, which is the discretization error from the predictor and the corrector step. And I'll explain what this corrector is. Okay, so our algorithm is based on the probability flow ODE, where we start with a draw from the Gaussian distribution, and we run the discretized backwards probability flow ODE for time 1 over L. And after that, we actually have to run a corrector, some corrector steps here, and then sort of alternate between these two until the end. So I'll explain presently what this corrector is and why we need it. Technically, we need to modify this a little bit, but I won't go into that. Okay, so what are some challenges in obtaining the square root d dependence? So the first one is that we can't use Gersonov's theorem, which is a staple of this SDE discretization analysis, because we're using ODEs. So we instead do a Wasserstein analysis with coupling. And when we do this analysis, we'll find that, so like the classic sort of analysis of the Euler discretization, we'll get this exponential growth in this distance with rate L, which is the smoothness, so that we can only run this for time 1 over L. So this is where the corrector step comes in. So we'll actually use the corrector step to convert this Wasserstein into TV error. This is called a short-term regularization result. And using the data processing inequality for TV distance, we can then restart the coupling and then run the predictor again. So what is this corrector? So this fits into the sort of predictor-corrector framework for diffusion models, where the predictor is sort of when we're trying to simulate a time-varying distribution. So here we're following the probability flow ODE, which is a distribution that's changing over time. Okay, so but when we do that, there's sort of increasing errors we can diverge, because of the discretization. So then we instead pause this probability flow ODE and then run a corrector, which doesn't try to advance, but just tries to take the current distribution as the stationary distribution and converge to it. And for this, we use you can use any MCMC algorithm, so like Langevin, Monte Carlo. And then predictor corrector just means we're interspersing these steps. Okay, so for the corrector, we'll use Langevin dynamics this is the algorithm for sampling using the score. The problem is if we use the simplest version of Langevin, we just overdamp Langevin, we need order d steps. Fortunately, there's an accelerated version, the underdamped version, which only needs square root d steps. Okay, so to go into more details, so that's sort of the broad strokes of what we need, of the ingredients that we need. So for the actual proof, we have to do this predictor analysis, the corrector analysis, and then combine them both. Okay, so for the predictor analysis, the technical ingredient we need is a score perturbation lemma. So So this is sort of one part that I kind of glossed over when I was talking about the SDE discretization. And this is because this is essentially the time discretization part. And for the SDE, it was sort of the space discretization that was dominant in the error analysis. However, if we look at the result that we have for the time discretization, so what essentially it is a bound between the score function of this, the score function of P, and then P convolved with a Gaussian of some variance H. Okay, so the original sort of time discretization result that we had looked like this, bounding this, the expected value of this thing squared by L squared DH. Now this bound is unsatisfactory because what we can look at this thing inside here, as we're sort of perturbing our distribution by some amount H, okay, and then we're squaring it, okay, so somehow if these differ by H, these should somehow differ, when you square it, should somehow differ by H squared, but we only have an H on the right-hand side. Okay, so somehow we only have, this is only saying some kind of a 1/2 Holder continuity. Okay, so we actually want an H squared dependence on the right-hand side here. So that's exactly the improved score perturbation lemma that we write. So it's in a slightly different form. But essentially, if you look at this and think about this as H times the derivative of P under this Gaussian perturbation, then what you want is actually an expectation over the derivative of the square of the derivative of the score function. Okay, and then we show that we can bound this in terms of L and D. Okay, so the idea behind here, so I'll consider instead of the OU process, I'll consider the simpler setting where PT is simply P0 convolved with a Gaussian of variance T. And we'll return to the key identity of the score function, expressing that as a posterior mean. So remember, I said that the score function is the posterior mean of the noise. So it turns out that by integration by parts, you can also write this as negative of the expectation under the posterior of the gradient of your potential V. Okay, yeah, and from this, we can then get a, by representing this, the score function as this expectation, then when we take the derivative, what we're changing is this, this posterior distribution where it's now conditioned on the distribution at time t plus delta t instead of t. Okay, so we can bound the difference between, where we have the expectation between distributions corresponding to t and t plus delta t. Okay, so this is the difference between these is bounded by the Lipschitz constant of our score function times the Wasserstein distance between these distributions. And we can bound this Wasserstein distance by the KL divergence between these two distributions by transport cost inequality, and then bound this KL divergence by the KL divergence of the joint distributions. And because this, the joint distribution has a simple form where the y just depends on the x, is just x plus Gaussian noise, we can actually explicitly compute this KL divergence. I'll note that here, this argument sort of uses the smoothest L in an essential way. Like one thing that's interesting is like, whether you can remove the dependence on L. Okay, so from this, what we get is this result on the expected value of the gradient squared of the score function. And from this, if we integrate this, we'll get a factor of h squared, so we're integrating this over one discretization step. And this is the expected value of this difference between the score functions at time t and s within a discretization step. From this, using a standard Gromwall's inequality, we can track how the same distribution Q evolves under the discretized and continuous dynamics of the ODE. And then we can repeat this for time 1 over L. Okay, so this gives us the Wasserstein error, after we run for 1 over L steps, or 1 over L time for the ODE. Okay, so the second part we need is the corrector analysis. And for this, we need, so remember in the corrector step, we're running the underdamped Langevin dynamics. And we need this short time regularization result where we say that the TV distance after running for a short amount of time, or the KL divergence, can be bounded in terms of the initial Wasserstein distance between the two distributions. Okay, basically, if you have two distributions, the Wasserstein distance is close. The TV can be very different because they could be mutually singular. But when you run underdamped Langevin, you're running an SDE, so it smooths out your distributions. So it converts this Wasserstein into a TV bound. Okay, so this bounds the TV in terms of the initial Wasserstein distance. And finally, we can put all these together so that we have our predictor step, we get a error bound at the end of running for time 1 over L. And then this is a Wasserstein error bound. The corrector step says that we can convert this Wasserstein into TV error at an extra cost of square root L. Okay, and then so we could get a bound for one stage of predictor and corrector, and then repeat that over time t, which will give us the final bound. Okay, so let me summarize what we have. We basically said that what these results show is basically if you can learn the score function, then you can sample from something close to your data distribution. And we show that first, the smoothing properties of the forward distribution can actually give you good convergence rates for arbitrary data distributions. And then second, if you use the ODE instead of the SDE, you can reduce the dimension dependence to square root D. There's a lot of open directions here to try use more ideas from numerical analysis or geometry to try and get or analyze faster algorithms. And I'll note that, in practice, what people actually do is tricks to get, not have to do a bunch of steps of a SDE, but do one or a few step generation. And then they actually try to somehow distill the neural networks doing multiple steps into a single one. So progressive distillation, for example. Okay, so this is a huge table comparing the kind of complexity for different algorithms. So what we showed is this, like, without the smoothest conditions, you can get this D squared complexity, which is later improved to D. And then for the probability flow OD, we get this improved square root D over epsilon dependence. I'll note that Yejie talked about her work with which uses the pure probability flow OD, which doesn't require the smoothest here, but does require an additional Jacobian error. Okay, so we have now reduced the problem of modeling our distribution to learning the score function. Okay, so the score function is the magic that turns our noise into art, or noise into samples from our data distribution. But this now begs the question of when can we actually, have this magic? When can we obtain this L2 accurate score estimate? Okay, how much time do I have? Okay, so maybe I'll just say some really brief, so here I only have some very high level things to say, essentially. So there's a ton of interesting work out there which tries to address the question of when we can have an accurate score estimate. So I can only give sort of a woefully incomplete survey here. I'll note first that there's a lot of interesting ideas you can take from statistical physics. So we call that this score, computing a score function is essentially equivalent to solving a denoising problem. Okay, so for distributions that are arising in some physics or statistics manner, there's a sort of off-the-shelf kind of algorithm that you can use for the denoising, which is called approximate message passing. So this has, in fact, been used very successfully to actually not just to actually get new algorithms for sampling from certain statistical physics problems. So this presents a case where the score function can be estimated. Okay, and then you can also show that this AMP can be represented by a deep neural network. Some work by May and Wu. I'll note that they do have some. You do only have a weak notion of error here, though, and the source of this is sort of the guarantees for AMP. If you could get better guarantees for AMP, then you can get better sampling. And there's also results that say, on the hardness side, that sometimes, learning via diffusion models might make your problem actually harder instead of easier, because you're now trying to solve this denoising problem instead. So they can actually make, compared to the problem of sampling directly using MCMC, sometimes diffusion models can be easier and sometimes harder. And on a different direction, you can also ask for structure on your distribution, such as being supported on a low dimensional manifold. And then there's also some work assuming that it's supported on a subspace. So a lot of these work focus either on the representation question, which is when you can represent the score efficiently with a reasonably sized neural network, and generalization, which is once you have found the empirical minimizer in this function class, that it will generalize. So I think there's less dealing with optimization. So it's sort of an interesting open problem to really get good families of distributions where you can get sort of end-to-end results on learning the score function. Okay, so I am out of time now, but I'll note that so we have some work with showing that we can learn exponential families with score matching. This is not diffusion models exactly because it's only the score, learning a score function at one noise level. And we have also some ongoing work with learning a mixture of Gaussians. Okay, so let me skip all these, and then there's definitely a lot more more interesting questions which I crammed onto this slide. Mainly, I think one big drop, I think it's very nice to have these kind of foundational results that says, once we get an epsilon close score function, then we can do the sampling, close to epsilon from the data distribution. But really, the truth is that our generative models are not learning a distribution that's epsilon close in one of these distances. Okay, so a lot of these metrics, kind of give some kind of unrealistic notion of closeness. And on the other hand, the kind of metrics that are used in practice are things like FID and inception score, and kind of not very, in a sense, not very interpretable. and unclear. So it's sort of unclear what the right metrics are. Yeah, so I think that's sort of a very interesting direction. And sort of what we want to think about, sort of what we want out of our generative models. There's more than just closeness in distribution. Okay, so I'll stop there and take any questions.
Great. We have time for one question while we change over to closing remarks.
Yeah, this isn't my result. Yeah. That aren't subspaces.
So you have this result about the failed differences between learned distribution and delta with there's no smoothness assumptions on this work on, correct?
Yes.
So how do you interpret that, like T delta? Is it sort of like by moving to delta, you like kind of evolve your distribution in order to smooth it out in some way, and now you can use smoother results?
Yeah, so P delta is our data distribution convolved with the Gaussian of variance delta. So if our distribution, for example, is supported on a lower dimensional manifold, then you can't hope to get like a KL guarantee to that, right? Because then that would mean your sampling process has to end up exactly on that manifold. Okay, but once you smear it out by a little bit, then it is possible. Yeah, and if you want to avoid having to compare to P delta, you could compare to P0 if you use a Wasserstein distance instead, though with somewhat worse rates.
Let's thank Holden again. So thank you, everyone. It's now time to wrap up. So we have closing remarks. I'll try to keep these relatively brief. How much of a delay do we have? I told this to go to the... All right. So at this point, everyone's brains are overloaded. So there's no content or math in the closing remarks. We just have several people to thank for putting all this together. It'll eventually show the speakers. So thank you to all these speakers. They were the backbone of the event, and fill it with content. The image is not going to come through. Well, okay. Now we have images, good. So also we have sponsors who provide the money and support for us to run this, have catering, offer travel support to everyone. So thanks to these great organizations. So maybe the co-organizers won't show up either. Okay. I was one of them. Many of them are here. Soledad did a ton of work. Gal, okay. There are many organizers. I don't know what's gone wrong with these. And our staff, in particular, Sydney and Veronica, are incredible. So if you two could come forward, we got you flowers. but Sydney and Veronica have been essential to running all the logistics today, and thank you very much. And okay, these photos come through, good. So thank you all. The community here is somewhat, essential. You bring the conversations and community that make this, better than Zoom conferences and things we've had to fight through in the past. So thank you all for being here. That's the end of the thank yous. Thank you for coming. And we'll see you next year. Organizers. Okay. Now it will.